All right, welcome to the next lecture, and we're going to continue moving through the material. So we're finally to the discrete components section here of the notes, and we're going to talk about resistors, capacitors, inductors, transformers, diodes, transistors, and maybe a couple other things. However, we've already seen some of these things, and we've already talked about them a little bit. And what I wanted to do before we kind of dug into more theory is I promised to do some hands-on stuff. So we're going to hook some circuits up, and we're going to draw some circuits and do a little bit of circuit analysis and kind of go over Ohm's law again, and with some examples, and then kind of build things and kind of go back and forth. So let's get into that right now. All right. So first thing is here. Let's refresh our memory on Ohm's law. And if we recall, Ohm's law, and I don't know, maybe we should pick a different color. What do you guys think? This color? Brighter color? Okay, so we've got Ohm's law, and it states that voltage equals current times resistance, which also means that current equals voltage divided by resistance, and it also means that resistance equals voltage divided by current. And then we also learned how to compute power, which is not part of Ohm's law, but we're going to put it here anyway. Power equals voltage times current. And then here's something interesting. Because of Ohm's law, we have, say, voltage and we have current here. We can write power in terms of voltage and resistance and remove current. So voltage equals current times resistance. So that's one thing. Current equals voltage divided by resistance. So if we replace the voltage here with if we replace current here with V over R, then we're going to get V times V over R, which of course equals V squared over R. Now this is really important. So power equals V squared over R. And this is important because it shows us that the power dissipation in a resistive circuit is proportional not to the voltage, but to the voltage squared. And that's why voltage is so important in systems, in computing systems, to lower the voltage down. So we've went from, in the 70s, from 12-volt systems, now we down to 5-volt systems in the 80s and 90s. Now we're down to 3-volt, 3.3-volt systems. We're down to 1.8-volt systems, 1.5-volt systems, and down to 1.2-volt systems even. And we keep trying to decrease that V so that this term right here decreases because it goes up as a square of the voltage. So keep that in mind. All right, so we have all of our equations over here, our modeling equations. So now let's go ahead and let's do some circuits again to kind of reinforce Ohm's law. All right, so we're getting pretty good. So I'm going to kind of go fairly fast. And let's get our calculators out and kind of follow. So let's do something. Let's say that we have a 9-volt battery. And in fact, let's not draw these as batteries. Let's draw these as just voltage sources. Okay, let's just keep things simple. So there's a voltage source. All right, and we've got a resistor. All right, and let's say this is a 9-volt battery, like we said, but we're drawing it as a voltage source. It's 9 volts. And then we've got this resistor. We'll call this R1. All right. And let's say that this equals, let's say 10K ohms, all right? So when we create this circuit right here, we've got a closed loop. We're going to get a current. We're going to get a conventional current that's going to go in this direction, always from plus to minus. That's the way that holes are going to flow, or conventional current. And now we want to compute what the current is, and let's call this I, all right? And so the first thing that is going to happen is, as we have a current which is flowing through the circuit, we're going to get a voltage drop. So in the direction of the current, so this is really important. So here's the direction of the current right here, right? The voltage over this resistor is going to drop plus to minus. All right, so there's going to be a voltage drop over the resistor, and there's going to be a current that's generated in this circuit. So the first thing is, what's the voltage drop? So if we come down and we draw ground right here, All right, so that's ground, and this is 0 volts, let's say. So at this node, remember, every conductor, all the voltages are the same in the conductor no matter where you are. All right, so we're at 0 volts here, 0 volts here, 0 volts here, 0 volts here. So we're at 0 here, and if we increase by 9 volts, we'd be 9 volts up here, right? So 9 volts up at this node, and we would be 9 volts at this node as well. And the entire voltage will have to drop over this one resistive element, so to get us back down to 0 volts. So we know that there's 9 volts that drop over that resistor, which makes sense because there's just one voltage source and one resistor. Okay, so let's do our math. So we know that V equals I times R. We want to compute I, so we know that I equals V over R. All right, and the voltage is 9 volts over R, which is 10K ohms. All right, so when we do this calculation, so everyone get your calculator out. So we're going to do 9 divided by 10x3, 10 to the third, and we get, depending on your calculator and what your calculator, what format it puts the number in. So we're getting, let's do it in milliamps, so we're getting 0.9 milliamps. All right, so we're getting 0.9 milliamps. Now, if we wanted to, we could turn that into, say, microamps, right? We could put that into microamps. If we did turn it into microamps, what would that look like? So we have 0.9 milliamps. If we want to turn this into microamps, we're going to have to move the decimal 3 times to the right. 1, 2, 3. Okay, so we would have 900 microamps. So there's 900 microamps flowing in that circuit with a 10K resistor. All right, and so there's one example right there. All right, so as we increase this resistance, the current is going to decrease, decrease, decrease. All right, so let's do another example. So let's see if we can delete all this up. And unfortunately, this tool, it does have a rectangular copy and delete, but it doesn't work exactly the way. Well, we're going to have to give it a try. Let's see if we can get this to do what we need this to do. And where did that tool go? It is right here. Let's see. We deleted the whole thing. Let's put that back. And this is a problem using these tools. Let's try lasso tool. And let's see here. I think the background is the right color. Okay, good. Okay, and let's go back to our pen that we had. All right. Okay, good. Okay, so now let's do another circuit. So let's say that we have, let's do batteries this time. All right, so we're going to have one battery here, and let's put another battery here. So we've got series batteries, and let's say that this is a 1.5 volt cell. Maybe it's a AA battery, right? So we could say that's a AA battery just for fun. And we could say that this is also a 1.5 volt cell, and we could say that this is, say, a AAA battery. So here's plus, here's minus, here's plus, here's minus. So we'll figure out what's going on there in a second. And now, and again, these are the symbols for resistors. We've seen this before, but we're going to really formalize this in the lecture in a little bit. Okay, so we have 2 resistors. So now R1 and R2, and again, you know, this course, we're not going to do an enormous amount of circuit analysis. We're going to do a little bit of circuit analysis. We want to learn all these things and how to do them. And one of the most important things when you're trying to learn circuit analysis is you have to be extremely detail oriented, and it's a lot of bookkeeping really. And if you don't do your bookkeeping and draw things properly, you're just going to get confused. So we've got resistor 1, resistor 2. We've got these voltages here. So let's call this V1 and V2. All right, and again, let's put a ground here. Okay, so we've got 2 resistors, and let's set these. So let's see here. Let's see. We're going to put 3 volts here. So let's go ahead and put a couple of common resistors. So we'll say that this is 100 ohms here, and let's say that this is 330 ohms here. Okay. All right, and you know, my omega symbols aren't as good as they could be. Maybe you can draw them way better, but as long as you know what you're talking about, you're good. Okay. So the first thing is, let's deal with the batteries over here. So what's going to go on with these two batteries? So we've talked about this before, and since we're putting these in series and minus the plus, the voltage will add up. So the total voltage will be 3 volts. So from here, this point here, to this point here will be a 3 volt difference, or 3 volt potential. So now we could simplify those batteries into one virtual battery or one abstract battery. That's 3 volts, but we're just going to say 3 volts instead of redrawing it. So now we've got 3 volts. We know we're going to generate a current here. So let's go ahead and let's draw the current. So let's start getting color, a little more colorful here. We might as well. All right, so we're going to get a current. The current's going to flow in the circuit. It's going to flow through both resistors. All right, in this direction, conventional current, right? Now, so here's some important questions, and now we're going to start getting into the nitty-gritty. We're going to start, picking up the pace a little bit. And so this current here, and let's call this current, we'll call this current just I. Question: the current I that goes through R1, is it the same current that goes through R2? So I want you to think about that for a second. Think about that for 1 second while I do some drawing. All right, so what do you think? So is it the same current, or is it a different current because we have different resistors? Now, whatever you said, let's think about this at an atomic level. So what is current? Current is the actual motion of electrons, or in conventional current, it's the motion of holes. The bottom line is we've got little charges that are moving around the circuit, all right? That's the current. Okay, so these little guys are moving around here, and they're going through the wire, through the resistors, and back through the power sources, and round they go. So one charge moves in at this end, has to go through here. That same charge has to go out through here, goes down the wire. Now it enters in here. Same charge has to exit out here and go on its merry way. So now, considering that, what's your answer, do you think? It's the same. The current is the same. So the current I that goes through R1 is the exact same current that goes through R2, and you can just look at that little analogy to kind of figure that out. All right. Okay, so now let's erase some of that. And okay, and so now let's look at something else that's going on. So now, since we have 2 resistors, we're going to have 2 different voltage drops. So here's where things get a little bit tricky. So if I were to ask you, what's the voltage at this node right here? So it's 3 volts here, and this is a wire, it's a conductor, so the voltage has to stay the same here. So it's going to be 3 volts here. So that we agree with, 3 volts. Down here, we're calling this ground, so this right here is going to be 0 volts. And it's going to be 0 volts right here. It's going to be 0 volts right here, because this is a wire, right? All right, so now here's where it gets tricky. So 3 volts up here, 0 volts here. What is the voltage right here? All right, so that's a good question. Now, there's a lot of ways that we can approach this. And again, we have Ohm's law. So we have this. So that's one thing to compute this with. Now, we also talked about a little bit about how batteries add up in series and parallel, right? Well, resistors kind of do the same thing. And we're going to go over this more. But right now, I'll tell you, and let's think about this. If we have 2 resistors, which are just pieces of carbon, all right, and we put them in series, what's going to happen is the resistance is going to increase, and it's going to increase as the sum of the individual resistances. Therefore, if we take these resistors and we just add them up, so we can say this, we can say, and let's go back to our yellow, we can say R total, or in fact, let's call it R12 equals R1 plus R2. All right, so if we were from this node here, this upper node here, to this bottom node here, if we were to replace that with one resistor and call it R12, it would just be the sum of the 2 resistors. So that would be 100 plus 330, correct? 100 ohms plus 330 ohm. All right, so that would equal 430 ohm, okay? So we would just have one giant resistor. So just for a minute here, let's just draw this resistor just kind of as a dotted line here. So this is kind of replacing. So this resistor, which we're calling R12, which we're calling R12, replaces these two resistors. And now we can just do the circuit as if these two resistors don't exist. So we have one resistor, we've got one 3-volt power source, and guess what? We're right back to the other example. So we've got V equals I times R. We want to compute I, so I equals V over R. So I equals V over R. What is our V in the circuit? It's 3 volts going over this big resistor, right? 3 volts. And what's R? Well, R is the value of R12, right? Which equals 430 ohms. Therefore, when you do that calculation, again, get out your calculator, 3 divided by 430 equals 6.97 milliamps. 6.97 milliamps. 6.97 milliamps. All right, so this I right here, I equals 6.97 milliamps. Now, let's forget about this virtual resistor or the series sum resistor to help us do the calculation. And now let's pretend there are two resistors back in the circuit again. Now we know that the current in the circuit, I, is 6.97 milliamps. It's the same current in R1, it's the same current in R2. So now we can compute what the voltage drop over R1 and the voltage drop over R2 is. So let's go ahead and do that. All right, so let's do that in another color over here. So we want to figure out voltage drop over R1, and we're going to figure out the voltage drop over R2. All right, so the voltage drop over R1 is going to be right here. So this is going to be V R1, and the voltage drop over R2 is going to be VR2. So VR1, so let's look, what's our equation for voltage? It equals current times resistance. So what's the current? It's 6.97 milliamps. 6.97 milliamps. All right. And what's our resistance? 100 ohms times 100 ohms. So we'll compute that in a second. Then VR2 is the same current, right, which is 6.97 milliamps. And let me fix that. That looks like microamps. Sorry about that. Milliamps times our resistance, which is 330 ohms. All right, again, let's get out our calculator. We could do this in our heads, but let's not. 6.97 milliamps, 6.97 x minus 3 times 100 ohms equals 0.697. 0.697, so 0.697 volts. All right, let's do the next one. Voltage over R2 is going to be 6.97 milliamps, 6.97 milliamps times 330. So it should be about 3 times as much, right? So it's 2.3 volts. Now, all right, and you know we're losing a little bit of accuracy here because I'm clipping some of these decimal places. The voltage drop of these two resistors has to equal 3 volts, right? So this number here plus this number here have to equal 3 volts. And when I'm clipping these off, and I'm not going as many decimal places as I should, or rounding, we're going to get a little bit of error. But that's okay. The reason it's okay is these resistors in the first place are only 5 or 10% accurate in the first place, so it doesn't even matter. All right? Okay, so now here's the interesting part. So over VR1, we dropped 0.697 volts. So VR1 has a voltage drop of 0.697. All right, and you know what? Just to make things happy, let's call this 0.7. 697. Let's just round it up to 0.7 volts. Okay. All right, and then VR2 is a voltage drop of 2.3 volts. 2.3 volts. All right. So the first thing is they do add up to 3 volts. So that's good. Now, what's the voltage V? I still want to ask this question. So we're at 3 volts right here. We drop 0.7, so we must be at 2.3 volts here. And that makes sense because the voltage drop over R2, or VR2 we're calling it, is 2.3. So whatever we're here, we drop down 2.3, which we computed. Or we could say at ground, we're here at ground, 0. And if we dropped 2.3 volts over R2, that means if we go back up, right, in the other direction, this would also be 2.3 volts. Whatever the drop was, if we go up in the opposite direction, it would be 2.3. So there we go. So there's a complete circuit analyzed. All right. And so we've got we did a series resistance, we had a series couple of batteries, we computed the current, we computed the voltage drops at all the different nodes, and this is basically what we're going to use Ohm's law. And there's some other laws that we're going to learn down the line a little bit called Kirchhoff's laws, and we'll go through those, which will help with circuit analysis. And remember, we just want to know how to do this so that if we have to compute something, we can get it done. Okay? All right, so now let's go ahead, and I've been promising to do some actual hands-on electronics here, and finally we have enough information to do so. All right, so we're going to go to the bench and we're going to build some circuits, some little ones that kind of use some of these ideas, and what we're going to do is we're going to turn LEDs on, and we're going to power them up and do some stuff with that. All right, so we're going to go over to the bench. So first thing is, let's just delete all that. So that's gone, and then meet me over here at the bench, and let's start playing with this stuff. Okay, so what are we going to do? We are going to build some stuff here. All right, so the first thing is we've got this little solderless breadboard, and let's do a quick discussion about this again. And again, my process when I teach is I like to show you things over and over in different ways so that you can kind of get the hang of it and see how it's used, so you don't just see it and then we jump right into it. So here's a solderless breadboard, and here's another one. Here's another one. Right? Here's another one. Okay, and all of these are just simply different sizes, different manufacturers. And for example, these guys that have the you can see they have the two rails up here, this blue and red, and this one's black and red actually. In this case, if we look here, these rails are all connected together. So that's connected, and then the one under it is connected, but they aren't connected to each other. And typically you'll use these for power. And then all of these are connected vertically in columns, but not across this trench. And that's because we're going to put chips in there and whatnot, and this is made a very special size so that the distance between holes is 0.1 inch, because that's a very common pitch for components. All right, and you can see they have these little bosses sticking out, and this is because they can be connected together, and you can make bigger ones out of them. And this is just simply a different manufacturer. And then another thing you'll notice, there's numbers on here, and that way you can kind of keep track of what pins are and so forth. And then in this case, you see all these are connected here, and then all these are connected here, but they aren't connected to each other. So you can see I've ran two wires connecting these two rails so they go all the way across like that. And then here's a little guy. And this is real cool and real small. It has no power rails, but this might be something if you want to just hook something small up. And then everything comes, you can get any color you want. They can get transparent or whatever. Now you might have noticed this paper on the back of these. Typically this is a double-sided tape kind of thing, and it's already stuck to the board. If you pull this off, it'll be adhesive, and then you can stick it down to something. All right. Okay, so and then this last one here, I just wanted to show you this. So this is a very old one, and this is Archer, and this is from Radio Shack. And I mean, honestly, I probably got this 20 years ago. And so this is an old Archer Radio Shack solderless breadboard. I've used it hundreds of times, and it's still working. And again, you see it's got this, and so forth, so that you could stick these things together and make bigger boards. Now these used to be quite expensive. Now the prices are gone down, and of course there's so many Chinese vendors you can get things for a lot less. But when I used to build things 20 years ago, I'd have to get 20 of these things to build a gigantic board. But now you can actually buy these. So for example, here's another one. All right, Global Specialties is another company that you can get these things from if you Google. And this one's got two built on it, plus it's got this nice metal board on it, right? And if you look under here, it's nice and metal, very, very strong. Now, the other thing that you gain, and we're going to talk about this a little once we get to a little bit more advanced subjects, this metal plane under here can act as a ground. It can act as a shield also. If you've heard the word Faraday shield, it can act as a shield, and fields can't get through this. Electric fields cannot get through this. So that's why we like this. And it also gives a place for the electronics. If we ground this metal, it gives a place for all the fields to terminate on. So that's a really good way to build things. And then you see there's a VA here and VB. And if you want, what you can do is, and I'll let you take a look at these up on Edge if we can see them, if the camera, yep. And so what you'll do is you would take your power supply wires, which might be coming from something else, let the camera focus, and you put them in here, and there's little holes in here. All right, and let me, again, see that little hole, and I put it through the little hole, and then I would tighten this down, and maybe this goes to the power supply, and then I maybe put another one in here, all right, and then what I would do is I would take this wire and I would put it into the plus. So now we would be running power into this, and then we can run power out of it. Or there's other connectors that we can do this with, and then we would connect ground, and this might be our negative, this might be our positive, and this might be ground, all right, which would also be connected to the negative typically. All right, now, and then there's even bigger ones here, like that. And so you can see they just get bigger and bigger and bigger. And in this case, this is you can see this here hopefully in the camera. So we got V sub A, V sub B, V sub C, and ground. So this might be because you have 3 different voltages. All right. And then this these connectors here. Again, let's take a look at these connectors. And then in your kit, or the things that you could have bought, you have different kinds of wire and whatnot. And so you can you could have either done things with just wire. You can cut it and strip it at each end, right? Or if you went and wanted to get some of the other wires, then you should have been able to get some of this stuff here. And these have, for example, females on one end, and then females on the other end. They have a certain length. And then we can go, and there's all kinds of variations of this. And this one right here has males on each end, so they plug right into these boards, really nice. And this just makes it really easy to hook things up. You can just plug them right in and then hook things up, right? So that's just part of construction. We're going to talk more about that as we go. All right, now another way that we might hook these things up is with what are called banana connectors. So, for example, so if you look at these connectors right here, and you see their ends, and let me put this on the zoomed screen for you. So take a look here. Right, you see that, and they're kind of spring-loaded, and that's kind of spring-loaded as well. And what we can do is we can actually plug these in here, like this, and plug it in, and plug it in, or plug it in to the red one if we want, because we want to be color-coded. All right, and then these ends, in this case, happen to be these little guys. So we could connect those to a battery, or we could connect them to something else, right? Okay, or another thing that we could do is we might have these kind of ends, and these are called alligator clips, all right? And we can plug those in, so there's metal in the tops of these things. So we can plug these in like this, and we could plug this one here, the ground, in there, make good contact. Now the other end of these things, right? So where would the other end go? They might go, they might go to your power supply, all right? So let's take a look at that right now. So in this case, so here is a power supply, and those 2 cables right here are actually plugged into that board that we just looked at, all right? And we can turn this power supply on. And so this is an adjustable power supply, and it's got a fine adjustment and a coarse adjustment. And then this little button enables power out. And this is what you're going to want if you're going to be doing a lot of electronics. You need bench power supplies, they're called. And here's another power supply. This is a 3-channel power supply. It's a little bit, the LCD screen's a little bit hard to see. Let's see if we can get it to cooperate, the camera. And this has 3 different channels. It's totally programmable current and all that. And this is very, very, very good. And these power supplies run anywhere from $150 to $300 or $400 for the small power supply. So this power supply you might be able to get for $100, $150. You can get them cheaper on eBay and whatnot also if you look. And that 3-channel could be, like I said, $300, $400, $500, depending on where you get it and what you get. All right, so you can see I have this set at 5 volts, and let me just play with this for a second just to show you. And I can put the voltage up, I can put the voltage down, and then I can play with the fine adjustment. And it says it's 5 volts. Now, why does the current say it's 0? Because we have no load on it. So I'll turn this on, and when I turn this on, that means that these lines are now hot. All right, so there's 5 volts, ground and 5 volts are here, and whatever I have hooked up would start drawing current, but since we don't have anything hooked up yet, we just have it plugged in the board, nothing is happening. So I'm going to disable the DC out, but I'm going to leave the supply on, all right? Okay, so we're back here, and so I've decided I want to use this board, and I need to get power in here. So what I've done is I've taken our 2 alligator clips, all right, and these are going to be hot in a moment from the main power supply that we just looked at. And so what I'm going to do is somehow I've got to get that power into here. And so one way to do it is you can see I've got these little posts, and these posts I've just taken apart. So if you take a look, so this is called a header, right? And it's just this is got 0.1 inch pitch, and it's just a bunch of contacts that can go into a printed circuit board. But you can pull these posts out and do things with them, right? And so that's what I did. So I pulled a couple of those posts out, and I put one here, and I put one here. One is on the plus, and one is on the minus on the top and the bottom, respectively. So now what I'm going to do is I'm going to connect that guy there. There's the red, and there's the black. All right, and we're going to connect that there. All right, and now when I turn that power supply on, we're actually going to, when I turn that power supply on, this board will be hot. All right, so we're going to do our electronics with the board hot and cold. It's only 5 volts, so we can't do too much damage. All right, but we want to keep that in mind. Now the power supply, if we were to short something, it actually has short protection, so it'll be okay. All right, so we don't need to worry about it, but we don't want to short it nevertheless. Okay. So what are we going to do? So let's have some fun here. So the first thing is let's go back and let's draw a little circuit that we're going to try and hook up, and we're going to see what the circuit does. All right, we're going to see if it does what it's supposed to do. Okay, so let's go back to the screen here. All right, so we're going to go back to the drawing tool here. All right, and let's do a simple circuit. So we've got our power source. Let's do 5 volts, which we said, and we're going to go ahead and we're going to put a resistor in here. All right, and this resistor right here, let's say that this equals to 100 ohms. All right, and that's going to have a current that's going to go through it, right? We're going to call that I, and I is going to equal what? V over R. V equals 5 volts, R equals 100 ohms. Again, get your calculator out until you can do these in your head, and I don't want to do them in my head yet until you're comfortable. All right, so that's going to be 50 milliamps. All right, 50 milliamps. So if we build this circuit and we measure this current, we're going to get 50 milliamps. Now, how do you measure the current in a circuit? To measure the current, we need to use the meter, and we haven't learned much about meters, but we're going to. But we have to use it in amp mode, and we have to put it in series. So what we got to do is we actually have to break this circuit open, and let's see if we can be so bold to find the eraser here. All right, and we got to break the circuit open. And let's get back to our pen. And then what we got to do is we have to put the meter inside of the circuit. So we go like this, go like this. Here is our amp meter, like this. All right, and there's our little amp meter, and plus to minus, and then this will measure the current for us. All right, and we should measure this 50 milliamperes. Okay, so let's build this circuit and let's see what happens. All right. Okay, so the first thing when we build circuits is we want to kind of get all our parts here so we kind of have them. So here's a few little parts. I've got some LEDs, I got some switches, I got a couple resistors here. All right, and we need our 100 ohm resistor for one thing. So so I looked here, and I believe I've got a 1K resistor and I've got a 100K resistor. So I need a 100 ohm, all right? And we're going to learn color code, but 100 ohm is brown, black, brown, all right? Brown, black, brown. So I'm going to look for that, and while I'm looking at that, I want you to look at this, all right? And this is a resistor color code, and we're going to go over this. So take a look at that while I'm doing this and looking for a 100 ohm resistor. So we're looking for brown, black, brown. brown, black, brown. Okay, so I found my brown, black, brown. And so if you look at it, the first band is brown, which represents a 1. All right, so now let's go under. So here's the resistor. All right, brown, black, brown. Let's go to the zoom screen. All right, and all right, so we've got brown there, and that's a 1. And then the black is 0, so that's 1, 0. And then we have this multiplier, which is a multiplier. It's brown, which is multiplier 10. So we got 10 times 10, that's 100 ohms. And the final band is gold, which means 5% accuracy, I believe. Yeah, plus or minus 5% tolerance. And then silver is 10%. Okay, all right. So we have our resistor. So we have all our parts here that we want to deal with. All right. Okay, so now we need stuff to build this with, and what I'm going to do is I want to use just plain wires. And so these are all pre-cut, and what I usually do is I make some long ones, I make some medium ones, and I make short ones. I don't cut every single wire to a perfect length. I usually cut them in a binary. So I might make one 8 inches, 4 inches, 2 inches, and 1 inch, right? Each one is half the previous or twice the previous if you're doing bigger. All right, and that way you can kind of hook everything up and make things neat and nice. Or you could use your pre-made wires, right? These kind of things. If you decided to have these and you know bought these in your kit, and I highly recommend these because they're very, very easy. You don't have to cut anything. All right. Okay, so let's go ahead here and we're going to build our circuit. All right, so let's do this. Now let's come down on this a little bit. We're going to zoom in just a little bit here. All right. Okay, now the circuits that we draw on the computer, right, are abstractions. And the real circuit doesn't need to look the same way geometrically, it just needs to be connected the same way, right? So we have power going through a resistor, going to ground. So that is as simple as it gets, through a 100 ohm resistor and then going to ground. All right, so what we're going to do is we're going to put our resistor inside here. Okay, so we've got our resistor in there. Now, one thing you notice, see how high that is? Typically, we don't like that, right? It's just horrible. It's flying in the air. So I'm going to take that resistor, and I'm going to take my cutters, which I have right here, and I'm just going to kind of cut half of that wire off, right? I'm just going to cut half of that wire off on both of those leads. All right, now, and this is why you want to have protective goggles on so that this doesn't go flying in your eyes. All right, but another thing you can do is kind of hold it as you cut it. So I just cut it. And then I have a little piece there. I'm going to throw that away. There's a garbage over here to my right. And I'm going to cut the other one. All right, just cut it like that. Okay. All right, and then, you know, I like making really neat circuits. So I'm going to just take my pliers here and straighten that out real quick. Okay, so now I'm going to plug this resistor back in here. All right, so cool, we got that. And maybe we can zoom in just a little bit more even. I think we can get away with, yeah. All right, now we need to connect this thing to power. So we just need to connect it up to plus and minus. All right, so we're just going to find a couple wires. And so, you know, these wires might be all bent up. Now, some people just plug this in. No, don't do that. Pull the thing out, straighten it out, clean it up, and try and get, you know, we only need a wire that'll go from here to here. That's it. Very, very short, right? So we don't need this long wire. We could use this long wire. So again, you know, what I'll do is when I'm building things, I'll pour everything out on a table and kind of spread them out so I can kind of see what's going on. So you're not going to be able to see this, but I'm going to be able to see this so that I can kind of work and do this in a clean fashion. So now I found some little short ones. I've got many short ones. I'm going to take that. I'm going to just bend that over, and be careful, everybody, when you're bending things and poking things. These wires, you'll impale yourself a lot. I have put holes through the tips of my fingers many times. Not going to kill you, but it doesn't feel good. All right. So we're going to put that in there. Nice. Okay, we're going to get another short wire. I got another one right here. I'm going to clean this up, straighten it out. Okay, bend it, get it all ready. Then I'm going to go ahead and put it in here to the ground. All right, so we've got the black going to ground, we've got the red going to red, and now we have our circuit right here. Okay, so let's go ahead and let's power this up. So I'm going to go ahead and turn on the power supply. All right. And I look at the power supply, and it's actually saying 50 milliamps. So let's go back over here. to the computer, and let's go back to our calculation here on the screen, and you can see we have our circuit, and we computed 50 milliamps. All right, so we have that 50 milliamps, and that's exactly what we're getting. So, okay, that's good. Now, let me actually show you on the power supply. So go ahead now and take a look here at the power supply, and you can see it's 0.05 amps, which is 50 milliamps, right? So that's accurate as it can be. All right, so that's good. Okay. All right. Now, the problem is, well, how do we measure this? So we're looking at the power supply, we're using that to kind of tell us what's going on, but how do we actually measure this? All right, so what we need to do is we need to get a meter. So we're going to get one of our multimeters, and we're going to create some room. And one of the things you're going to learn real quick when you do electronics is you do not have enough space. There is not enough space in the universe to build stuff. You need just countless surface areas. All right, so I'm moving things out of the way here. Okay. All right. I think I'm good. All right. So now what I'm going to do is I'm going to get a meter here, and I'm going to put the meter next to this, and I'm going to unfortunately have to zoom out so we can see what's going on here. So we're going to zoom out, zoom out, zoom out. Okay. So I'm going to zoom out, and we've got our meter here. All right, and so the first thing I'm going to do, again, we're going to learn more about this, but we can just figure it out now. So we're going to put the meter on milliamp mode, and you see it's blinking at me, and that means, hey, put the cable in this connector, in this socket. So I'm going to put the test probe in that socket, and now I've got my two test probes. And so this is ready. It's going to read milliamps. It's on milliamp scale right now, DC, so we're all good there. Now, what do I do with this? What do we do with this? We have to somehow put this inside of this circuit, right? And this is not very easy. So I have to undo one of these power supply lines and then kind of insert this into here, all right? And let the current flow through the meter, all right? So there's a couple ways to do that. One, we could just kind of undo this and let it flow through the meter, all right? So let's give that a try. So first what I'm going to do is I'm going to turn off the power supply. So I just turned it off. All right, and now I'm going to undo the ground line. All right, now I'm going to turn the meter back on. All right, and now what I'm going to do is this. So we have positive conventional current flowing through down here, and now it can't get anywhere. It's got to flow through the meter. So now I'm going to actually touch the probe here, and then I'm going to touch it to ground. And as I do that, the meter will complete the circuit, and then the current will flow through the meter, and we'll be able to view it. All right, so let's give that a try. Here we go. And there it is, 49.2 milliamps. So 49.3 now. So amazingly, that works. So we can, we made our first circuit, and we measured the current, and it did what it's supposed to do. So now I'm going to put the wire back in, and I'm leaving the power supply on, and it's okay because there's not much to short here, so I'm pretty confident I'm not going to damage anything. Now on the meter, I'm going to put this probe back into voltage, the voltage port. I'm going to put the meter into voltage mode here, and I'm going to measure what the voltage is. Okay, so we checked the current here for our circuit, and it was 50 milliamps like it should be. But another thing that I want you to get in the habit of doing is verifying your equipment. So don't just assume something's correct because one piece of equipment says that the value is what it should be. So over on our power supply, if we look at our power supply here, let's see if we can get this in focus a little bit better. All right, so it says 5 volts, and that's what the circuit should be generating, the power supply should be generating to our circuit. The question is it? So now let's take our meter, we put it back into voltage mode, and let's actually check the voltage. All right, so the top rail would be here, and the bottom rail would be here, so we touch our probe, and get it on there. All right, and you can see that the meter is reading 4.97 volts. So that is that's correct, and that's, you know, as accurate as you're going to get. And again, I just measured it from the two rails. I could measure it from right across the resistor, and it technically it'll actually be slightly different because we've got different lengths of wire, and these wires actually have resistance in them. But for all intent purposes, the wire is a perfect conductor. And so 4.97, so we're happy with that. All right, so let's go ahead and let's build another circuit. All right, so let's take a look at some of our components here. So I have some LEDs here. I've got some momentary switches. All right, and I've got some more resistors. So let's take a quick look here. So we've got 3 LEDs here, and we haven't learned too much about these yet, but we will. So they're just light emitting diodes. This one's a bicolor, I believe. All right, and here's a red one. And you can see that large, let's get something to point this. So this large internal structure right here, this is usually the cathode or the negative side. All right, and then also you can see that there's a flat side, and you can see it right there. You can see the specularity. See that flat side? And again, the flat side usually is the negative side, or the cathode. And then we've got a green one, same thing, and the flat side, again, marks the negative side. All right, so we're going to play with those a little bit. Then we have these little momentary switches. All right, and these are a lot of fun. So little momentary switches, and these are through hole. All right, and I've cut them off the tape, and you press them down. And when you look these up and you try to find the part numbers, so these are called usually soft momentary switches, and then you won't be able to hear this, but there's a click sound. And the amount of force, so there's a couple things that are interesting here. So if you look at this, the amount that this plunges in, so I'll push it here so you can see that. So that's the travel, all right, the depth that it plunges in, that travel, and that's usually measured in millimeters or a fraction of a millimeter. All right, and then how much force it takes to press this down is a force measurement that you'll see on the button. So if they're really hard or really easy to press, okay? And then here is a blue one, and you can see this one has got a larger plunger, and this one's got a little bit more travel, all right? So, and then we got a couple resistors, all right? So what we're going to do is we are going to go over back to our screen capture, and we're going to draw a circuit, and then we're going to implement the circuit. Okay, so we're back here on our screen capture. So the first thing let's do, let's erase this. All right, and so let's do something fun. And again, we're doing things out of order sometimes, and we're going to talk about discrete components at length in the next lecture. But I like to kind of experiment with things and show you things so we can just kind of get some hands-on feel. All right, so let's make a circuit. So we've got our 5-volt power supply. All right, so let's start there. So we've got our plus minus. Let's make this circle a little bit nicer. So we've got our plus, we've got our minus, we've got our 5 volts, and we can change that, of course. All right, so let's do a couple fun things here. All right, so what we're going to do is we're going to take a, let's go ahead and let's take the momentary switch. So we'll take the momentary switch, and this is the symbol for the momentary switch, or one symbol. You may see lots of them. Sometimes they might look like this, or they might look like this plunger version. So anyway, that's a momentary switch. So we're going to take that momentary switch, all right? Then we're going to add another momentary switch here, all right? Like so, okay? Then we're going to add a couple resistors, like this. Now what we're going to do is we are going to put some LEDs in here. So let's go down here, and then the symbol for an LED or a diode looks like this. It's a triangle and a line. All right, this is the cathode side, and this is the anode side. So positive current or conventional current is going to be flowing this way through the circuit. We're going to draw it in a second. So that's a diode, and then if you want it to be a light emitting diode, a lot of times the symbol will be 2 arrows going out or an arrow going out. So let's do the same thing here. Draw another LED. Okay, and plus to minus. All right, and then we're going to tie all of these together like that, and we're done. And this is, we'll call this ground here. All right, and these are all tied together, so we can put little dots there if we want to emphasize that. All right, so let's name these things. So we can call this SW1 for switch 1, but since this is a momentary switch, right, a lot of times if you just say switch, that'll mean a switch that stays on or stays off. So since this is a momentary switch, a lot of times you'll see MOM, momentary, so 1, all right, that's one way to do it, but we're going to call it switch 1, and we're going to call this one switch 2. We're going to call this one R1. We're going to call this one R2. So we got these two resistors, R1 and R2. And then we're going to call this, we're going to call it LED1. And we could call it just D1 for diode 1, but we're going to call it LED because it is an LED. All right. And when you're doing electronics, a lot of times people will use kind of abstract reference designators. So R definitely is a resistor, but you'll see things like J's and H's for connectors. It doesn't hurt to put what they are. So you can put switch or you can put con for connector. So, feel free to use larger strings to describe things. It just helps. All right, we've got all the memory in the world these days. Okay, so here's our circuit right here. So right now, when these switches are open, so these momentary switches, these are going to be normally open switches. When we press it, it's going to close these contacts. When we press the plunger down, the contact will short, and same thing here, it'll short and turn the circuits on. All right, so that's how they'll work. All right, so when we do either of these two circuits will be completely independent. There'll be two independent currents. So if we were to close SW1, what's going to happen is we're going to get a current coming out of the battery. It'll go through the resistor, it'll go through lead 1, and it will come back like this. And we can call this I1. All right, by the same token, we use a different color here. When we close SW2, we're going to get another current, which is going to go through here, like this. All right, and we're going to call this current I2. Now, what's going to happen is we're going to have I1 up in this top area. We're going to have I2 in this top area through R1 and R2. But when we're down in this bottom rail, I1 and I2 are going to sum up. So we're going to have both of those currents because both have to return here. So being specific here, we have I2 here. All right, and then we have, what do we use, this kind of green color? Then we have I1 here. I1 here. All right, and then those are going to sum up. So right down here, we're going to have, in this area here, we're going to have I2 plus I1 will be the current here. All right, and we can call that something like, we can just call that I, or we might want to call that I3. All right, so the currents will sum up. So we got one current in the top, we got one current, and so in this top loop, we got one current in this other loop. So they're completely independent. So they're being powered by this power supply completely independently. But since we're summing the currents at this node right here, the currents will sum up and return back to the battery. All right, so the question is, we want to build this circuit. All right, so we want to build this circuit and put real values in here. So for R1, let's go ahead and let's put 100 ohms. And for R2, let's go ahead and let's put 100 ohms. And for LED1, we'll make this one, let's make this one a red LED, all right? And we'll make LED2 a green LED, all right? So we should have two LEDs, we've got two resistors, we've just got two independent circuits, and then the point is these currents are going to sum up here, and then they'll return back to the battery. So the battery, one current splits off in this direction, one current splits off in this direction, goes through, and then they sum back up and then return back to the battery. So we don't exactly, we can definitely analyze this circuit right now with Ohm's law, more or less, but for now, let's start off and make a couple assumptions here, and I'm going to show you how these things work before we have gone through what diodes do. So let's just take a look at this top loop here. So in the top loop, all right, we have 5 volts. Let's assume this switch is closed. we have R1, which is 100 ohms. And let's forget about the diode for a second. So we just have 5 volts and we've got 100 ohms. All right, so how you do these kind of LED circuits is the following. LEDs have a special property, and once, or diodes in general, once they're forward biased, and we'll learn what that means, biased, but once they start to conduct, their voltage stays the same almost. So as they conduct, no matter how much current goes through them, their voltage only varies very, very, very little. So they have a forward on voltage, and that on voltage or forward bias that's required to turn the LED on can vary depending on the doping of the LED, the type of LED, and so forth. All right. So right now, these two LEDs, we don't know exactly what their forward voltage is that's required to turn them on, but from experience, I can tell you that it's usually in the ballpark of like 2.1 to 2.5 volts for some of these off-the-shelf LEDs like I just showed you. So you need 2.1 to 2.5 volts to turn these things on. Once they're on, this voltage will roughly stay the same no matter how much current goes through there. So what we do first in an LED circuit is we put a resistor in here to limit current, because if we have no current limiting resistor, the circuit will just run full throttle and the LED will potentially burn out based on whatever its internal resistance is and the battery. So what we want to do is we put a resistor. So coming back to Ohm's law, right? We have V equals I times R. All right, and so we want to know what the current is, so we want to know I equals, and that'll be V over R. And in this case, that's going to be 5 volts over 100 ohms. Okay, so go ahead and get your calculator out. So we've got 5 volts divided by 100, and that's going to equal 50 milliamps, just like the previous circuit, right? So we've got 50 milliamps. Okay, that is way too high. All right, so these LEDs, 10, 20 milliamps is kind of what they like. So that's too high. So what we need to do is we need to reduce this current through the R1 and R2. So we need to limit it some more. All right, so maybe what we're going to do is we could double it, and then that would half the current. So we're going to do something along those lines. So what we're going to do is we're going to go look over for some values, and what we're going to do is we're going to get rid of these hundreds, and we'll say, 220 to 330 ohm resistors. Okay, so 220 to 330 ohm resistors. So that'll limit the current. So once the current is limited and we know the circuit's not going to burn out, then what's going to happen is the LEDs themselves are going to act as resistors, and they're going to drop a voltage. But this voltage is not dependent really on the current. Once they're forward biased, the voltage will stay the same as the current can change. So the current in the circuit is actually going to be different than what we set the limit current to. It'll be less. All right, but this will be its limit. Okay, so we know that we want to use probably 220 to 330 ohm resistors. Let's hook the circuit up like this. So we're actually going to build this circuit right now, and then we're going to try and measure some things here. All right, so let's go over and build the circuit. All right. Okay. All right, so we've got our board here. We've got our solderless breadboard, and now let's go ahead and let's pull out the resistor that we had in there. Okay, and it's actually warm. So it's actually warm to the touch. All right, so the first thing that we need to do is we're going to kind of make two circuits that look the same. So if we look at our schematic back on the screen there, and remember what was going on there, we have power going to a switch and then going to the LEDs. All right, so what we're going to do is we're going to put one switch here like this, and we're going to put, in fact, yeah, we use two different color switches. So we've got our two switches here. All right. Now we're going to hook these switches up to the positive rail. All right. So first, the first switch. All right, to the positive rail. We got that. Okay. Now we'll do our other switch to the positive rail. Okay. And, again, you got to kind of open this up and look at, what's being connected to what here and make sure you're connecting things right. So I'm doing that as I'm doing this, talking to you here. All right, so we got those. All right, now we are going to then go through our resistors. So we can go over this ridge here, over this gap, and put our resistors in there. All right, so we're looking for something like 220 to 330, and let's see what we have here that I can find quickly. Okay, so I believe, I think we got lucky here. So red, brown. So this should be 220. So here's red, brown. And again, we're going to learn resistor color code in a moment in the next lecture. But let's put our meter. All right, we're going to put our meter on resistance. Okay, and let's scoot this over for just a second here. And we're going to measure our resistors just to make sure. So I'm going to put that there. I'm going to put that there. All right, and we let it go ahead and measure. And it's adjusting, and you see it says 215 ohms, and that's within the 5%. So we got one of our 220s. And then here's another red, brown. And then you can look at it on the zoomed screen here. There you go. So red, brown, and then gold. And you know, these are not easy to see. And even if you have really, really good eyes, the colors are sometimes hard to discern. And sometimes, you know, purple looks like brown. So we got our two 220 ohm resistors there. Okay, so let's bring this back. Bring this back in the middle here. All right, and now we've got these really long leads. Now normally I would cut these leads, but I'm not going to cut them. We're going to leave them long for right now, but we don't like that. We don't like long leads. All right, so we're going to take those from our two switches and connect those in there. All right. Okay, so we're getting there. So we've got our two switches, we've got our two resistors, and now we simply need to go through our LEDs and then down to ground. All right, so we could just connect our LEDs right in here and then right in here and be done with it. So let's do that. All right, and we're going to use red and green. So here's our first LED, and again, I'm going to look at the polarity of this. So if we go over to our zoomed screen here, zoomed camera, so there's the negative, so I'm going to put the negative cathode is going to go to ground. All right, so we're going to go like this. All right, and then here's our red LED, same thing. Okay, so now let's zoom in a little bit here. All right, so there's our circuit. Okay, now let's go ahead and turn the power on. So we're going to turn the power supply on. So the power supply is on. And now when I press these momentary switches, these LEDs should turn on. So let's see what happens. So I'm going to press this first one, and it turns on. Cool. And press this one, and it turns on. Now, as I press these, let's go ahead and let's take a look at the power supply. So I'm going to put this camera on the power supply. All right, and now I'm going to press the first LED on, and you can see there's some current there. Now remember that current meter on that power supply is not very accurate, but it looks like 0.01, so it could be, remember, we don't see what that last digit is, so we're not quite sure, but there's definitely current. And then here's the other LED. Now when I press both of them, we should see the current sum up. All right, because the current is being sourced from the power supply through both individual circuits. Okay, so, all right, so that's all working the way that it should. All right, so that's cool. Now, let's do a couple measurements here. All right, so let's go ahead and let's take our multimeter. All right, let's zoom out and give ourselves some room. All right, and one thing let's try, let's put this in voltage mode. Okay, so now what we're going to do is we are going to measure the voltage drops over the resistors and LEDs, and we're going to see if it makes sense. Okay, so when we power this circuit, when we close this switch, we're going to get current through this circuit, and then if we close this switch, we're going to get current through this circuit. We're expecting a voltage drop over the resistor and a voltage drop over the LED. Once the LED is forward biased, right, that voltage drop will roughly stay the same no matter what the current is. All right, so that's one thing. So let's go ahead and measure this. All right, so we've got our meter. It's on voltage mode. I've got my probes. So I'm going to put the positive probe up here on the top of this LED, and then I'm going to put the negative probe right here. And of course, it doesn't really matter. We can flip it around. It's not going to hurt anything. The voltage will just measure negative. All right, so now I'm going to press the momentary switch, which is going to turn the circuit on, and current is going to flow. So let's watch what happens. And we get 2.9 volts over that first resistor. So we get 2.9 volts over the first resistor. All right, and the resistor is 220 ohms. So if we take our calculator, right, so voltage equals current times resistance. Current equals voltage divided by resistance. So we have 2.9 divided by 220, and that's going to give us 13 milliamps. 13 milliamps. All right, and that seems about right because the power supply in the second decimal place put a 1 there, so it really was a 13 if we could see the other decimal place. So it's about 13 milliamps is flowing. So we've got a good amount of current here. And we want to usually put these at 10 to 20 milliamps and based on their specs. Okay, now let's measure the voltage over this LED. So the voltage drops in the loop have to equal the source voltage. So we had 5 volts to start with. We just dropped 2.9. We better be seeing 2.1 over the green LED when we turn it on. So again, we're going to put the probes here, making contact. We're going to turn the circuit on and watch the meter. And sure enough, we get 2.1 volts and some change. So they sum up to 5. So we get exactly what we believe we get. Now, let's measure the other circuit. So the only difference is we have the same resistor, but it has a 5% tolerance. So it'll slightly vary what the actual value is. But this is a red LED, and the red LED is going to have a different forward voltage than this green LED. Okay. Okay. So let's see what we get here. So again, we're going to put the probe over the resistor. All right, and I'm going to press the button, and again, you know, it's really hard. You got to be very dexterous with your hands and fingers to be able to do this stuff and turn things on and all that. So I'm going to press the button. Here we go. And oh wow! So now we have 3.1 volts over the resistor. So we're going to have now we have less voltage over the LED. So over the LED, we're going to have like 1.9 volts roughly. So that tells us that the red LED, right, requires less forward voltage to turn on. And this makes sense because green, right, is a higher energy than red is, and then blue is higher than both of them. So the green requires more forward voltage and the red requires less. Okay, now let's go ahead and let's measure the voltage over the red. And sure enough, it's 1.9 and some change. All right, so everything is as it should be. All right, and again, we can compute what the current is through here. Let's go back up top here over the resistor because then we have a voltage and a resistance, so we can compute the current. So we got 3.14, right? So we got pi volts, right? So we're going to take our 3.14, divide that by 220 ohms, and we're going to get 14.272727 milliamps, right? So the first circuit has 13 milliamps going through it roughly, and the second circuit has 14 milliamps going through it, all right? Now, so let's have some fun now. So now let's go ahead and let's drop our resistors to 100 ohms each, all right? So I'm going to turn the power supply off here. All right, power supply is off. And we're going to change these to 100 ohms. So first we got to find some 100 ohms. All right, so there's a 1K and a 100K. So I'm going to go in my little bin here and look. All right, so luckily there's one right there. So there's 100 right there. So that's brown, black, brown. Take a look here in our zoomed camera. Brown, black, brown, and then gold is the last one, which is 5%. So we got one. All right, let's see if we can find another one. And, you know, again, I'm doing this all in real time because I want you to see what really goes on. I don't want to just skip and edit everything. I want you to see, you know, what has to be done to do this stuff, because this is what it really takes. It's a very slow and lengthy process. And I could have, you know, all these parts kind of set out and whatnot, but then I know exactly what I'm doing, and I'm kind of, as we're doing this, I'm kind of changing my mind what I want to do. Okay, so I'm having trouble finding one there. So in this bin, I've got all powers of 10. So let's see if we can find 100 in this one. And usually you can find everything but 100. So looking, I see 10Ks, I see 100, I see 10 ohms. And as a matter of fact, let's steal that 10 ohm because we're going to play with that in a minute. That might be fun to play with. And again, we're still having trouble finding another 100. Ah, there's one. All right. Oops. Okay, so there's another 100 right there. Okay. All right, so we've got our 100, we've got our long leads, and then we've got this other 100 with kind of shorter leads. So again, I'm going to grab some of my tools. I'm going to straighten some of this stuff out because I don't like things all bent up. And I'm going to actually cut these because I want it to be roughly the same as the other one. All right, so I'm going to cut that. Again, make sure you've got your glasses on, your protective glasses. And see these little shards, these leads? Let me put them under the other magnification. If these get on the ground, they're going to end up in your feet. I guarantee it. So if you're walking around barefoot or in your socks, they end up and they really hurt. And I've impaled myself many times. So what you do is you throw them away. Got your garbage and throw those away. Okay. So now what we're going to do is we're going to change the circuit. And let's see if we can zoom in a little bit here. A little bit. Okay. So we're going to change this circuit and we're going to remove our 220 ohm resistors. All right, which there are two 220 ohm resistors, and we're going to replace them with our 100 ohm resistors. All right, so we should get twice the amount of current roughly, and it'll be limited by the internal resistance of the LED, whatever that happens to be ultimately. All right, okay, so we got that. So I'm going to turn the power back on. So we're good to go. All right, and there's the LED. There's the other LED. So now they're not blowing up or burning out, so we're okay. So now let's go ahead and let's measure the voltage over the first resistor in the first circuit. All right, so we turn on the LED. Let's watch the meter. And this time I accidentally have the pros backwards, so it shows minus 2.67 volts, right? No problem. Just turn them around. There you go. So it did exactly what it should do. All right, 2.67 volts. All right, 2.67. And then the remainder of the 5 should be over this one, so we should be looking at 2.3-ish. All right, so what's the current in this? So let's figure out the current. We'll use the first resistor. So 2.67. All right, we're going to call that 2.68. 2.68. All right, so we're going to take 2.68 volts divided by the resistance, which is 100 ohms, and that's going to give us 26 milliamps. So 26 milliamps. All right, so we're actually putting a lot of current through there. And let's go to the second one. And if you recall, the voltage on this one was like 2.1 volts, this LED, the previous time. So let's see what we get this time. All right, so we'll put our meter over the first resistor. And we get 2.96 volts, all right, which means that over the LED, we have to have 5 minus that, which is 2.07. Notice it's almost 2.1 again. It hasn't changed, but the current, right, has went up tremendously. So if we look at the current here, right, so over our first resistor, we're dropping 2.96, almost 3 volts. So now we have 3 volts divided by 100 ohms equals, of course, 30 milliamps. So we've almost tripled our current, but yet the voltage over the diode stayed the same, and that's exactly what diodes do. Right, now they don't exactly stay the same, but it's very close. All right, and that's their property. Once they're forward biased, then that voltage stays the same, and that's one of the properties that we use. Okay, last thing. So now we've been reading the voltage and we've been computing what the currents are by using Ohm's law over these diodes, because we know what the voltage is and we know what the resistance is, so we could compute the current. But let's actually measure the current. So remember, to measure the current, we've got to go in here and break the circuit open. All right, so let's go back to the computerized blackboard here. So back on the blackboard. All right, and so what we would like to do is we've got to actually go inside and we got to break this open someplace so that we can measure the current through each one of these loops. So let's just do it in one of the loops. So what we really want to do is we want to break this open. So again, let's throw caution to the wind and get the eraser here, and hopefully it doesn't explode or blow us up. All right, there's the eraser. Good. And go back and get our drawing tool, I think our pen. All right, so then what we're going to do is from this these 2 points right here, we're going to run these out to our ammeter, right? And there's my little ammeter. That'll be plus, that'll be minus, amp meter. All right, and we can measure the current. So the current will flow out of the source, the battery, through the switch, through the amp meter, and then back through the circuit. So you have to put them in the middle of the circuit. Remember that amp meters need to go inside of the circuit. So we're going to try and confirm one of our currents by doing this configuration right here. Okay, so let's go do that. All right, so let's go ahead and let's zoom in a little bit here so you can see what I'm going to do. All right, so let's mess with the first circuit here, and let's make sure our power is off. All right, power is off. All right, so anywhere inside of, so the current is coming from here, going to the switch, going through here, going here, anywhere inside here, if we put the amp meter, we will be able to read the current. So what I'm going to do is this. I'm just going to move this LED over like this, and I'm going to give it like 3 spaces. So there's 1, 2, 3 spaces. So now I can take the amp meter and hook it here, and then hook it here, and then measure it. But one thing you're going to do a lot of when you do electronics is fabricate things. So what I've fabricated here, let me show you this. This is we're going to have to, let me see if we can get this to focus. Of course not. Let me back out a little bit for you. All right. So if you recognize this, this is a power cable from a computer. And what's nice about these is they have really thick wires and they have these holes in them. And these holes just happen to be the perfect size to fit the average probe tips. So see, that goes in there, that goes in there real nice. So now I've got the probe tips, and I've got on this other end here, I took a little header and connected some posts, and now I can plug this into the circuit. So I'm just going to plug this right into the circuit right here. So we're going to go right here, and we're going to plug it right in here. Okay, so now, and again, this is messy business. It's messy business doing electronics, right? So the current's going to flow through the positive rail, through the switch, through the resistor, into this red lead, which is connected here. And again, if we want to do our colors properly here, go like this, go like this, all right? And it's going to go into our meter. All right, so now we're going to back this out so you can kind of see what's going on. So let's zoom back out. All righty. Okay, and we have to do one thing. We have to make sure and be very careful this, you'll blow something up. We have to make sure that our meter is in current mode. So first we have to move the probe because it's in the wrong place. So we're going to put it in milliamperes here. Then we're going to switch the dial to milliamperes. Okay, so now we're good. We've got our meter. We got everything we need. All right, so now when we turn the circuit on, we should see the current. All right, and it should be what we calculated. All right, and let's see what happens. So I'm going to turn the power on, the power supply. Power's on. And when I press this button, this should all work. So here we go. And there we go. There's 26 milliamps. All right, and what did we compute the current should be in the other circuit? It was about 30 milliamps. All right, so let's go ahead and do that. So we'll take this out, and we're just going to leave the power supply on. We're going to just get bold here. All right, I'm going to put this over 3 notches because I know that I made this little connector to be 0.3 inches, and I know that each one of these little holes is 0.1 inches, so 0.3, so that way it'll fit. I'm going to plug it in there. Okay, so we're good to go. And again, let's press this one. And there we go, 30 milliamps, 29 and some change, so 30 milliamps. So we just had 26 and 30 roughly, 26 and 30 roughly, so that should be 56. So if we were to measure the current coming out of the circuit, right, from the red lead here, right from the power supply, we should get about 56 milliamps. So let's go in line in that part of it. So we're going to take this out, we're going to put this back, all right, and now this will be a little bit more difficult. So what we're going to do is we are going to move this around a little bit. We are going to take a wire, and we're going to go over 3, and then we're going to take this wire here, and we're going to plug this into the positive rail, like so. All right, now we're going to take this, and we're going to connect it here. All right, so now here comes our positive rail. There's a gap here of 3 of these little holes. Then we're taking that and going into the positive rail. So if we put our amp meter up here, we'll be able to complete the circuit. Okay. There we go. All right, so now let's see what happens. So the power's on, and I'm going to turn the first switch. Watch the current. And we get 26. Now let's do the second switch. We get 30. Now let's do them at the same time. Ready? There's 26. And there's our other 30, right? And now, so now look at this. So we've got 26, and then we push this one, and we've got 29, right? And some change. So if you look at this, you've got 26 plus 29, all right, is 55. Then when we do them both, we're getting 53.954. So it's a little bit off, and there's a couple reasons why this can be happening. First, we're just kind of subtracting away some of the decimal positions, points there, and we're losing a little bit of accuracy. The other thing is the meter itself affects the circuit. And so the more current you put through it, you can affect it. So the meter actually, it's not perfect. So the meter is shunting this current through it and measuring it. So the meter itself affects the circuit. So you have to take that in consideration. All right. So it can actually affect your reading. So depending on the quality of the meter. All right. So anyway, so that's that. So we measured everything. We built our circuits, and we analyzed it. So, and let's do one final thing here. I think we have a little bit more time, so let's do one final fun thing here. So let's keep the circuit being powered by the system over here, so we can measure the current. All right. Let me move this over here. And again, like I said, this is messy business. You know, you need a lot of space. But let's play with something else here. So these two LEDs, right? These two LEDs are a discrete, a green one and a red one there, right? But this LED is like a bicolor three-way LED, all right? Now, if we look at it under the magnification here, it's got this center rail, center pole, and then it's got these two outsides. So the center one should be ground, and then the outsides should be the two anodes. And if we power either up, we should be able to get this thing to turn on. So let's give it a try. And I could be wrong, could be backwards, but we're going to see what happens. All right, so what we need here is, and there's lots of ways to do this, but let's just do it like this, do it kind of clean. All right, so we're going to put our LED in there. Let's zoom in so you can see what we're doing. So we're going to put our LED in there. All right, now I'm going to run one wire to this side, and then I'm going to run another wire to this side, and then I'm going to run the ground down to ground. So then we'll have two complete circuits, okay? So let's go ahead and do that. Let's get our wires. Let's see what we got here. All right. Okay, so for example, let's do this. So see this wire right here? This is kind of a, you know, good wire. So I'm going to take some wire cutters here and strippers. All right. And then I'm just going to put it in like the second hole here, and then just clamp down on that and slide it off. And then we got that. And then again here, and then slide it off. Okay. And so now we've got that. All right. Okay, so we're going to use this, and we're going to hook this side up here, and then let's find another one. Again, here we go. Got to take your time. You got to have your wires out, and you could be using your other ones too. I'm just using this one instead of the pre-made hookup wires. I like using these sometimes because I can make things cleaner if I want. Now this circuit is not very clean. All right, we would flatten these all out if we wanted to like use this for something and put it in something for kind of a prototype, we'd make this very flat and clean. All right, and we need our ground. Now I've just been using a yellow wire. A lot of times what people will do is they'll color code everything. So here's black wire. So I might use this for grounds, right? So I'm just going to get out a black wire here. And same token, we might use red for positive and power. All right. So we got our black wire here, straighten our leads out, okay, and that's going to go from that center down to ground. Okay, so now we've got our circuit here. Let's zoom back in. Get it to focus on us. All right, there we go. And let's get our meter here. Actually, let's back out so we can see the meter. I want to keep seeing the meter. Let's keep that in the mix here. Okay. And let's see, can we put this like this, maybe? Maybe that's a better way to do it. Okay, so we're ready to go. Let's turn the power on. Okay, the power is on, and let's press the first momentary switch and see what the LED does. All right, and that is a really nice red, and you may not be able to see it with the camera, but that's a red. And look at our current, about 30 milliamps. Now I'll press the other one, and there's a really nice green. All right, and when we do them together, we should be getting about 56-ish, because they'll add up. And what do we get? 55, 56. There you go. And notice what the color is. It's orange. So see, I can get 3 different colors out of this by mixing them together. And that's really cool. So you can do a lot with that kind of LED. Very cool. And we're probably driving this too hot. We probably only want to put 10, 15 milliamps through each leg. All right. Okay, so that's it. Okay, so anyway, we analyzed the circuit. We built some cool stuff with this, and that's that. So what we're going to do is we're going to continue on with the material, and we're going to start talking about discrete components, more of them in the next lecture. So why don't you finish up, and I'll meet you back in the next lecture, and we're going to just keep going through this. I'll see you then. Bye. All right, welcome back. And we're on the next lecture. We're continuing on with the material here. We're getting through it slowly but surely. There's a lot, just a lot of it, so bear with me. But we're learning a lot of cool stuff. We're going to do some more hands-on in this lecture and mess around with some capacitors and maybe a transformer if we can get to it. We'll see how the time goes. All right, so up here on the screen, introduction to discrete components. So now we've talked about a lot of these things already, all right? So resistors, capacitors, inductors, transformers, diodes, and transistors. So we've actually seen these things. We've talked about them. We've kind of used them a little bit. And so you know, you're already a little bit familiar with it, all right? So this is going to be kind of review and some more information. All right, so resistors, we already talked about this. Resistors resist current flow and voltages drop over resistors. We use these things to control currents, voltages, and inside of circuits. There's different kinds of resistors. All right, they're measured in ohms. All right, and one of the important things is how to read a resistor. And we've kind of avoided this for a little bit, but we're going to get to it right now. Some of the symbols you might see, the top one here is kind of just like a heartbeat almost. You'll see that commonly. Then many of them, and then sometimes you'll just see a resistor kind of drawn with you know, lines representing the actual bands or a representation of it. All right. And down here, just a little circuit. We've got a current flowing in and out, and then over a resistor we'll have a voltage drop plus to minus V, and that V will equal I times R, which is just Ohm's law. All right, now reading the resistor color code. So some people have trouble with this, some people don't. If you just kind of do the math and follow the rules, you'll kind of get the hang of it. So resistors can have more, they can have different numbers of bands, all right? So they might have 4 bands, they might have 5 bands if they're precision resistors. So you have to kind of figure out what kind of resistor you have and how to read it, all right? However, with the resistors that we're going to be talking about, which are non-precision resistors, just for now, it's not like we can't use precision resistors. But we're going to have 4 bands on them. And the first 3 bands are going to indicate the value, and the last band is the tolerance, all right? So let's take a quick look on our zoomed in screen. Okay, so if you take a look at the zoomed in screen, so this particular resistor is brown, black, orange. I believe that's orange. So let's make sure it's orange. Let me look at this carefully. Definitely orange. So it's brown, black, orange, and then the last band is gold. All right, so we've got brown, black, orange, and gold. All right, so let's remember that, brown, black, orange, and gold. Okay. All right, so this this paragraph right here, so the 4 places are the B1's place, which is the tens place, B2 is the ones place, and B3 is the multiplier, and B4 is the tolerance, and that stands for band 1, band 2, band 3, band 4. All right. Now, This is not in color here, and I'm going to show you a color one in a moment. All right, and the different bands, so black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver. And these are the numeric values assigned to each one of these colors. And many people make songs up to remind themselves the color code. So you can do that if you like. All right. And here's kind of how you do the computation. So it's 10 times the value of B1 plus B2 times 10 to the B third power plus or minus B4. And that's the tolerance here. All right. So we had a brown, black, orange with gold. So we'll come back to that in 1 second. So now if we go over here, and just to let you know, if you type in resistor color code, there is no lack of really nice charts to kind of help you figure this out. So I picked one out right here, and this figure is a really good one because it shows both versions of the color code, the 4-band and the 5-band resistor. So that the 4-band 1, 2, 3 and tolerance, and the 5-band 1, 2, 3, 4 and tolerance. So the 5-band version is for precision, which will be down to these 1% values, or 0.1, 0.25, 0.5, and then the 4-band is 5 or 10%. So we'll be dealing primarily with this one. But if you go into your parts and you find something with 5 bands, chances are it's a precision resistor, so you can read it like this. In any event, how it's read, just like the math just showed, we have the first band, all right, and then we have the second band, and then we have the third band, which, if you follow this down, is the multiplier. And then you can kind of compute what these values are. All right, so we had brown, black, orange. So we had brown, so the first band is brown, so that's 1, all right. Then we had black for the second band, all right, so that's the second number, which is 0. So now we have 1 and 0. And then the third band, we had orange, which is here, so this is times 1K. So we have 1, 0, that would be 10, and then times 1K, or 10K. So we would have 10K ohm, and that would be our value. And then we had gold as the final band, so here would be the final band, and gold is 5%, so it would be 10K plus or minus 5%. So 10K plus 5%, it would be 500 ohms, right? And minus 5% would be minus 500 ohms. So it's going to vary from 9,500 to 10.5K, all right? Okay, so that's how you read resistors. If you don't want to memorize this or learn it, just use a multimeter, and you can do it with a multimeter and get the value. So let's go take a look and do it with the multimeter and just verify that our 10K resistor is 10K. And let's go back to our math. And if we do our math, so it was 10 times 1, that would be the brown. So we have 10 times 1, which is 10. And then we have plus B2, which was black, so that would be plus 0, so we would just have 10. Then we would have times 10 to the B3, all right, and that was orange. And then if we look back at what the value of orange is 3, so it'd be 10 to the 3, so 10 to the 3 is 1,000. So again, we'd have 10 times 1,000, or 10,000, or 10K ohms. So no matter how you slice this, this is how you do it, all right? So let's go take a look and let's measure it and just make sure. All right, so we're going to put our resistor down here. Let's zoom in just a little bit. Okay, we've got our resistor. And let's get our multimeter. So we got our multimeter here. Okay, and let's put this on ohms. And it's on auto range right now. So we'll just let it automatically range. Let's take our resistor, which is brown, black, orange. You can see it right there. All right, and let's go ahead, and I'm putting it on here. And there we go. And 9.7K. And that's exactly what we expect out of it. And I'm holding it on here right now. Just hard to focus on it. 9.7K. So it's within the tolerance, and that's exactly what we would expect. All right. Okay, so that's the whole idea of resistors, and then there's some examples in the text which you can look at yourself. All right. And resistive power rating, we've talked about this. Typical values are a tenth of a watt, an eighth of a watt, fourth of a watt, half watt, 1 watt, 5 watts, and so on. And as the wattage goes up, these resistors will get larger and larger and larger. And like those, the big rectangular white one that we looked at, I believe was 5 watts, or maybe it was 2 watts, was its power rating. So again, and then power, what's power? Voltage times current, V times R, right? And if you're going to put some resistors in a circuit, you want to compute what the currents through these resistors are, and the voltage is dropping over them, compute what the power is, and then the rule of thumb is set your resistors so that they can handle twice the amount of power. So if you're going to be putting, say, 0.5 watts through a resistor, or it's going to dissipate 0.5 watts, make sure it can handle a watt. And that's a really good design tactic. It'll cost a little bit more, but the circuit will be much more robust. And if something gets overpowered or overvoltaged over time, it's not going to damage it. A lot of engineers, they design things right at the edge of tolerance, and things overheat, burn up, and so forth. If you're a gamer, I'm sure you're familiar with game consoles overheating. The Xbox famously has always overheated. The big bricks overheat, and this is because of poor power supply design, poor power dissipation, and making assumptions about how much heat and so forth can be dissipated. So always over-design your circuits when it comes to power, at least by a factor of 2. All right, and you'll always be safe, and nothing will burn out. All right. Let's go ahead and let's talk about capacitors again. So we've seen capacitors before, and nothing new here. Some symbols. So this is a non-polarized, might be a monolithic or ceramic capacitor. Just 2 parallel plates is usually the symbol for it. Then a polarized capacitor will have a line and then a curved line, and that'll be plus and minus in that orientation. And then you might also see this kind of a fat line also polarized, representing the ground or the negative side. So polarized capacitors, they must have the voltage plus to minus, or they will be damaged, or they could explode. So watch out for that. And again, capacitors store charge. We measure the capacitance in farads, named after Michael Faraday. All right. And again, all a capacitor is 2 metal plates separated by some distance. And then there's what's called a dielectric inside of it. This could be air, paper, and many other materials. A dielectric is, you can Google it, but a dielectric is an insulator that when you apply an electric field, it becomes locally polarized. So what happens is the orientation of the atoms, dipoles, or their magnetic domains can switch. So locally they become oriented in such a way that the electric field pushes plus to one side and minus to another side. There's no current flow, but it just becomes momentarily polarized, and that's why it's called a dielectric. All right, again, we measure capacitance in farads. All right, types of capacitors. There are countless types of capacitors, actually. More capacitors than you can possibly imagine. So as a matter of fact, what I want to do, let me show you this figure, and then we'll look at some types of capacitors. So again, here's another figure showing kind of the charging of a capacitor. So we've got a voltage source. We apply it to the 2 metal plates. The charge will accumulate plus and minus. We'll have an electric field. There's a distance d, and then the plates themselves would have a surface area. We're not going to go into the exact physics of a capacitor, but you can look it up, how to compute capacitance based on the distance, the material, the dielectric. There's formulas for it. You'll have a plus charge on the positive plate and a minus charge on the negative plate. And then now the interesting thing is this: when you take this voltage source off, the capacitor stays charged. And so that's really interesting. The charge stays there. It's not gone anywhere. This is an insulator in here, this dielectric, so it can't flow through it. So that's the whole point. A capacitor will stay charged. All right. So, all right. And then we've got some pictures here of types of capacitors. These are kind of hard to see. So let me tell you, I created 2 versions of the book that we're using for notes, Design Your Own Game Console and the Black Art of Video Game Console Design. And we're using the books, of course, for the basic electrical engineering and circuit analysis sections for our notes, so that we have something to kind of talk about. However, the the Design Your Game Console version of it, which is kind of the online version, and the Black Art version is kind of the printed version. The Design Your Game Console version is in color because it's online. So let's go look at that. So I just switched over to that. And so here are these capacitors. You can see them a little bit better. There's the electrolytic capacitors, which you've seen before. And these guys right here are ceramic, and there's many, many ceramics. Here's mica capacitors, for example, and there's the tantalum capacitor, which you've seen. And like I said, there are many, many, many different kinds of capacitors. And the electrolytics can be, very, very huge capacitance, and usually, 0.001 microfarad all the way up to a farad. And a farad capacitor will be, like that big. It'll be huge. Ceramic, 1 picofarad to a microfarad. Actually, and again, these are just rough ranges. 1 picofarad, and they might go up to, 10, 20, 50, even 100 microfarads. You can get in a ceramic capacitor if you really want to be very expensive. All right, good for bypass circuits, and there's these descriptions here kind of tell you what you would use these things for. Mica capacitors, 1 picofarad to 20,000 picofarads, very high performance and for very high frequency applications, high voltage, high stability. So when you're building circuits with the capacitors, one thing is if the capacitor is being used for like bulk storage, for charge storage, or as what's called a bypass capacitor for noise, the value, if the value changes much because of temperature or frequency, you don't care that much. But if the capacitor is in a part of a circuit that has something to do with timing or something that's critical, you want it to stay exactly the same, right? You don't want it to vary over temperature or frequency. And so that's why there's so many different kinds of capacitors, and that's why their cost varies. All right. So, and then tantalum, these are pretty big capacitors, and they'll go down very small, like 0.1 microfarad, 0.01, even smaller, a little bit smaller, and up to 1,000 microfarad. Be a very expensive tantalum capacitor, actually. And tantalum is a material, very expensive. All right, these are low inductance, and they have low ESR, which is equivalent series resistance. And so that's why these are used, that they have very low ESR but very high capacitance. So typically you would replace your canister electrolytic capacitors with tantalums if you could afford it. All right, they would just be better. All right, and okay, so now this is going to kind of move into the inductor, and let's go back here. And again, see, these have been redrawn in black and white, so they're a little clearer, but the other ones are a little bit more colorful. So if we have figures, then we can see them better. All right, so now what I'd like to do is let's go over to the bench, and let's start playing with some capacitors and have a little fun there, and then we'll come back and we'll talk about inductors and transformers. So let's go talk about, let's go play with some capacitors and have some fun and check some stuff out. Okay, we're back here on the bench area, and so let's play with some capacitors, and let's not try to blow anything up. Well, maybe. So what we're going to do is we're going to take a look at some large capacitors. And for example here, I've got this 4700 microfarad, 25 volt. And I've got this 330 microfarad, 50 volt. And I've got this 47 microfarad, 250 volt. All right, so again, those are three examples of electrolytic capacitors. And let's go ahead and first, let's just measure these. So to measure a capacitor, we could build a circuit that can measure it. That's one way to do it, right? We don't know the exact laws. There are modeling equations for capacitors that we're going to learn about for their charging and discharging with resistor circuits, right? And they're called RC, resistor capacitor circuits. And there's also RL, resistor inductor circuits. And we're going to learn a bit about that a little bit later. But just for now, we're just going to kind of play with this and just have some fun. All right, so the first thing that I want to do is I want to show you how you measure these. All right, and we're going to do this in real time, so bear with me. I don't like staging things and faking them. All right, so the first thing that we've got here is a meter. And this particular meter is fairly expensive, couple $100. I don't know, maybe it was $300, not compared to a fluke meter, which are very expensive. But this meter has capacitance, and it can measure capacitance. So we'll put it on capacitance, and we got to look around here and see where that is. There's inductor, there's frequency, There's current, amperage. There's capacitor right there. Okay, so capacitor and inductor. We've got our leads in here. So there's our leads. All right, and then now what I want to do is I want to measure and see if we can measure these capacitors. All right, so let's go ahead and give this a try. So here's this first one. And this one is a 47 microfarad at 250 volt. All right, so I'm gonna make sure I use the probes with the proper polarity actually. So it's got the same polarity as the capacitor requires. So there's the negative side. So I'm gonna use the negative probe on that. So I'm just gonna hold this on here, and I'm gonna try not to touch both leads with my fingers, just one of them, so that I'm not the inductance and capacitance of my fingers is not getting involved. All right, so we put it on there. All right, and the meter is doing its thing. It's auto scanning, and there we go, 46 microfarads. That's actually pretty accurate. I'm surprised. So this is 47 microfarads, so that was pretty accurate, so that's impressive. So we got that. All right, now we've got this other capacitor here, and this one's 330 microfarads, 330 microfarads. Again, this one, the plus side is marked. Instead of having the minus side, the plus side is marked. So we're going to take care of that. So we're looking for 330 microfarads here. So let's go ahead and put this on here. All right, and try not to touch the other lead. So we're not part of the circuit. And there it goes. And it's saying 31 microfarad. All right, so so something's going on here. This is supposed to be 330 microfarads. So now sometimes when this happens, turn the meter off, turn the meter back on, and we can change the range of the meter. All right, and let's see if this kind of helps here. All right, and now let's see what we got here. And you know, sometimes things are beyond the range of the meter, or it's between ranges, and it makes it difficult for the meter to read. And this is saying it's out of the range here. Okay, so let's go ahead and let's put it up one more. All right, and this is millifarads, so let's try that. Okay, so that's better. So see, it's 0.3 millifarads, which would be, you know, 300 microfarads. All right, and we're missing that other decimal place right there. So again, the reason why I showed you this is this capacitor is between the ranges, so it makes it hard to read, right? It's the meter's having trouble reading it. And if we go back to the previous scale, and so you're not crazy, and we go back to the scale of microfarads, all right, and then we do it again. And if you looked at the manual for this, it would say what the ranges are. So sometimes it's hard to get a read of what you want. And again, see, that's off scale, that OFL off scale. All right. All right, so then we have to put it back to the bigger range, which is millifarads. All right, and we'll put it on millifarads, and there we go, 0.3. So this is this capacitor is a little bit hard to read. We can't read it with this particular meter, and I've got more than one meter. All right. Okay. So now there's other kinds of meters to measure capacitance and inductance, which are specifically designed to do that. And here's one here. This is an LC meter, and you can see it's only got capacitance here and inductance here, and that's the only scale it's got. It's got a couple leads so you can connect your device. It's got plus and minus here, so you can plug devices into here also. And these leads, you want to keep them short because the leads have capacitance and inductance, and that's why they're very short leads as compared to the very long leads of our other meter, which is not specifically designed for measuring capacitance. In any event, let's see if this meter can read this 330 microfarad more accurately. So the first thing that we do is we just power this thing on. All right. And it's in 1000 microfarad range right now, so it should be able to measure something up to that. We'll hook up the positive lead to the positive side, like so, and the negative lead to the negative side, like so. All right, making sure those don't touch. We'll just set that down there gently. And then we press the test button. All right, so let's press it. And very cool. So it's measuring 300, 310, 300-ish, and that's what we expected. So both meters are kind of giving us the same value. We got 0.3 millifarads, which would be 300 microfarads, but we didn't have those decimal places of accuracy. So here are those decimal places of accuracy. Now the capacitor itself is probably, this capacitor, if we're lucky, is a 20% or 10% capacitor. So it doesn't really matter what this says, because it's probably going to be off plus or minus 10%, 20%. So that would be plus or minus 30 to 60 in this case, right? Okay, so now let's take a look at this big one. All right, so this big one here is 4,700 microfarad. Let's see if we can read this. So what do you think? So where's the plus side? So here's the negative side. That means this is a plus side. So what is this other post? Well, this capacitor is so big, when this goes in a circuit board, it would bend all over the place. So there's extra posts for stabilization. And sometimes up to 4 or 5 posts, and only 2 of them are the capacitor, but the other posts are just mechanical stabilization. All right, so here's plus. So it's going to go right there. And then minus right here. Okay, let's put our capacitor over here and let's press the test button so you can see it. And it's going up, going up, going up, going up, and it's 4,700 microfarad. So this meter is thinking that it's 500 microfarad, but it's incorrect, right? So these things are, all these things are fallible. It's not going out of range. It's just saying, hey, I think it's this. So this is wrong. All right, so we know it's wrong because this is a maximum of 1,000 microfarads. So let's put that away. So let's turn that off, put that away, and let's go get this guy again. All right, let's see what happens here. So we're going to put this in millifarad range here, and it's got 2 decimal places of millifarad, so that's very large. All right, and let's see what this guy gives us. So go on here and put it over here this time. All right, there's our negative lead and our positive. All right, and we're looking for 4,700 microfarads. All right, and give it a chance. All right, so 4,700 microfarads. And so far, we're looking pretty good. That's 5,500 microfarads right there. And that would be within our tolerance of 5 or 10%. So this meter's saying it's hanging around 5.4, so it's 5,400 microfarads, all right? Okay, so we've got this big capacitor. Let's have some fun with it. All right, so we're going to learn the modeling equations for capacitors and how to charge them and discharge them, and we'll be using them in our digital circuits. We're learning all this analog stuff right now just so that we have some understanding of what's going on. But later, we're going to not worry about this so much. We're going to just kind of do digital, and then as we start doing circuits with Circuit Maker, it won't matter so much. But let's go ahead and let's do a circuit right now. So I want you to take a look at this right here. And what I have done is I've taken one of our LEDs, a piece of wire, and a resistor. This is a 1K ohm resistor. And then we've got our 2 posts. So if we were to hook power up here, we would create a circuit and the LED would turn on. But we've got a really big resistor, so we kind of need a big voltage here to get this to turn on. All right, so let's go ahead and let's take our voltage source, our power supply. So I'm going to hook our power supply up here. And now I'm going to go turn our power supply on. And let's go take a look at the power supply. All right, so here's our power supply, and we're going to use the course adjustment, and I'm actually going to put this up and just kind of show you. I'm going to put it at 5 volts first. All right, and we'll kind of use the fine adjustment. We'll put it at 5 volts. All right, 5 volts, 5 volts, there it is. And then we'll turn it on, so we'll press on. All right, now as we did that, you see on this other monitor here, the LED turned on, but it's not too bright. There's not a whole lot of current going through here. All right, so let's turn up the voltage. So I'm going to turn it up and just stay on this screen right here. So I'm going to turn it up and tell you what I'm doing. So we're going up 6 volts, 7 volts, 8 volts, 9 volts, and hopefully you can kind of see it changing. 10 volts, 11 volts, 12 volts, and I'm going to adjust it back down to 12 volts exactly. All right. So 12 volts, that LED is on pretty bright right now. All right, so that's all fine and dandy. So 12 volts will light this LED with this 1K resistor, right? And we could actually compute, if we wanted to, what's going on here. And so real quick, we've got the 1K resistor, right? Let's get our meter out, all right? And, let's get our meter out and let's kind of measure what's going on here. So I'm going to zoom back so you can kind of see this. And this is when it starts getting fun. We're starting to know enough information where we can start to be dangerous here. All right, so let's measure the voltage across the resistor. Let's do that. Measure the voltage across the resistor. And I've got the probes backwards, but it didn't hurt anything, right? We just like positive numbers. And what do we got? We got 9.8, call it 9.9. We got 9.9 volts. All right, so 9.9. And we've got a total of 12 volts, so 12 minus 9.9 equals 2.1. And remember, our green LEDs, they drop about 2.1 no matter what. So we go over here and we look, and sure enough, 2.09 or 2.1. All right, and if we go back and look at this resistor here, this is 9.9 volts. So what's the current going through here? So the current, V equals I times R. I equals V divided by R. So 9.9 volts divided by 1 kilo ohm equals 9.9 milliamps. So call it 10 milliamps. So 10 milliamps, so that's a a good amount of current, but it's not the 20 or 30 we had with the really bright version. So about 10 milliamps, nothing's burning out. That looks good. Okay, so now let's see if we can do something with this capacitor. All right, so capacitors can charge, and they will charge up to whatever the applied voltage is. So if you put an applied voltage, they'll charge up. Now their capacitance is the how much charge they can hold, but the voltage is independent of that. Okay, so now let's see if we can do something with this capacitor. All right, so we've got the capacitor, and this particular capacitor can charge up to 25 volts, but it's 4,700 microfarads. So that is how much charge. So the microfarads, that has to do with the amount of charge. What's its capacitance? The voltage is just the maximum voltage that it can charge to. So what we're going to do, and we're going to learn the modeling equations for this much more a little bit later, but we're going to charge this capacitor up, and we're going to hook it up to the power supply, and we're going to charge it up to 12 volts. Then we're going to use it as a battery, and we're going to power this circuit without the power supply. Now, the capacitor will slowly discharge, and as it does, we'll lose power, right? But it momentarily will power the system. Okay, so first thing, let's undo this. We're going to turn the meter completely off, or the power supply completely off. And now we're going to go to the positive lead here. And we're going to hook this to the positive lead, and we're going to hook this to the negative lead. All right, now some words of caution. So what we're doing right now is we're going to directly charge this capacitor. Now, typically when you charge a capacitor, you want to have some resistance so that you can model the charge rate of it. All right, and the resistance has to do with the charge rate has to do with the resistance and the capacitance. If there's no resistance, this theoretically would have instantaneous infinite current, all right, and it would explode. But the capacitor itself has some resistance, so it's going to limit the charge itself. So we're not just going to dump 12 volts into here because there would be a huge current spike immediately. We're going to put 1 volt, 2 volt. We're going to just slowly ease up the power until it's charged to 12 volts, all right? So this is here, so that's going to be there. Now let's go over to the power supply. All right, so we got the power supply. So the first thing that I'm going to do is I'm going to turn this thing on. All right, and now watch the current. Every now and then you'll see it flicker and because it's charging the capacitor. Okay, so we're going to slowly turn this up, real slow. We don't want to freak out the capacitor. And keep your eye on that current. There, oh, see, a little bit, right? And we don't want to go over 12 volts because we can't undo it unless we discharge it. All right, so now I'm going to do the fine adjustment. And this is why I say you can't drink coffee and do electronics. You've got to have really stable hands. Okay, so we got it at 12 volts. All right, good. All right, so now our capacitor is charged to 12 volts. Okay, so if this was, say, the 250 volt capacitor and I charged that to 250 volts and I were to touch my finger, that would hurt a lot. But we're not doing that, at least right now. Okay, so now I'm going to undo this gently and undo this. All right, I'm going to turn off the power supply so these, if I short them together, nothing happens. Okay, so now let's go ahead and let's measure the voltage across this capacitor. But we want to be very careful that we don't short the leads out, because then we'll lose our charge. All right, very careful. All right, so again, I'm going to kind of suspend my fingers here and very gently touch these. And look at that, 11.9 volts. But see how it's slowly decreasing? Because the meter itself, right, is a load and we're losing charge. So let's not do that. Let's undo that. Okay. Now, so now we've got our power supply. So this is charged. Now we've got our circuit, and now we want to connect this to this. All right, so there's a number of ways we can do this. All right, the first thing is you should have, as part of the things that you bought all kinds of little hookup wires and things of that nature. So there's lots of things right here that we could hook things up with. But what I want to do is I want to show you, again, everything we do I want to show you is an opportunity to show you something else. All right, so one thing we could do is we could take one of these wires, and you see these are female. All right, and let's zoom in here. As a matter of fact, let's go to our zoom screen. So these are female, and these are male. So what we could do is we could plug a couple of these in here and peel these off. Then we could plug the other end into our circuit. The only problem is the diameter, the inner diameter of these holes, these females, is too small for these big guys. So these are just a little bit too big, and we could probably stuff it in there, but we would damage it. But nonetheless, it's a good idea. That would work really good with, say, this one. So this one, if I were to come here and do this, that's real good. Now, of course, this is just a temporary connection. We wouldn't want to do this for a real circuit, but if we just wanted to play with something, there we go. All right, so that's not going to work. So what else do we have over here? So another thing that we have are these, what are called, these are like little probes, little alligator clips, little probes, and they have very, very fine little grippers on the end there. And let's look at that zoomed. So you look at this right here and you see, so this is what this looks like. And when you push this, see that little thing comes out there and it can grab onto things. So let's not mess with our charged capacitor, but we can put it on here, for example. See that? So that would work, but this is kind of little. And then how do you connect these? Well, in the bottom usually, so there's a little metal connector right there, a little metal post. And then we could use one of our wires again, our hookup wires. You just kind of put that in there and just gently, gently push it in. So there, and then on the other end, this could go into the circuit, or we could put another one of these on it, right? So this is kind of what we're going to use. But what we want to do is use a bigger one. So I've got some here. So here's some other ones that are already set up. And I got a couple of them here. All right, 2 of them. And what we're going to do is we are going to connect these to our big capacitor, and then we're going to connect them to this these posts here. But we are going to do this considering discharge time. So I want to measure the voltage. The second we connect this circuit up, I want to take our meter, all right, and I want to start measuring the voltage here, all right, and just kind of watch what's going on. So we're going to measure the voltage over, say, the resistor, all right. Okay, so first let's hook our circuit up. So we've got our capacitor, which is still charged. Now we're going to hook this thing up. So here we go. So here's the negative one, negative lead. All right, and then I'm going to hook this up to this negative lead here. All right, now I'm going to hook up the positive rail. But before I hook this up, why not make our measurement a little bit easier so we don't have to kind of do this with a probe and rush? Why don't we do this? We have this little device here. Why don't we grab the voltage off the resistor and then connect our meter so we don't have to go in there in real time? And again, these are just things you learn so you can do things better. All right, so the voltage we want is right at that node there, right in the middle node, right in the middle. So we're going to tap off that. All right, and then we're going to have to ground the other side. So let's get a piece of wire, and we need to run that to ground, the other side to ground. So let's actually get a black wire for once. Okay. And, well, actually, let's do this. Let's measure the voltage drop. We'll just measure the voltage drop just over the resistor. So, in fact, we won't use a black wire. We will just run this other side up to the top rail. All right. We're just looking for the differential voltage here. We just care about what the voltage is, not relative to ground. We just want the voltage across the resistor. And again, this stuff is tough. Things don't fit. Got to take your time, be gentle. All right. All right, so we got that hooked up. Good. We got our capacitor over here. We're ready to hook that up in a second. We got our meter over here. Now what I'm going to do is I'm going to hook these things up. All right, and I think I have the polarity right. Doesn't really matter. We're just looking for the differential voltage over that resistor as this thing starts to discharge. All right, so the second I turn this thing on, this LED should turn green, and we should see a voltage, and that voltage should slowly drop as the system discharges. Okay, ready? Here we go. And of course my hand's on that. Can I do this way so you guys can see better a little bit? Nothing's easy. Everything's got to be difficult. All right, here we go. All right, 1, 2, 3. All right, there we go. And we did have this flipped around the wrong way. That's okay though. So 3 volts, 2 volts, 2.2 volts. The LED is still on. You can see it. Still on. 1 volt, 0.6. Still on. Still on, still on, still on. So even though the resistor has almost no voltage drop, we still have enough to keep that LED forward biased and on. And that's it. It's dead. It's done. All right. So that's that experiment. So anyway, let's stop here, and we're going to continue on with the next section. We're going to start talking about inductors and transformers, and we'll do some experiments with those as well. All right. Okay, so I will see you in the next lecture. Bye. All right, welcome to the next lecture, and we're just moving right along here. So we're going to talk about inductors and transformers, and we're going to do some experiments. So this will be kind of a cool lecture. So on the screen right now, you see kind of a representation of an inductor here, and let's go back here. So typically they're just a coil of wire, that's the representation or the symbol, or if you want to show that it has a solid core, a couple bars next to it. So we've seen inductors before, but again, how an inductor works is whenever we have a current, so in this case right here we have a voltage, and when we apply a voltage to this inductor, this is going to, a current is going to flow, and the current's going to flow positive to negative like this through here and through these coils of wire. And whenever we have a current or charge moving through a wire, a magnetic field will be generated. And then when we have these coils of wire, what happens is these field lines or these flux lines kind of link together, and it makes a larger field. So you get kind of a magnetic field that billows out in all directions, kind of looks like an apple core. And a couple things. As you do this field generates, and it just stays static. So if the current isn't changing, so once we establish a constant current in here, this magnetic field will just sit there in space. All right. Now, if we were to move a piece of metal through it, we've talked about this before. If we were to move another conductor through that, we'd actually generate a current. So we can use that electromagnetic induction to generate currents, and then also we can generate magnetic fields with currents. All right, so that's all an inductor does. We've seen them before. We've looked at them before. And again, we measure inductance in henries after Joseph Henry. And inductors are typically in the microhenry range. All right, if you had a henry, that would just be massive. So microhenry, and they're very, very small. And inductors are used in filters. They're used in power supply circuits. Typically, when you're doing analog design, a lot of engineers, well, if they're analog engineers, they won't avoid them, but a lot of times engineers that are more digital engineers will avoid inductors altogether and try and do everything with capacitors. In many cases, wherever you can use an inductor, you can use a capacitor and vice versa, but in some cases you can't. You have to use an inductor because of its properties. All right, so inductor operation. So we see a figure right here, and we've got an inductor in the circuit. And we're going to show two examples of what goes on here. So first, we have the switch in position 1. And so now this voltage source is applied to this inductor, which has some finite resistance actually. So infinite current is not going to flow. So this thing might have milliohms or even ohms sometimes, but usually milliohms. So current will flow, and as that current flows, this magnetic field will billow out, and it will then stabilize. And this transient event, the moment that we flip the switch to position 1, and this inductor is charged or current flows through it, that transient event, there are modeling equations, differential equations that describe exactly what goes on. And we're going to actually look at those a little later on. But for now, let's just assume we're in what's called a steady state. It's been on, the switch has been on for long enough where we just have a constant current flowing, and then there's a magnetic field there. Now, the energy is actually stored not in the charge, but in the magnetic field itself. That magnetic field now has potential energy. And if we were to switch the switch from position 1, where we're sourcing the energy from this battery or voltage source, whatever this is, if we switch it to position 2, then what happens is the field will collapse, and as it collapses, current will flow out of the inductor. Remember, if we have a changing magnetic field, we will induce a current. So there was a field sitting there statically, and then the second we turn off that battery or switch to position 2, that field collapses. So we have a changing magnetic field, but it's changing in just one direction. As it collapses, current will flow out and through this resistor R here, and we'll get a current I. The interesting thing about this is as we charge the inductor or run current through it and it gets into the steady state, and let's mark this down, the polarity in this particular case will be plus to minus of the voltage, and you can see that because of the battery right there. Now, but current is flowing in this direction. It's flowing downward, right? Downward. All right. The moment that we flip to position 2, which is down here in this part of the figure, what happens is the voltage is still plus to minus, but current flows out now. So the voltage polarity stays the same, and this is really key. The voltage polarity stays the same, but the current flows in the opposite direction as the magnetic field collapses. So current flows out of the positive, which is what you would expect. All right, so the current flips direction, but the voltage polarity stays the same. And again, as this inductor, as the field collapses and current flows out of it, there's current and voltage equations, differential equations, modeling equations that will describe how fast this will occur with a resistance R. So this is called an RL circuit. Okay. All right, so that's what an inductor does, and we can use these, and again, these have certain properties, and they have properties when you're talking about AC or changing signals, and these are reactive components, so they do not dissipate power, just like a capacitor does not dissipate power, and the reason why is because the current and the voltage in an inductor are out of phase by 90 degrees. So in an inductor, current and voltage are out of phase, and by 90 degrees exactly. And remember, they have to be in phase, either exactly in phase at 0 degrees angle or something from 0 to 90. If they're not, then when you multiply these two things together, you're going to get no real power. You're going to get 0. And remember, we talked about the power factor and all that same kind of thing here. So when current and voltage are out of phase by 90 degrees, the waveforms, you will get nothing. So they have to be from 0 to 90 minus some small amount so that you'll get some overlap and you'll get some actual power. But inductors, at least ideal inductors and ideal capacitors, are reactive and they do not dissipate power. We'll look later at some equations that will describe their actual impedance as a function of the frequency of current that we're running through them or voltage we're running through them, but not yet. Just right now, I just want to talk about them just for a minute here, just so you can kind of see them. All right. And types of inductors, they're inductors that are wrapped on ferrite, which is iron, inductors that are just in the air, inductors that are ferrite beads, big inductors, small inductors, all kinds of inductors. And here on Wikipedia, there's some nice pictures here. You can Google and look for some. But here's this right here are 3 different inductors. This one's just wound around this kind of a core. This one is wound around this ferrite rod. And then this is another inductor right here. And all this is a piece of ferrite, a little cylinder of ferrite, and then just a couple windings around here. And again, when we have a transient signal or an AC type signal running through this inductor will become a higher impedance. And inductors do not like to pass high frequencies. They will block high frequencies, whereas capacitors, the opposite of inductors, like to pass high frequencies. So inductors have high impedance as the frequency goes up of the signal going through it, and capacitors have high impedance as the frequency of the signal goes down. So capacitors block high frequencies, capacitors pass high frequencies, and inductors block high frequencies. All right, and when we see the modeling equations, you can see that happening. So again, a lot of times, so here's some axial lead inductors, so they look like resistors, and this is kind of a big problem. So if you look and you have some of these little parts in your parts bin or whatever, you might actually think they're resistors. And sure enough, if you look close at this image, this one looks like it's brown, black, brown, and then it's actually got gold. And you can get really confused on how to read these. So again, you want to keep these things separate from your resistors, because if you have axial lead inductors, you might mistake them and vice versa. All right, and then also I wanted to show you, and then these are some of these modeling equations, which we'll go through a little bit, and they're calculus-based. Lenz's law is important. Lenz's law basically states that as we run a current through the inductor will, the polarity, the voltage, it'll generate a voltage to oppose that current, and so the polarity will oppose the current flow. All right, and one thing I wanted to show you here, which was kind of interesting, there's some more inductors kind of all over the place there. And there, in your power supply, there's an inductor. Here's some inductors with lots of windings. Here is a ferrite bead, and we actually looked at some of these a little while ago. All right, and then here, this one's interesting. So this is an adjustable inductor. So by rotating this, it changes the windings and so forth to change the inductance. So this is a big mechanical, basically adjustable inductor. All right, and then again, there's, and we'll look at this, and we're getting ahead of ourselves here, but X of L, this is the impedance or inductive reactance. It's called X sub L, and it's 2 pi FL. So L is the inductance, 2 pi is just 2 pi, and F is the frequency. So we can see the impedance goes up by proportional to 2 pi times the frequency and times the inductance. So it's proportional to F. So if the frequency goes up, its actual impedance goes up, and we can use that property to design circuits and filters and oscillators. All right, and the same thing with capacitors. Capacitors, actually, X sub C is just 1 over 2 pi FC, so it's just 1 over. So they're inverts of each other. All right, but we're going to get to that. We'll get to that later. All right, so let's go back here to our stuff, and let's take a quick look. I want to measure some inductors really quick and show you a couple problems with measuring them, and then we're going to come back and we're going to talk about transformers, and we're actually going to do some experiments with some transformers. That'll kind of be fun. So let's go over to the bench camera and let's mess around with some inductors real quick. Okay. So what we see here is one of my little parts bins, and this has a number of different inductors inside of it. And we've seen this before, so I'm going to kind of run through this really quick. And just like I was saying, we have the situation where we've got some inductors that actually have a value written on it. So this is actually 10 microhenries, so it's 10.0 microhenries. And so there's this plastic sheathing is over it to protect it, but there's a winding in there and then ferrite that the inductor's wrapped over. Okay, so that's like 10. And then we can look here, rolled away, and then here's another one. So this one I believe is 220, so it's 221. So that 1 means times 10, so it's 22 times 10, so that's 220. Another inductor. All right, and then that ferrite bead that was in the picture on Wikipedia, there's one right there. So just a piece of ferrite, which is powdered iron, and then just a couple windings, and then that will give us some impedance to an AC signal, which we may want in our circuit. And then, like I was saying, we have these axial, and axial again means, you know, lengthwise. We have these axial inductors, and let's actually take a look at that on the zoomed in screen. So let's take a look here, and there you go. So you can see, and there's a code just like the resistor code for reading inductors, and typically now the problem is this is not as uniform as the normal resistor code. So you know, if you lose what these inductors are, many times you're going to have to measure them because different manufacturers might use a different coding on here. All right, and then here is another one. All right, another inductor, axial inductor. Okay, and then the other thing I wanted to show you, let's kind of zoom back down a little bit, is surface mount. So here's some surface mount. Let me see if you can see that. So, and these are from DigiKey, which is a parts distributor, and these are quite old. And if I look at this, what is this? 2002. Yeah. So I've had this for a long, long, long time, and God knows what I used it for. 33 microhenries at 10%, so 33 microhenries. So very, very small, and we're actually, let's take this out of the package. I just want you to see how small this is. And this would be a surface mount. This would be a surface mount inductor, and let's put it under the zoomed camera. So that's what it looks like there. And you see it says a 330 on it, luckily. And then you can see it's got two metal flat areas, and that's what you would solder it onto your circuit with, or your surface mount printed circuit board. So the question is, when we're doing electronics and designing stuff, if we are using surface mount parts, then you know, they're going to get lost, they're going to get this and that, so it's hard to keep them organized. So one thing, as we're prototyping and we want to put that into, say, our solderless breadboards, you know, what do? So here, for example, and let me zoom in on this a little bit. So here is an example where I've got a number of inductors which are surface mount, and these are all surface mount inductors. Right here, and see the camera focus on that, and this one looks like it's 3.3 microhenry and 0.45 amps is its saturation current. And then so I'll mount them on these little boards and then write the information, and then this way I can put this into our solderless breadboard, right? So if we have our solderless breadboard from our previous experiments and we want to do something with an inductor, but we want to use a surface mount inductor, so I can just do that. All right, now if we have a through hole inductor like this, sure enough, we can do that as well. All right, but if we're using surface mount, we want to use those, we can actually do that kind of thing. And again, you know, all kinds of different sizes. Here's another manufacturer here. And then again, this is something that you should do. So you can get these little boards, these little adapters, and there's lots of companies that make these. You can look online for surface mount component adapters or surface mount to dip adapters. Anyway, and then you solder these things on here. And then, you know, I've written down, this is Cooper, and this is 47 microfarad, 1.3 amp saturation current. And then also I've written down what its resistance is. It's just the resistance of the coils of wire. The wire, real wire. So even though it's an inductor, that's what makes it not perfect, not ideal, is it's actually made out of wire, and the wire has some resistance. And I believe this one says like 200 milliohms. All right, so you have to take that into consideration when you're doing calculations. Okay. All right, so now before we go, what I'd like to do is do a measurement and just measure quickly one of these inductors. So let's get a couple of these inductors. Let's see if we can measure them. All right, and I'll show you some of the problems that you're going to have. So if we take one of our meters here, now many meters don't have this functionality. So inductance is something that's usually expensive to measure. So this meter, for example, and I'm going to zoom out just a little bit more and I'll come back in a second so you can see better. This particular meter right here does have inductance, and you can see it's on the top scale here, so there's capacitance and inductance. And so it can measure. So we're going to put it into inductance mode. Then the other thing that's important, where the probes go, over here, this right probe, you can see voltage, and then ohm, and then the other symbol there is the capacitor, and then hertz for frequency. So we got to pull this probe out, because the probe that we want, see this probe here says milliamp, micro and milliamps, and then also has the symbol for inductor, and then also temperature. So we got to pull this out and put this probe in the right place. And so you got to be careful and pull your probes out and understand your meter and read the manual. Right? There's no hard fast rules about these meters. You just have to read the manual and understand what's going on. Okay. Now, since this particular meter has more than one function per wherever this dial is, the orange button on this particular meter is going to change what the function is. Right now it's measuring nanofarads. We don't want to measure capacitance. We want to measure inductance. So I'm going to press this until I see this change to inductance. Okay, so now it says millihenries. All right, nanofarads and millihenries. All right, now I'm going to press the range button and see if I can change the range here a little bit. All right, so I can move this decimal place back and forth a couple times. All right, now I'm going to get the leads here. So I'm just going to grab the leads. And what I'm going to try and do here is measure one of these inductors. So this should be 10, I believe, and this one I think is 220. All right, so let's see what happens. Now, if I were to measure the inductance between my fingers, right, typically you won't get anything, but you will get capacitance and you will get resistance. So when we're measuring an inductance, you can be fairly safe if you kind of touch your fingers onto the device under test. You're not going to disturb it too much. It's not a good idea ever to touch because you want to have a really good reading and not have anything else disturb it. But in this case, inductors, you're kind of okay. So, but nevertheless, I just have a habit. And then another thing, these leads, let me take a look under the zoom camera real quick. You can see the tip. Let's see if the camera will lock into this. Of course not. All right, so there, see that tip? And a lot of these tips have this little notch in them, and the reason why is it makes it easy to kind of capture. And yeah, see that? I can capture that, and so I can kind of grab that real good, right? So that kind of helps when you're trying to touch something and not slip past it, okay? All right, so let's do this. So here we go. So we're going to try and measure this, and again, this is going to have to be super difficult, so now I'm going to give up and grab one with my finger. All right. And you can see it says 0.02. 0.02 millihenries. All right. So 0.02 millihenries. So if we were to move, and again, we don't really know if this is accurate, right? Because we're just not quite sure. So now it's saying 0.01. So because we're not measuring something, we're measuring microhenries, I'm not even confident that I'm going to read this right, and we're even get a value that's even remotely accurate. So this is, I don't even want to use this meter. All right. So what else do we have? And if you recall, we have our actual LC meter. Remember this one? And so again, we've got this LC meter. And if you look on this meter, the scale on this is not doing us much better. So if you look at the inductance scale over here to the right, 2 millihenries, 20 millihenries, 200 millihenries, 2 henries, and 20 henries. So this has got a real high scale. So you can measure very large inductances. So measuring small inductances is not easy. So I'm going to put it on 2 millihenries. I'm going to turn the power on, and then I'm going to go ahead and I'm going to put my probes on here, and these little now remember, wire has inductance, right? Wire has inductance, so you want these leads really, really short, and that's why we have these tiny little short leads. All right, so I've got my inductor connected in there, all right, and now I'm going to press the test button. Okay, and now we've got a better number. So this is supposed to be 220 microhenries, right? So that would be 0.200 and something millihenries, and it's reading 240 millihenries, right? 0.240 millihenries. So that's 240 microhenries. So this meter actually worked, and this measured what we wanted it to measure, and it's accurate within the accuracy of 10% or so. So that did the job that we needed to do. Now, why did I show you this example? Because if you have this meter, and say you spent $200-300 on a meter like this, whatever, and you put it on there and you measured it, you wouldn't have an accurate number. And that's why you have to have many, many pieces of equipment many times so that you can get an accurate reading. Okay? And a lot of times you just have to have, 2 or 3 things give you the same result, then you know that you're in the ballpark. All right? And let's see here. Let's do one more little test before we turn this all off. So let's do this guy, which should be 10. This should just be 10 microhenries. All right, I don't know if we'll even be able to read it. All right, there we go. And let's press test. And pretty good. It's reading 17, 16. And again, I'm not comfortable with this accuracy, so I'd want a different meter that has a lower scale, down in the microhenry scale. All right, so that's it. So we're done there. Okay, so we're finished up right now. Now we're going to go over transformers, and we're going to do some experiments with this. And this is, and we're going to take a look at some equipment. We're going to take a look at the oscilloscope and the signal generator. So this will be kind of fun. So let's stop right here in this lecture, and then let's catch up with each other in the next lecture. All right, so finish up, and I'll see you in the next lecture. Bye. Okay, welcome back. Welcome to the next lecture. So we're going to continue on with our discussion here of inductors and transformers. And now we're going to talk specifically about transformers, which are an application of inductors and inductance. All right, so a transformer is a device that has basically 2 inductors and 2 or more inductors. And these inductors are mutually wrapped around each other, or around, for example, this is an iron core here, or they could be wrapped around each other in one single cylinder, or even in the air. But the point is that because we have 2 coils of wire, so we have one inductor here, and then we have another inductor here. And then in this configuration right here, this piece of iron, this ferrite, this iron, actually conducts magnetic flux. So the flux that occurs in this first coil will then impinge on the second coil and induce a voltage over here, induce a current over here. So basically a transformer is a pair of inductors in the simplest form, where we apply a signal to the primary side, and then that generates a signal on the secondary side completely by electromagnetic induction. So without touching anything, we're going to generate a current or a voltage in this secondary side. So this has some interesting side effects. So for example, transformers, so where are transformers used? Transformers are used to step up and step down voltages, or step up and step down current. They're used to isolate circuits. So for example, this circuit that's over here on the left on the primary side, it doesn't touch the secondary side other than electromagnetic fields generating and collapsing. So there's no current, there's no way for current to get back to the primary side, or any way for current from the primary side to get to the secondary side. It's all through flux, through magnetic flux. So you can isolate things. So for example, if you're going to mess around with AC systems, you might have heard of a thing called an isolation transformer. And all that really is, and you might have an isolation transformer. So say here in the United States, we have a 120 volt AC system. So you might have a transformer, and its input is 120 volts, and its output is 120 volts. You're like, what good is that? Didn't do anything. It didn't step it up, didn't step it down. But what it did do is it isolated it. So the primary side and secondary side are separate. What this also has the effect of is on the primary side, we're connected to the mains of the power company, right? Many amps of current can be sourced from the mains. But on the secondary side, we just have this little coil of wire, and this has finite resistance, so only so much current can be generated through this coil of wire. So it's a safety feature as well. So it's also a good thing and a bad thing. All right, so anyway, so all a transformer is, in its simplest form, we're just going to kind of look at it like this. It's usually something rectangular, or it could be cylindrical. There are two coils, and the coils are wrapped around each other, or they're wrapped around a core, and then the core itself is magnetic in nature, and flux can flow through it like ferrite, iron. And we call this the primary side, we call this the secondary side. All right, what are the equations that kind of model this? So a real transformer in the real world has a lot of things going on. There's heating, there's inductance, there's capacitance, there's resistive loss, there's things called eddy currents, currents that get generated in the core due to these fields changing. But if we kind of ignore all those second, third, fourth, fifth order effects, the basic equation is V1 over V2 equals N1 over N2. V1 is the voltage we put on the input, and we're talking about AC signals here, primarily sinusoidal signals. And V2 is the voltage output on the secondary side, and N1 and N2, N1 is the number of turns on the primary side, and N2 is the number of turns on the secondary side. All right, and now things like the thickness of the wire, the diameter of these, the geometry of this core, all come into play, but at its simplest form, this equation can tell us a lot of information and is a good starting point. So V1 over V2 equals N1 over N2. All right, so what we can do is we can use this to increase voltages, decrease voltages, step things up, step things down, and that's exactly how the power companies operate. So the power company may send current with voltages in the tens of thousands of volts from the power generation stations. And these voltages may be very high. And then by the time they get to your residential area, they've been stepped down. And that's what those, and you may see them outside in the United States. You see these big green boxes, big blue boxes that are, 6 feet by 6 feet by 6 feet. Those are giant transformers. Those are step down transformers to step down the high voltage. All right. So again, read these notes. They talk much more about it than I'm going to talk about it right now. So you read these notes. We're just going to kind of, again, go over the main points and do some experiments. But the key to this whole operation of the transformer working is mutual inductance, meaning both of these inductors feel each other's inductance, all right, or they become coupled, all right, and that's by that ferrite core. All right, and again, the inductors themselves do have resistance. They are coils of wire, so there's some resistance, so they're not ideal. Okay, and then we have these modeling equations right here, which is just that equation up above, and you can just put this thing in many different forms. V1 over V2 equals N1 over N2. It's as simple as that. So you can take that and start playing with it here. So you can just move things around and get whatever you want. And then the other thing is we can play around with sometimes you can just call the turns ratio N, call it N2 over N1. Sometimes you might see that. And then we can convert things into current, right, if we want. So current will be 1 over the voltage in this case, because resistance will cancel out if you convert. So if you use V equals I times R, and then you say that I equals V over R, and then you put, and then you replace the terms, the V's with these I's, the R's will cancel out, but you'll get inverted equations. So all of it's just simple algebra. All right, so let's go ahead and let's put some transformers to use. So I've got a couple interesting experiments. So first, let's look at some transformers. Let's make some measurements, and let's actually put some AC signals into them, some sinusoids. Let's see what happens. All right, let's go. Okay, so over here on this camera, we see 3 different transformers, and I just wanted you to get an idea of what these things look like. So they can be very small. I mean, transformers can be teeny tiny, that big, or they can be as big as a house, literally. These are 3 transformers that you might see to step down voltages or step up. Now, when you have a wall wart, right, so like your standard little wall wart, let me grab one here. So here's a wall wart right here, and if we look at this, this says 9 volts DC at 300 milliamperes. So this is taking the 120 volts AC, and then it's outputting 9 volts DC. So the DC is happening because there's what's a bridge rectifier in here, which are some diodes, which we're going to learn about those a little bit more, and a couple capacitors to smooth it. But at the end of the day, this is going from 120 down to 9 volts DC. All right, so this is a step-down transformer, and if we were to take the 120 volts and divide by the 9, call it 10. So let's just call it 120 divided by 10, right? So we step down about 12 times and maybe a little bit more. So this is about, you know, a 12 times step down, right? Okay, but what's inside here is just a transformer, and it fits right in there, all right? That's what's in these big guys. Now, just to continue with the analogy here, here's an Apple charger, standard Apple charger, and this is much smaller, and this puts out like 2 amps of current or 1 amp of current, and it's regulated. This is a switch mode power supply. So this typically will not have a transformer at all. It will have an inductor in it though, or inductors, and it uses a different kind of technique to generate or step down or step up the voltage, and that's a switch mode power supply. Later we'll talk about those, but they're much smaller, and kind of one of the first step switch mode power supplies is in the original Apple I computer, right? Which if you're a retro fan, you know that. Okay, so we've got these 3 transformers, and let's take a quick look here. So now these happen to be labeled just because they are, and so let's look at this first one right here. And so it says white orange is 277 volts at 60 hertz. So white and orange is 277, and then black and blue is 120 volts at 25 milliamperes. So first is this 277. So these transformers happen to have been custom designed for me, and these are for an industrial application where we were going to 277 volts, which is industrial lighting voltage up in buildings, right? So these have been wound in such a way that you're going to apply the 277, and then on the secondary you're going to get 120 out, and you can pull about 25 milliamperes before this voltage starts dropping. Okay, so that's one case. So the orange and the white, this is the primary, and then this is the secondary. Okay, so we're going to make some measurements in a second, but let's keep looking. Here's another one, roughly the same size, and again we've got white and orange is the 277 in. And then we've got white and red is 120. So now, actually in this case, now these are manufactured in China, I believe, if I can remember. And so this is probably wrong. So maybe what's going on, so this is an interesting situation. So what you can have when you have transformers is, so this is saying white and red, white and orange, and it's not even talking about the black and the purple, all right? And so this is mislabeled. But what I wanted to show you here was, in this case, what probably is more realistic is that this is the primary right here. So the black and the blue probably are the primary, all right? And this is probably wired wrong because these are all samples, prototypes. And the secondary here has got, so normally you've got the primary and then you've got the secondary, but then you've got this center tapped wire here. And what's going on here is that we've got the coil, right? But in the middle someplace, another wire is coming out of it. So we can kind of get a different voltage, so we can get a different turns ratio, all right? So let's take a quick look at that on the drawing board and kind of just look what's going on with this probably, right? And we're not going to mess with this because I can't remember. And again, since these are samples, the color codes, the wiring's all messed up, who knows? But let's take a quick look at what I'm talking about. If we go back and we look at our transformer here, so we've got our primary and we've got our secondary, and what I'm saying is, and sometimes you might have a secondary that is tapped at multiple places or center tapped, so there'll be another wire here. So like here, the coil goes around, but then someplace in the middle we might take off a tap or another tap or another tap or another tap, many taps. And sometimes you'll see one of these, usually 2 or 3, so it can be really any number, especially if it's a custom design. The same thing can happen on the primary. The primary can be tapped in multiple places, so you can apply different voltages to the primary as well. So you might have center taps on the primary and on the secondary. So either way, can be in your transformer, especially if it's by design. Okay. All right. So let's go back, and then here's our other last large one here, and let's see if there's anything interesting about this. So while I'm showing you this one, so this one's 277 volts, and this is 120 at 50 milliamps. Now, if we look at this one is at 25 milliamps. Now, look at the size difference. So much different in size, and to get that extra current out, we need a thicker wire. All right, so the wire is thicker, and we're dealing with 277 volts, which is a lot of voltage. So the wire has to be thicker, otherwise it'll overheat. All right, so let's go ahead and we're going to play with this transformer here, because I've tested this and it actually is what it's supposed to be, which is remarkable sometimes when you have things custom made and they're being rushed. All right, so what we're going to do is, so we know the primary is the white and orange, right? And I don't know, does that look orange? It's orange, but on the camera it kind of looks red. So here's a primary, here's a secondary. All right, so number one is we're looking for the turns ratio. So this is N1 side, N1 turns, and then this is N2 side, N2 turns. So we don't know what the turns ratio is, but we can measure it. So the length of wire, right? So the number of turns will be proportional to the resistance of the wire, all right? And so if we can measure the resistance of both of these sides, we can sort of accurately measure the turns ratio. Now it's not completely accurate, right? It's close, but we can do that. So let's go ahead and measure it. So let's get out our meter, and we're going to put it on resistance. We'll put it right here. All right, and then I'm going to go ahead and measure the primary resistance. And this is, again, just to give us an idea of what we think is going to go on here. Okay, so the primary, I've got my leads on the primary. Now, I want you to watch what happens. So we've got this on resistance, and the scale, let's put it on ohms. Okay, there we go. So I'm measuring it, and all right, I want a little bit more decimal accuracy maybe, so what I'm going to do is I'm going to move the range to ohms here. Let's see if we can just put it to ohms. All right, and let's see if it'll measure. No, it's out of range. Let's go one more time. Out of range. Let's go one more time. There we go. So, all right, so 0.9589. Now, I'm holding this with my fingers, and I'm about a couple hundred K of resistance. Let's actually see. So right now, finger to finger, what's my resistance? So I'm not in the K range, right? But if we go to the meg range, we go up to high K, there we go, meg range. So I'm reading about 1.6. Okay, so about 1.5 meg ohms. All right, so I'm actually adjusting the circuit. So we want to take me out of the circuit. So I'm not going to hold both of these leads. Okay, I'm going to try and just hold one of them, and then I want to show you what happens here. All right, so I'm going to hold both of them to start, and we get 0.97, 0.96. All right, now I'm going to hold one of these and just touch it here. All right, and it's about the same. So we're talking about K to meg, so that's a 1,000 or 1/1000th error introduced by my impedance, so it's okay to hold it. And again, I want you to have a feel for this stuff so you know when you're doing something that's going to cause a measurement error. Okay, so about 0.96, let's call it 0.96K. All right, 0.96K for the primary. So we're just going to write that down, 0.96K. All right. So 0.96 K ohms. All right, paper and pencil. Okay, let's come back over here and let's measure our secondary. All right, straighten everything out. All right, and we're getting about 0.34. And let me take myself out of the circuit for a second. 0.34 as it should be. Okay, so 0.34 K. So 0.34 K ohms. Now, you notice, why am I not writing all the decimal places? Why am I not rounding up and all that? The reason why is because the meter is not that accurate. It's within whatever it is, a percent, 0.1%. And all the parts we're using are within 5 or 10%. So you don't have to be that dead accurate when you're doing calculations to 3 decimal places. Usually just 1 decimal place or 2 decimal places will suffice unless you're doing precision work, all right? But for this, we're okay. All right. Okay, so now we have measured the primary and the secondary side. And so now let's take a look. Let's go back to our screen here, back to the drawing board. the blackboard, and let's take a look at some math and see what we expect here to go on. So let's go do that. All right, so the first thing is let's write down our simple model of the transformer so we know what we're talking about here. So let's go get green. So we know that on the primary side, right, we're going to call that V1. So we know that V1 over V2 equals N1 over N2. All right, and so V1, N1, that's the primary side, and V2, N2 is the secondary side. All right. Okay, so we want to know first what we think these N1 and N2 are. Right now, the cool thing is if we measure the turns is going to be proportional to the resistance. All right, and maybe it'll be nonlinear because of the construction of the transformer, but it'll be close enough. Okay, so let's go ahead and let's take our values down. So we figured out that the primary resistance. Okay, that is literally the worst primary resistance. And it's not as easy as it looks drawing on these tablets. Okay, so let's try this again. Primary resistance. Okay, that's about as good as you're going to get. Primary resistance, and we figured out that that was 0.96 k ohms. All right, and then we did secondary resistance. And we figured out that that was about 0.34 k ohms. Okay, so I am submitting that if we use these values, these will be proportional to the turns ratio, all right? And we can use them in this equation up above. All right, so that says that V1 over V2 equals N1, and N1 is the primary, so we're going to just say that this is 0.96. And the secondary is 0.34. All right, now we're going to excite the primary, so we're going to apply a signal to the primary, all right, and we want to use this as a step down transformer. So it says on it, it's 277, so it says it's 277 volts to 120 volts. So if we take 277 and 120 and we look at what the step down is there, right? So if we take 277 divided by 120 on our calculator, we get 2.3, approximately 2.3. So it's stepping it down 2.3 step down. All right. If we invert that, if we take the inverse of that, right, it's 0.43. All right. So 0.43. All right. So whatever the input is, the input voltage. So whatever the input voltage is, V1, right, times 0.43, that's going to equal what the output voltage is. So if we look at this equation over here, let's move things around. So we're looking for V2 as a function of V1. So let's invert both sides, right? That's simple algebra. So V1, V2 over V1 equals, and then flip this side, 0.34 over 0.96. Therefore, V2 must equal V1 times this quotient here, which is 0.34 over 0.96, which really just says, if we go back up here, right, we can recast this as V2 equals V1 times N2 over N1, right? You can just write these in any number of ways. Okay, so now we have this right here, all right? And now let's compute what this ratio is here. So it's 0.34 divided by 0.96. So 0.35. So this is approximately equal to 0.35. And the label says it should be about 0.43, so they're in the ballpark. So we just used a crude calculation of measuring the impedance of the coils, and that gave us a really good starting point to figure out what the output voltage should be. All right, so now let's go ahead and we're going to actually excite. So this is what we're going to do. So let's take a look at what we're going to actually do here. So let's go get yellow here. All right, so here is our primary. Here's our primary, and here's our primary coil, and plus to minus, all right? And then we're going to have our transformer, all right? So here's our transformer, which is a bunch of iron ferrite core, all right? And then we're going to have our secondary here. Here's our secondary, all right? And so here's our V1. Here's our V2. So we're going to excite the V1 side right now, and we're going to excite this with a sine wave. So we're going to put a sine wave into it. All right, and that sine wave is going to have a certain peak, right? So what do we call this? We call this V peak, and this is V peak max, and this is V peak min, right? And this could be 0 volts right here. So this could be 0 volts right here, right? Maybe not, right? It could be this AC signal could be riding on a DC value, but just for now, call it 0 volts. VP max, VP min, and then what else do we have? Remember, what else do we have? We have this value here, which we call the RMS value, all right? Okay, all right, so we've got all these things, so we're gonna excite this, and what we're expecting is if we put in some voltage, say we put in 10 volts, on the primary side, we're expecting it to step down by 2.3 times or 0.43 the input. So if we put in 10 volts, we should expect about 4.3 volts out. All right, says the label. Our measurement says maybe we should expect out about 3.5 volts. Reality is someplace in between because this number up here, right, that's on the label is for an unloaded transformer. It's when there's no load. And if you recall, it said, I believe, 25 milliamperes is how much current you can pull out of it. So what that means is if we pull 25 milliamperes of current out of it and we put a load that at whatever the voltage is, the 120 volts, pulls 25 milliamperes, then the voltage will stay around 120 volts. But if we try and draw more current, the voltage will actually drop. If we draw less current, the voltage may be higher. So we're going to be measuring the open circuit voltage of the secondary. All right, so that's one thing. So I want you to just remember this word, open circuit. Okay, open circuit, no load. All right, so here's the situation. So now let's go ahead and let's excite the primary and see what happens on the secondary. So the first question is, how are we going to do this? What are we going to do it with? Are we going to plug this thing into the wall? Absolutely not. I don't want to kill myself right now. So, and secondly, we don't have 277 easily available. I can generate 277 with a special kind of transformer that I have, but we're not going to do that. We're going to use a very small signal, and we're going to use a device called a signal generator, and we're going to use another device called an oscilloscope, which both of these things we're going to learn about as we go and as we need them when we talk about equipment. But we're going to just jump in right now and take a look at these two very useful devices for this experiment, which is why this is going to be fun, all right? So let's go jump back to the bench camera and let's go take a look at hooking up the transformer, exciting it with the signal, looking at the output, and then we'll come back to this screen here and see if some of this is making sense or we're accurate at all, okay? All right. Okay, so we're here on the bench, and we've got our transformer here that we want to play with, and we want to apply a signal to the primary. We're going to apply an AC type signal, and we want to see what happens on the secondary. So our first problem is we don't want to plug this into the wall. We could actually plug the primary into 120 and things would work, but I don't want to do that. I want to mess around with high voltages. We don't really need to do that. All right, and so we know that white and orange is the primary, and we know that blue and black is the secondary, okay? So we're going to inject a signal into here. All right, so the first thing that I want to show you is a couple pieces of equipment, and then what we're going to do is we're going to move the camera to kind of a wide view so you can kind of see what I'm doing. So you're going to have to look closely. But first, let's take a look at a couple pieces of equipment here and run a couple experiments with them, all right? Okay, so the piece of equipment that you're looking at right now is an oscilloscope. All right, and an oscilloscope is a device that can measure and render signals in real time. And so typically it has 1, 2, 4, 3, 6, 8 input channels. Okay, so this is a 2 input, and so commonly you'll see 2 and 4 input oscilloscopes. And these inputs, you apply a signal, and then on the screen you'll see the signals drawn. So right now these signals are flatlined. There's no input signal, so we're not seeing anything. All right, and there's many controls, positions of these these are called traces, how fast the oscilloscope is sweeping the rendering, the gain on the inputs. These right here control the gain, all right, so that we can amplify and look at microvolts and millivolts and actually see them on the screen. And then this particular oscilloscope, this is a Hantek DSO 5202B, and I don't know if you can see this, but this one is a 2-channel, 200 megahertz, 1 gigasample per second. And so what this means is it can look at signals that are about up to 200 megahertz, all right, and be able to sample them. Now this is a completely digital oscilloscope. That's different from an analog oscilloscope. Now, before there were only analog scopes, and how they worked is they actually had a CRT, a little cathode ray tube, and there would be horizontal deflection plates, and there would be vertical deflection plates. And the system would get swept from left to right, so the actual electron beam would get swept left to right by internal circuitry, the horizontal drive. And then as the signal that you input would change as a function of time, it would modulate the vertical deflection plates, and you would actually see the signal draw on the CRT screen. So it's purely analog. The signal would come in, it would be amplified, purely analog, and then it would be sent directly to the horizontal and vertical deflection plates of the cathode ray tube. And you can look up how a cathode ray tube looks and see how that goes. Now, if you want to see one, here's what a couple of them look like. So here is a Textronics 2247, for example, and then here's another one, all right? And both of these are analog oscilloscopes. They both work just fine. And but I prefer using the digital now because it records everything and you can do signal processing on it. All right. But if I really want to look at something, I'll go back to the analog scopes. Okay, so that is our oscilloscope, and we're going to use this to view the signal. All right, so now how are we going to generate the signal? Okay, well, we're going to use a different piece of equipment for that, and that's over here. And this piece of equipment is called, fittingly, a signal generator. So this is a signal generator, and the signal generator is a device that generates signals that are programmable and outputs them on a couple outputs. And you might have 1 channel or 2 channel like this device, or 3 or 4 or whatever. Again, you know, a complicated device. Over here on the left is showing the parameters of the channel 1. Over here on the right is the parameters of channel 2. And you can see right now it says 60 hertz, 10 volts, and offset is 0 volts, and the phase is 0. Now I can change what the output waveform is, a square wave. I can make it a ramp wave. I can do a pulse. I can do noise, arbitrary harmonics, countless things. This is a very complicated and very flexible device. This is one of my favorite toys, actually. And this is a Rigol DG4102, and you know, this is fairly pricey. I think these are anywhere from $400 to $800, and the O-scope that I just showed you, I think again that's around $400 to $800 as well. But much cheaper than some of the marquee brands, and almost the same performance. And there's lots of online reviews of these devices. So anyway, something you definitely want to think about in the future. In any event, we're going to use this to generate our signal and inject it into our transformer. All right, and then that signal then will go into the primary, and then we'll read what happens in the secondary by plugging that into the oscilloscope. All right, so what I'm going to do is I'm going to back the camera up so you can kind of see the whole thing from a bird's eye view. The resolution won't be as high, but let's see what we can see here. Okay. So I think we've got both of them on screen here, and we've got some room to do our stuff here. All right, so what we're going to do is first we're going to take one of the output channels of the signal generator, and we're going to inject it into the primary. So first I'm going to turn this all the way down to 1 volt. All right, and again, we'll only be able to drive this so much. The signal generator doesn't have infinite drive. It has a finite amount of current that it can drive. So again, we can't really do things too hard, and it only has about 20 volts I think it can output, so we can't do that much of an experiment. But anyway, all right, so here's our transformer, and now I'm going to take and I'm going to hook up this signal to the primary side. It doesn't matter which side I connect it to. All right, doesn't matter which side, because it's an AC signal. Okay, so now that's hooked up. So now on this secondary right now, if I turn this on, if I turn on this function generator, the primary is going to get excited. It's going to start generating magnetic fields because it's two mutually coupled inductors. Then a voltage is going to get generated on this, and then we're going to take a probe here and we're going to measure that. All right, so let's get our probe. So we'll get let's get channel 2. I was playing with a little while ago. Let's play with channel 2 again. Okay. And we're going to get rid of channel 1 here. So we're going to press this button, and that'll turn off channel 1. So that's off. All right. And we're going to move channel 2 back up here. Okay. All right. Now, here's what a probe looks like. So there's a probe, all right, and ground for the probe. And you can remove this, and it's got this little tip right here, so you can touch things very delicately. Or you can put it on here, and then you can grasp things, all right? So we're going to hook this up, and we'll just hook black to black just for kicks. And then we're going to hook this up to the other side. Okay. Now, we've got our primary, we've got our secondary. The oscilloscope's not doing anything because we haven't turned on the function generator. The function generator is set at 1 volt right now, and function generator is set at 1 volt right now, and so when we turn it on, what we're expecting is the output voltage should be somewhere between 0.35 and 0.43 of the 1 volt. So we should see a peak to peak of 0.43 to 0.35. That's what we're kind of expecting. So let's see what happens. So this button right here turns it on. All right, so it's turned on, and now we're not seeing anything here on the oscilloscope. Why? Well, like I said, each one of these channels has an input amplifier, so we need to change what the amplification is so that we can see this signal. All right, so now we're starting to see a signal, but it's all over the place, all right? So we're going to tell it to track to it, all right? And there we go. All right. Okay, so now we've got that signal, and we can see it, and we can start making measurements. So we know that it's 1 volt peak to peak. Over here on the right is the signal that we're outputting. We're getting a sine wave out of the secondary, so that's good. Now let's start measuring. So now this oscilloscope has a lot of cool features. One of them is we can just press this measure button, and you see the measure button, and we press that, and out of here it's saying peak to peak is about 560 millivolts. All right, peak to peak, 560 millivolts. All right, so that's about 0.57-ish, right? So a little bit higher than what we expect. So this is not stepping down as much as we expected. But again, it's an open circuit, and we're not using it at 277 volts. Okay, so let's go ahead and let's increase the voltage. So over here, we're going to increase this voltage. All right, so I've got an amplitude, press this little amplitude button. All right, and we can start increasing this. So let's put it up to 10. All right, and sure enough, this has jumped way up, so we're going to have to scale it back down. Okay, now we're doing better. And so now we've got 5.44 volts peak to peak. All right, and we've got 10 volts peak to peak here. So again, we're, it looks like it's scaling about down by 2, right? So like a 0.5 instead of a 0.43 or a 0.35 that we were kind of expecting, but that's okay. Again, it's unloaded, so this information here, right, and our measurements are not going to be that accurate. All right, now let's go even further. So let's go up to 20 volts, and that's the limit of where we can go. All right, and now again, I'm going to do something here. Let me do this arm so you can see a little bit better. No, maybe not. Let's go in this arm, and we're going to go to cursors, channel 2, and then what I'm going to do is I'm going to move these cursors up here, and little measurement cursors, so we can see. All right, and we can see that this dV here is about 10 volts. Right, so we're putting in 20 volts and we're getting out 10 volts. Okay, so it looks like it's a, a step down 2 transformer at this point right here. All right, but if we were to put a load on this, then it would drop down much more. But we're not going to put a load on it. Okay, so that was fun. Right, so it's doing what it should do. We're getting a sine wave out of here. We're putting a sine wave in, but let's play with something. So now the transformer is designed so that it works effectively at 60 hertz, which is 50 or 60 hertz. No matter what country you're in, that's kind of the AC frequency, 50, 60 hertz. Let's change it a little bit and see if it becomes more or less efficient. So watch the amplitude here. We're going to change the frequency over here. So we'll go to frequency, and we're going to just change it by 1, by the ones place, and we're going to see what happens. All right, so 61, 62, and as a matter of fact, let's put measurements up here. So right now we're at 10.8 volts. Let's go back to 60 hertz. Okay, so at 60 hertz, we've got 10.5 volts out. Let's go down to 50 hertz. At 50 hertz, 10.0. So see that? So 10.0, all right? And now let's go down to 40. And as we go down, it's getting less and less accurate or efficient. All right, so let's go to 60. All right, there we go. Okay, now 10.5, let's go up to 70, 10.8, 10.9, we're at 85 hertz, we're at 100 hertz, 110 hertz. Now notice what's happening. As we keep going up in frequency, I'm going to just keep rolling this, 150 hertz, 160 hertz. The output voltage is going back down again. So it was going up, and then it was going back down. All right. So again, it was going up and then going back down. All right. So again, this thing has a frequency response, and it has kind of a sweet spot, a resonance spot. All right. So let's just put that over there, and let's lower this back down to 60 hertz. Okay. So that's cool. Now the question is, can we do something else? So this is a transformer. It's a step-down transformer. That's how it's supposed to be used. But can we use it in a way it's not supposed to be used, right? That's what makes electronics fun. Yes, we can. So I'm going to turn off the signal generator. I'm going to go down to the amplitude. I'm going to turn this all the way down to 1 volt. Now, if this was a step-down transformer in this direction, wouldn't it be a step up in the other direction? Absolutely. And in general, depending on the design of the transformer, you can use it in both directions without damaging it. Of course, if you're unsure, contact the manufacturer, but many of these things can be used in the different direction. Of course, you can't apply the same kind of voltage, so I'm not going to go applying 277 volts to the secondary in hopes that this thing's going to step it up to some giant voltage. I'm going to, you have to keep it in the same ranges because that's how it was designed. All right. So now the primary is over here. So now we're going to switch and we're going to use this as the primary. So we're going to use the secondary as the primary. So now instead of a step down, it'll be a step up transformer. And we're expecting it to step up a couple times, right? Let's see what happens. Okay. So let's go ahead. We're going to put our oscilloscope on here. Okay. And those transients are just me touching it. Okay. So here we go. Everything looks good. Okay, let's go ahead and let's turn on our signal generator, and let's see what happens. So we turn on our signal generator at 1 volt. All right, now let's make sure we got everything. And oops. All right, so there our signal generator's on, and we look at the signal. Let's amplify it here a little bit so we can see it. So it says we've got 2.5 volts peak to peak. We put in 1 volt, so we're getting a step up of about 2.5, a little bit more step up than we were getting step down, because we're using it in the opposite way, so it's different things are going to be going on in this. All right, so that's cool. Let's increase the voltage. All right, so let's go to 5 volts, and now we went off the scale, so we're going to adjust this. And now we can see here it says it's 12 volts. So 5 volts now went to 12. See, now it's stabilizing more. It looks like it's tending towards a 2-to-1 ratio, right? So let's keep going. Let's go to 10 volts. All right, so now we got 10 volts. Let's lower this. And now we got 25. So now we're back at a 2.5 ratio. All right. And let's keep going up to 20 volts. And now we've got 50 volts out. So we put 20 in, we got 50 volts out. All right, and that's the peak to peak. Now also look, we have root mean square 16.8, right? So 16.8 is the root mean square. All right, and let's make sure that that's right. So if we were to take half of the peak voltage, which is 49.6, got your calculator, divide that by 2, that's 24.8, multiply by 0.707, that will give you the root mean square, and the calculator says about 17.5, and we're reading about 16.8, on this oscilloscope here, so within the margin of error, I'm happy with that. Okay, so we've got this maxed out. Now, let's see, can we get more out of this? So remember the frequency, so this thing is going to have a kind of a resonance spots. This transformer is going to have more efficiency at different frequencies. So let's go back up to frequency here. All right, and let's just go by 10, so I'm in the tens place. Okay, so we're maxed out at voltage, and let's say we just want more power out of this. We want more power. Can we get more out of it by increasing or decreasing the frequency? So let's decrease the frequency to 50 hertz, and our root mean square just dropped, and we're at 10 hertz, and it's horrible. Okay, let's go back up to 60. All right, there, our peak to peak is back at almost 50 volts. Let's go to 70. All right, it's up over 50 volts. Let's go to 80. It's kind of staying there. Let's go to 100, kind of staying there. 110, 120, up, now it's going back down. And there you go. So it looks like from about 60 to 100 hertz, that's our sweet spot if we wanted to use this as a step-up transformer. Okay. Now let's look at something else that's interesting. Right now we're doing this slowly moving sine wave. If we put different kinds of signals in here, we can get different kinds of effects. So on our signal generator, let's go ahead and let's put in a different signal. So let's go and put a ramp signal in. So you can see it changed to a ramp signal, all right, which is this kind of sawtooth looking thing, all right. And notice that the voltage is roughly the same because it kind of looks like a sine wave, right? So not that much different. It's fairly slowly rising and fairly slowly falling, right? Now let's go to a square wave, and we're going to learn the modeling equations for the inductor a little bit later in the lectures, but there's a term, and it says V equals L, inductance, voltage equals L times di dt. So dt, so delta time, right, has something to do with the voltage. And if dt is really small, so in your mind, think for a second here, V equals L times di dt. If dt in the denominator is really small, you're going to get a really large number. We'll look at that in a minute. And so if we have a square waves make instantaneous changes. So this time that this current is flowing is very, very small. So it creates a spike. So watch this. So now we're putting a square wave in, and now look at our voltage out. We've got 130 volt peaks. 130 volt peaks, and then the cyclic RMS has increased to 23. So we've got this kind of horrible looking signal on the output. We put in a nice square wave. That's what the input looks like. But on the output, we've got kind of this horrible bent up wave. That's what the inductor of the transformer does to it. But what we gained, if we wanted it, was we gained these little transients, and let me put one on here for you so you can see it. And of course, everything has got to fight with you when you're doing things in real time. Okay, so I'm moving the horizontal position here. All right, there we go. Okay, and see this right here, this ringing effect? So if we go and we look at that, and we measure what is going on here, right? It's saying 75 volts peak to peak. So something, it may be heating, it may not like this. So let's go back to the sine wave for a second, and now we'll go back. And we want to be careful we're not touching this now, I hope. Now what may have just happened is I may have set off the signal generator. It may not have liked that. All right, we're going to turn it back on. All right, and let's go ahead and drop the voltage. Back again. Okay, so I got that back to neutral. Sometimes if you send out a signal and you get a large voltage, so the transformer is a two-way device. So if something happens on the secondary, it actually can reflect that back to the primary, and the signal generator may have not liked that. So everything got wonky for a moment. Now it's all back working again. All right, but all I wanted to tell you was that if we do put this square wave, so now we've got the square wave in, and we see these impulses right here, and these impulses are very high. And this is one of the reasons, and let's go to amplitude, so let's put this up to 20. These impulses are very high, and it's reading these, and again, we don't know how accurate this is because we don't know exactly what the oscilloscope is reading. So we can go to cursors here, and then we can take our cursors, and again, I want to make sure you can see this, sorry. So let me move this one here. So, and then let me move this one up here. All right. And yeah, it's about 125 volts. So the measurement that's displaying on the screen is actually accurate. But this event is so small, this little transient is so small, and that's what I want to show you right here. It's very, very small. So the time that happens, and let me show you what that is. So if we say we want to measure time here, now we take our cursors. And so the time of this entire event is from there to here. All right. And it's only about 200 microseconds, so 200 microseconds. So that little transient is very, very fast. However, that high voltage transient could damage your circuit. So the point that I'm making is that that's why we drive transformers with sine waves and not square waves, because the short time of the rising edge and the falling edge of the square wave is going to cause very, very high voltage spikes. And those voltage spikes can travel back through the signal lines and damage other components if you aren't expecting them. They can reflect back. So that's why a lot of times you'll hear the word slew rate, or you have to slow the edges down. And what that means is even in a digital circuit that's going very quickly, if the edges are too fast, if the rising and falling edges of the ideal square wave are too fast, you can actually damage the circuitry. So what we'll do is, instead of making them square, we'll make them trapezoidal. So it'll go up and down like that instead of straight up. So those times that those signals go up and down, we want to stretch them out. And that slows down that V equals L didt term that I talked to you a few moments ago. All right, so anyway, that's fun with transformers. Let's put this back in sine wave mode so we don't burn anything out. And we've used this as both a step up and a step down transformer, and kind of abused it in a little bit. And again, I don't recommend doing things that you're not supposed to do unless you know what you're doing and you can afford to damage things. And so anyway, keep that in mind when you're playing with expensive equipment. You don't want to break anything. So, and that's why we're using very low voltages. And I know that this signal generator drives a very low current, and I also know that it's got good input protection, so we're not going to damage it too much or damage it at all. So anyway, so that's it. So I will see you in the next lecture, and we're going to start talking more about semiconductors, diodes, and transistors. All right, so see you then, and hope this was fun and interesting. Bye-bye. All right, welcome to the next lecture, and this time we are going to be talking about semiconductor devices and the p-n junction. Now, we've talked a little bit about semiconductors before, and as I said, and I'll keep saying, we're going to talk about things more than once. So we're going to kind of, talk about it in the context of something else, and then we'll maybe use it a little bit, and then we'll maybe dig a little deeper. And then this way, it's not like we're just looking at some new subject and have no clue or idea what's going on. And again, the idea of this course is we want to learn basic electronics. We want to learn how to design some basic circuits, but we want to keep things hands-on. So we want to learn just enough theory so that we know what we're doing, but ultimately we want to be able to build things. So again, a lot of these subjects, especially semiconductor theory, are deep, deep, deep complex subjects. And if you really want to learn more, you can read many books on semiconductor theory, many courses, college courses that you could take online. But we are not going to go into all the depth. We're going to just go just enough so that you have a working knowledge of the material and that so that you can use the parts. All right. That said, let's begin here. All right. So first thing, we're going to talk about the p-n junction. All right. And that's kind of the basis of most semiconductors. All right. And we talked about what a semiconductor was and what an insulator and what a conductor was. So take a look at this figure right here, and this is kind of a good representation of some of these ideas. So we know that whenever we have a material, the outer electron shell, right, we call that kind of the valence shell, and we have electrons in that shell, and those electrons can be bound tightly or loosely. If they're loose, then very little energy is required to move them out of that shell, all right? If they're tight, then more energy is required to remove them out of that shell. Okay, that said, we have insulators and the valence band, all right, to the conduction band, we have this very large energy gap, and we measure this like in electron volts. Doesn't really matter, but electron volts. So if you have matter and it's made of some material, say copper, say rubber, right, which would be a good insulator. So rubber has its electrons in its valence shell, but to get this, to get rubber to conduct, you have to introduce an enormous amount of energy to get those electrons to jump out of orbit into what's called the conduction band. All right, so it makes a very poor conductor or a very good insulator because it requires a lot of energy to move those electrons into what's called the conduction band. All right. Okay, now we move to let's move over to conductor. Now in the conductor's case, we have the valence band and we have the conduction band, and these two bands, these energy bands, right, and these are called band diagrams, energy band diagrams. These two bands overlap, so they actually overlap. So the valence band and conduction band, very, very little energy. These electrons are just already ready to go, so they're ready to conduct as is. So you just apply the tiniest amount of energy and those electrons are going to conduct and move out of the valence shells into adjacent atoms and conduct. All right. Now, the thing we're interested in are these semiconductors. And the semiconductors have the property where the energy gap is much, much smaller than an insulator and much larger than a conductor. It's somewhere in between. And depending on what the material is, you know, you can actually look up what these energy levels are in electron volts. But all we really care is that this material semiconductor is somewhere in between. All right. And we learned that we could dope a semiconductor material and we could change its properties so that it becomes a better conductor. All right, so let's keep going and talk about that. So starting with, say, silicon, right, and that's kind of our neutral go-to semiconductor material. It looks like this. Its energy band diagram looks like this right here to begin with, right? It's not a good conductor, it's not a good insulator, it's just kind of something in between. It's got 4 electrons in the valence shell, right? So 4. Now, if we dope it, all right, and remember we talked about doping. We can dope it with something that has 5 electrons in the outer shell or 3 electrons in the outer shell. If we dope it with something that has 5 electrons or something that would be called pentavalent, all right, then we have this situation right here, where we would create an N-type semiconductor. So we've got a silicon matrix, and remember this is a 3-dimensional crystal, and we've got silicon atoms everywhere, and then we introduce phosphorus in this case, which has 1 extra electron. So this is pentavalent, 5 electrons in the valence shell. And we do this through heat. We would diffuse, usually we have pure silicon, we have phosphorus, we vaporize the phosphorus, and then using heat, the phosphorus will then diffuse into the silicon, all right? And you can control this with pressure and temperature and so forth, all right? Semiconductor process theory. But at the end of the day, we just have these interstitial phosphorus atoms, and now the bulk properties of this material changes. We've got these free conduction electrons floating around. So if you look at the periodic table, silicon and phosphorus will bond very well together. So the silicon doesn't really know that this phosphorus is not silicon. It just thinks, oh, okay, and it bonds to it just like it would another silicon. So it's very happy. So these are very happy together. But the extra electron in phosphorus is now free to conduct, and it's just sitting there. All right. So that's how we make an N-type semiconductor. Same thing with a p-type semiconductor. We pick a dopant that has 3 electrons in the valence shell, or that's trivalent. All right, so now in that case, we have a situation like this, and like boron is an element that has that configuration in the valence shell. And in this case, we've got our silicon matrix again, and again, silicon just thinks, boron is close enough to silicon where it bonds to it very well, and everything is fine, except the boron has 1 less electron. So what's happening here is there's a hole. So the bulk properties of this starts to become a p-type material. So it's positively charged net because there's these holes. All right, so we've got p-type, we've got n-type. So we can dope and create these 2 kinds of materials. Now, where things start getting, and you can read the text in the notes here of different materials and so forth. That can make the semiconductors. But where this really starts getting interesting is when we put these 2 things together, this p-n junction. So now if we were to take a p-type material and an n-type material, and you can't just touch them together. These things have to be fused together, so they have to be melted together or some process where they're actually atomically in contact with each other, right? Can't just touch them together. And this is one of the big problems when the first transistors were invented. It was, you're working with these materials and how do you get these things to stick? Anyway, so here's a p-n junction. So let's take a look at kind of what's going on here. So we have our p-type material and we have our n-type material. So the p-type material has a positive charge or really lack of negative charge, or it has holes. So it's overall positively charged. Then we have the n-type material, which has extra electrons, all right? So when you put these 2 things together, something is going to happen. So what's interesting, and this is really interesting, when you take the p and the n-type material and you sandwich them together and you melt them together properly at an atomic level, what happens is you have these 2 different regions, and you've got positive charge and negative charge, and the system wants to get into an equilibrium like anything. So for example, if you take something hot and something cold, you put them in contact with each other, right? They're just, that interface is not just going to sit there. What's going to happen is there's going to be heat flow from one side to the other because the system wants to get into equilibrium, all right? The same kind of a situation happens here. And if you take a look, this region right here in the middle where the interface is, we call this the depletion region. And what happens in the depletion region is, on the N side, positive charge starts accumulating on the N side, and negative charge starts accumulating on the P side. And so this depletion region kind of starts opening up and the system becomes balanced. So given the average kinetic energy of the electrons and the holes as they move around and things are kind of doing what they do, the system finds this equilibrium so that it creates this depletion region. So this depletion region ends up being like a barrier, and it's an energy barrier. So we've created this device that has this region in it, this depletion region, out of an N-type and a P-type material. All right, and so this is the basis of basically all the semiconductor materials and components. All right, is kind of what's going on here. So, all right, now we got that, and now, and again, you can read all this, but I just want to kind of go through this. All right, so now here's where things start getting interesting. We can take this p-n junction and we can put this thing into a circuit. All right, so we can put this into a circuit and we can start applying a voltage and we can see what happens. Can we move charge through this in one direction or the other? All right. The interesting thing is, all right, if we apply a positive voltage to the P side and a negative voltage to the N side, what this does is forward bias this p-n junction. All right, and forward bias, let's talk about the word bias for a second. So bias just simply means voltage, and I believe, I probably learned this 30 years ago, but I believe the word bias comes from vacuum tubes. and some of their nomenclature and terminology, bias. And in any event, bias just simply means voltage. And so this PN junction here, we want to forward bias it, and that's going to turn this thing on. And how it turns on is we apply a positive voltage to the P side, a negative voltage to the N side. And as that voltage increases, what starts happening is this depletion region, right, starts to decrease. Its actual width starts to decrease. And you could think of this as width geometrically, or you could think of it as energy. So as it keeps decreasing, as this voltage, this bias voltage, right, keeps increasing, we keep making it smaller, sooner or later, charge is going to start being able to get from one side of this region to the other. It's going to be able to make the energy barrier leap from one side to the other, all right? And these electrons and holes are going to conduct through the region. When that happens, we're going to get current. So when we forward bias a PN junction enough, we get current flowing through the system. So in this case, we forward bias it plus to minus, plus on the P side, minus on the N side, and we make that depletion region smaller, and we start conducting. Okay? All right. Now, we look at the opposite situation. If we reverse bias it, so if we put a negative on the plus side and we put a positive on the N side, what we do is we open the depletion region up. We actually make it wider, so we make the situation worse. So we make the conduction worse. So there's no conduction to begin with, and now we make the situation even worse. So nothing is going to conduct. So that's forward biasing and reverse biasing. And that is the basis of how the PN junction works. So you've got this PN junction, you got a P material, you got an N material, you put them together at the atomic level, right? So you have this interface. This interface creates an equilibrium where the plus charges kind of move over to the negative side because positive is attracted to negative. The negative charges move over to the positive side because negative is attracted to positive, and this thing sits at an equilibrium depending on the materials it's made, right? What is the P-type material? What is the N-type material? What's the concentration of the doping and so forth? All that semiconductor theory, but that's where this is all coming from. Now we have this little device, and now we can start to play with it and use it as a circuit element to get it to do work. So what can we do with this PN junction? Good question. All right, so we can make a diode with it for as an example of one thing. So here would be the P side, the anode, and here's the cathode, the N side. So a diode is a device that allows current to flow only in one direction. So only in one direction. And with the symbol right here, so conventional current flows in the direction of the arrow. The cathode is usually this vertical bar, and then we have this triangle here, anode and cathode. And again, these names are coming from a vacuum tube theory, right? So early vacuum tubes, anodes, cathodes, there was lots of pluses and minuses, bias voltages, and so forth. So that's all that nomenclature kind of comes from back then, which is kind of passed on into semiconductor theory. So that's where that kind of all comes from. Ultimately, you can Google it. All right, so we've got a diode, and so a diode is a device that takes advantage of this PN junction property. All right, now, depending on what kind of diodes you have, and there are many kinds of diodes, and we're going to look at them in a moment. We're going to actually take a look and see them. But let's take a look at a circuit right here. So we have this simple circuit, and we've got a standard kind of silicon diode, and I'm just going to throw out a name here. Let's just say this is a 1N4001 silicon diode. All right, this is just kind of your go-to little simple diode. And depending on what the diode is made out of, so there's many kinds of diodes, like I said, and there's many materials they're made out of, and there are composites and alloys and inversions and all kinds of different things, countless. But a couple big classes of them are germanium and silicon. And this forward bias voltage that's required to turn this thing on to break over that barrier, right, that depletion barrier, is 0.7 for silicon and 0.3 for germanium. And again, this is roughly, 0.3-ish and 0.7-ish, all right? So assuming we have a 1N4001 diode here, and we have kind of constructed this circuit, we see that we've got a battery, 9-volt battery here with plus on the anode, right? So that's good. So we know that this diode is going to get forward biased. Now, we have a resistor here, and this kind of limits the current. And then we come back to the battery here. So we've got a complete circuit. So now the question is, how do you even analyze this? Now we're going to learn a lot more about analyzing diodes later. But right now we're just going to kind of hand wave a little bit and see how to do this. So the first thing you do when you want to analyze a diode circuit or a semiconductor circuit sometimes is make an assumption. So you assume something's on or off, do the calculations, and then they'll come out correct or they'll come out contradicting themselves. Then you know you assumed wrong. So we've got a positive voltage on the anode here, and let's assume that the diode is conducting. So the diode is conducting, and we know it's going to conduct because we've got this large 9-volt battery. So the diode is conducting. When it conducts, the diode, now here's the interesting thing. No matter what current goes through the diode, and we're going to see this in a moment, no matter what current goes through the diode, once the diode starts to conduct, right, the voltage drop over the diode stays relatively the same. It changes a little bit. It's called the dynamic resistance, but for the most part, it stays the same. And the current can go up and go down. So in other words, once this thing is on, the voltage stays the same, but the current can go up and go down, all right, once it's on. If the voltage drops under the forward bias requirement, then no current will flow. So it's like a switch. So it's like a switch in one direction. Once it's on, then you can keep pushing current through it, but the voltage won't change. That's unlike a resistor, because a resistor, right, if we look at a resistor, it says V equals I times R is Ohm's law. V equals I times R. So R must equal V divided by I. It's linear. So no matter what, if you add voltage, if you increase the voltage, then the current is going to increase. So it's this linear curve. Diodes are not linear, and we'll see that in a second. But let's get back to the circuit analysis. All right, so we assume the diode is conducting. We then assume that roughly about 0.7 volts is going to drop over it. Now, this is not actually true. It might be 0.6, it might be 0.8, it might be something, in that range, because we don't know what the current is in the circuit yet, right? But we're just going to assume that 0.7, it's conducting kind of, in a reasonable, at a reasonable current level, and so maybe 0.7 volts is dropping over it. Now we have 9 volts here, a drop of 0.7, so 9 minus 0.7 is 8.3 volts, so this node is 8.3 volts. Now we've got 8.3 and we've got a 100 ohm resistor. So now we can compute the current. The current in the circuit through here, through here, through here is the same current. There's only one loop in this circuit. And again, we're going to learn more circuit analysis later in later lectures, but whatever the current is in this resistor is the current, right, in the circuit. So V equals I times R, so I must equal V over R, right, Ohm's law. So we do the calculation here, we get 83 milliamperes. So now we have 83 milliamperes flowing through here. Now, is that correct? Probably not. The reason why it's not correct is we made an assumption about the voltage of the diode. It's 0.7. So if we actually put a meter inside of the circuit, an amp meter and a volt meter, we'd see slightly different values. So now what we need to do is via iteration, we could make our calculation more accurate. So now that we know that we've got 83 milliamperes flowing in the circuit based on this 100 ohm resistor, current limiting resistor, we then go to the curve for this particular diode, which we don't know what manufacturer this is. It could be Fairchild, it could be NXP, it could be Philips, it could be this, it could be Vishay, who knows? And we don't know the exact model of it, but if we did, and we said it was a 1N4001, so if we said it's a 1N4001 from Fairchild, et cetera, and all the different specifications, and we got the exact data sheet for this exact diode, then we could look up at 83 milliamperes, what is the forward voltage? And it says, oh, it's 0.63. 0.63 volts. So then we would go and make that 0.63 volts. We would change what that is, 0.63. Then we would say that this node here above the resistor is 9 minus 0.63 volts, which is 8.37 volts. So there's 8.37 volts over here. Now we would take that 8.37 and we would divide by the 100, and now we would get 83.7 milliamperes. So we get a little bit more current going through here. Okay, and then we'd say now we got 83.7 milliamperes, and we go back to the chart again, and we'd say, is there any difference? Nah, maybe it's just the same. It's just there's so little change, and it's not even worth looking at because the resistor is a 5 or 10% accurate resistor, so that's close enough. And again, did you even need to do that? We went 83.7, so we changed not even 1, so 1%. And the resistor itself is probably a 5 or 10%. This is why in electronics you don't need to be too accurate. The parts themselves, if they're only 5%, then any calculation, if you're getting better than 5% accuracy, it doesn't really matter because the parts are inaccurate. If you're down at 1%, you want to do 1% calculations, and so on and so forth. So the electronics should be designed robust enough where they can tolerate some inaccuracy in these values, right? Okay, so there's our circuit. So we've actually used the diode in our circuit and done something with it. We've turned it into a switch. Now, what if this voltage, this 9 volts, was less than 9 volts? What if it was 0.5 volts? Nothing would happen. It's not enough voltage to turn or forward bias this diode on, all right? Okay, so diode characteristics. So definitely read through this. And there's a couple things. So we're talking about the forward bias voltage, right? So we've got a forward bias voltage. And so, you know, and when you go and look at a data sheet for one of these things, all right, there's many different parameters. So real quick here, and we're going to look at some more of this, but let's see here. So here is, for example, a 1N4001, and let me just zoom in a little bit here for you. 1N4001 through 1N4007 Vishay. All right, and these are this is a data sheet, and I got this from an online distributor, DigiKey, and we're going to go through this in just a little bit. But right now, we're just kind of working our way up to it. All right, and the data sheet for this particular diode. Now, even though other manufacturers will make the same diode and they're supposed to follow the same specifications, that's why they call it the same part number. They're all slightly different. So if you want to be accurate, you need to look at the manufacturer you actually bought the part from, right? Okay, so you can see there's these characteristics, and reading data sheets is a whole class in itself, right? There's a lot of material here, but we can look at some things here. So IF, right? So this is I forward, so it says 1 amp. This means that this particular diode can handle about an amp of forward current, all right, before it starts, burning out. So I forward, AV is average, all right? Let's see here, and then some of these things, IFSM, VRRM, you got to look these things up, right? Because you just, unless you're reading data sheets all day, you forget what they are, right? So let's come down here where some things are, written out in English, all right? So there's all these different diodes here, and each one of these diodes has some different properties. So now here's the interesting thing. So the average rectified current, right, this is this IF, is 1 amp. Now peak, so this is a peak forward surge current, right? And it's for single half wave superimposed. You see all this, and every one of these manufacturers has their own kind of way of talking about things in data sheets. But what this is saying is, so if you had a surge current for 8.3 milliseconds and a half sine wave like this, it could take 30 amps. That's very manufacturer dependent, right? So that's a test that they did, and could be a standard test, but it's just something that they have. And so again, everyone's going to kind of have their own testing protocols and so forth, but some things are universal, like this I forward. This is the amount of average forward current this thing can handle, 1 amp. Okay, great. Now these different models of the diode, there's something here interesting. So repetitive peak reverse voltage. So this means if we put the voltage in the opposite way, what's the highest voltage that this diode can tolerate before we destroy it, right? And so the 1N4001 is 50 volts, but the 1N4007 is 1,000 volts. So if we're going to have a circuit with high voltages, we want to use these guys, right? Probably more expensive, right? But if we don't care, then we can use the 1N4001. But everything else is the same here, all right? And let's see here. So this is important, this forward current here. And then the other thing that's important, and the reverse voltage, that's important, all right, to read off of here. And this right here, this piece of data, this VF. So this is, and again, this will be probably at 1 amp, this is saying the V forward voltage drop is 1.1 volts. So we've been saying about 0.7 volts for a silicon diode, and that's about true. But if you push this thing all the way to 1 amp, its internal resistance plus the junction itself, you're going to end up dropping 1.1 volts. Now, if you've got a really good data sheet, a lot of times there'll be curves here, and sometimes they have curves that are useless. And so now I'm not seeing anything I like on this data sheet. So there's one curve here that I like, and this is showing the instantaneous forward voltage versus the instantaneous forward current. So this is actually useful to us. So in this case right here, we see that as the forward voltage increases, all right, then we're seeing what the current is here, all right? And notice down here the voltage is very, very low. And up here the current's going from 0.01 amps up to 100 amps. All right, so where this thing starts to really conduct, we have to get at least at 0.6 volts, all right? And then this thing starts conducting. 0.6 and so forth, and then by 0.8 we're conducting, now this is a logarithmic scale, so this is 100 amps up here, and here's 1 amp right here, and here's 0.1 amp right here, all right? So it's logarithmic in nature. So you have to forward bias this thing at least by 0.8 volts if you want, say, 200 milliamperes. If you want to get an amp out of this thing, right, here's this 1 volt, right, you want to get an amp out of here, right, you got to put about a volt, and then you'll get an amp out of this. All right, so this is where this forward voltage is coming from. But if we have the diode biased from about 0.6 to 0.8, we're going to get up to 100 200 milliamperes out of this. And as long as that's all we need, we'll never need to exceed this forward voltage drop. All right. So anyway, the point is that these curves inside of these data sheets have various pieces of information, whatever the, there's a mechanical, whatever the manufacturer deems is important, okay? So you'll go to the data sheet, and that's, you look at things on the data sheet and see if you like what it does, right? And if it does what you need it to do, all right? Okay, so the next thing that we're going to talk about here is the types of diodes, all right? And there are many types of diodes, and that's too big. Okay, you know what? Actually, let's zoom into that for a second, because that's something I did want to talk about here. Okay, and everything has just got to be huge. All right, so different types of diodes. So we're going to talk about that in a second. But here, this conduction curve, that's what we just looked at with that data sheet a little bit. And what it's kind of showing in another way, and here's this kind of generic curve, is when you have a forward bias diode, so you start applying a forward bias to it, a forward voltage to it, the diode does not conduct. So the vertical axis is current, the horizontal axis is voltage. The diode is not conducting. And then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and then all of a sudden 0.7, this thing snaps on, and then exponentially this current can rise. So in other words, the diode turns on at a certain voltage, this forward voltage, and then no matter what voltage you apply, the voltage wants to remain the same at 0.7, 0.8, and so forth. It doesn't want to keep going up infinitely. But the current will go up to whatever the limit is, maybe 1 amp, 2 amps, 5 amps, 10 amps. So this is the VI curve of a diode. Now, here's what else is interesting. If you go in the opposite direction, the diode will kind of work in the opposite direction sort of a little bit. And what happens here is, but you can see that the voltage, see this minus 50? This is called the breakdown voltage, the reverse breakdown voltage. So if you use the diode in the reverse fashion, right, we're opening that depletion region up, and then, but there becomes a point where there's just so much potential difference, this thing cannot stop current flow, and then it breaks down. And when it breaks down, then current rushes through it. So that's what's showing here. So this breakdown voltage in the reverse direction is important because if you overvoltage the diode in the wrong direction, we don't want it conducting. And that's what this is showing. It doesn't conduct, doesn't conduct, doesn't conduct. But if you push this voltage up higher and higher and higher, and this is just a generic graph, right? It could be 50 volts, could be 5,000 volts, right? Depending on the diode construction. Minus 50, minus 100. But typically these are the kind of ranges, minus 30 to maybe minus 200, and then this thing is going to conduct, and it's just going to break down and start conducting really, really, really hard, and you're probably going to burn it out. All right, so this is the characteristic curve here. all right, of a standard diode, or just, you know, in general. This is kind of what diodes look like. All right, so let's talk about some of the different diodes that there are. And okay, so there's standard silicon diode that we've just been talking about. There's a diode called a Zener diode, and a Zener diode is kind of designed to work in the reverse direction. So it takes advantage of this reverse biasing situation, so that and what it does is it maintains a certain voltage. So Zener diodes are actually used in voltage regulation or to clamp voltages in circuits, and we're going to take a look at those. So a Zener diode is actually used in the reverse direction. All right, and then, you know, normal diode kind of has this triangle and bar, and the Zener diodes kind of have this triangle, and then they have these kind of you know, two little slashes here. And then another diode is also that's really important. It's called a Schottky diode, after William Schottky, the physicist. And Schottky diodes are interesting because instead of using a p-n junction, they just use either p or n in metal. So it's basically one semiconductor, either p or n. Typically it's n material, and then metal, and then that's fused together. So Schottky diodes have a couple interesting properties. One is their forward voltage is much lower because you don't have P and N, so you don't have a depletion region that's as large. So they might forward conduct 0.2 or 0.3 volts, which is really good for some situations. So when you want to use them as a switch in one direction, they only need to be turned on by 0.2 or 0.3 volts before they conduct. So that's important in this situation. They are very fast at switching because there's not a P and N material. So when the diode is normally conducting, silicon diode with a P and N junction, to get it to stop conducting and then get it to conduct again, you've got to move all this charge out of this depletion region. So it's like, you know, things are moving around. But with a Schottky diode, this is not happening. So these things can switch almost instantaneously down in the picosecond range, all right? So whereas normal diodes might switch in the microsecond range, all right? One thing though is because they only have one semiconductor region, a P or an N, they're a little bit more fragile. They have lower reverse breakdown voltages, so they can't tolerate as much as a reverse voltage. Now, because it's the year it is and we have the technology we have, everything is good now. So before, you know, Schottky diodes, maybe they could tolerate a 10-volt reverse voltage. Now you can get them up to, I don't know, I think up to 200 volts reverse voltage. So pretty incredible. But again, Schottky diodes are designed to have very low forward voltages and turn on very quickly and then switch very quickly. All right, so that's some of their properties that are important. All right, and the symbol for it, yeah, let me show you that. It's not on here. Let's take a look what the symbol is real quick for a Schottky diode. So a Schottky diode, and okay, I'm gonna Schottky, try and spell this. Okay, Schottky diode. And what the symbol is typically looks something like this. And that would be your plus, and that would be your minus, right? And it's very similar to the Zener diode, right? And the Zener diode kind of goes like this and like this, all right? That would be the Zener. But the Schottky is like that. They're at 90-degree angles, all right? So that's a Schottky diode. And the cool thing about it, you know, about 0.3 volts, and this thing will conduct very, very hard. So that's a Schottky diode. All right, so going back here, all right, and let's keep moving on here. So we talked about standard rectifier silicon diode, talked about the Zener diode, light emitting diode. We've seen those, the LED, and then if you look at an LED, it's the exact same kind of thing as a normal diode. It is a PN junction. What's interesting about an LED, let's actually take a look at this. Let's draw this. So on an LED, what goes on here that's interesting, and of course this won't let me delete this. Okay, so with an LED, what happens here is they create the device so that on a little pedestal, and if you look very closely, right, and if you look very closely at an LED, you'll see this little pedestal. You actually will see this PN region here. All right, you'll actually see this. And then so the whole idea here is what happens is when we forward bias and we get current to flow, we get electrons, electron plus conventional current to flow through here, what happens is this, is as the electrons are moving across this region, they're making contact and they're bumping into things, and these LEDs are doped in such a way that this some of this energy, instead of just moving kinetically, it actually causes photons to be generated. So as these electrons and as these holes move over this region here, this depletion region, and go from the P to the N side, what happens is energy there's excess energy, and this excess energy is photons. And so you actually have light emitted from the junction. So as this junction operates, light is emitted from it. So you have this transparent plastic enclosure. You have the diode right there on a little pedestal, and so you're going to get light out of here. That's how LEDs work, all right, in their simplest form. So an LED is basically just a diode. It's been doped with certain materials. That's where it gets its color from, and the doping controls its voltages. And the voltages of LEDs are anywhere usually from, and again, everything that we say is with a grain of salt. There are many, many variations of it, but usually somewhere between 1.7 to 3.1 volts you're going to find for the forward voltages for a great majority of LEDs. This will be kind of the red side. Red will kind of turn on at like 1.7-ish, right? And then 3 volts when you get over here to kind of the blues and the greens. All right, they're going to require more energy. Why? Because those photons, green and blue, right, have more energy than red, right? Remember the spectrum. Here's red over here, right? Here's green. Here's blue. And then if you look at energy, right, energy as a function of frequency, energy as a function of frequency, it goes up in this direction, goes up. So that means whatever we're doing here, right, quantum mechanically or with energy levels, we're going to need more energy for blue and green than we are for red, and that translates into this voltage here. That's why you can turn the LEDs on with a lower voltage if they're red and a higher voltage if they're blue. All right? Okay. So let's see what else we got here. Okay. Rectifier, Zener, switching diode. All right, and then now we're getting into the transistor, and I want to save this for two lectures from now. What I want to do now is, now that we've talked about these parts for quite some time, let's come back and we're actually going to build things with diodes, and we're going to play with them and experiment with them and have some fun. Now that we have some theory out of the way, we know we've got our standard silicon rectifier diode. We've talked about a little bit about Zener diodes. All right, we've talked a little bit about the Schottky diode and about LEDs, of course, which we've seen before. So now let's actually build some circuits on the bench and play with them and kind of see what their properties are. All right, so finish up here and I'll meet you back in the next lecture. Bye. All right, welcome to the next lecture. Really, we're just continuing the lecture we had started on diodes, but now we're going to actually build some circuits and play around with the diodes that we talked about now that we know a little bit of their theory. And so we talked about kind of silicon rectifier diodes, kind of standard diodes. We talked about Zener diodes. We talked about Schottky diodes, and of course LEDs, light emitting diodes. All right, so now what we're going to do is we're going to actually look at some diodes, kind of look at them online a little bit, and then we're going to start building stuff. All right, so the first thing is, let's go take a look over at the bench camera, and let's take a look at some actual diodes and just see how to kind of read the part numbers off them when we can do so. All right, so let's go over there. Okay, so down here we've got a few different diodes that I've just kind of picked randomly from my little diode bin. And again, typically I keep these parts in these little bins here and keep them sorted by depending on what they are. So like, here's some capacitors, for example. Here are some resistors, all right? And you can get these at a hardware store. At a hardware store, you can get these bins, and you know, these giant bins, and they have many of these little drawers in them, and then you can kind of sort things that way. So anyway, just to keep things organized. All right, so we've got a few different diodes here. We're going to look at them up close, but I just kind of wanted to show you. So these are all obviously through-hole diodes, all right, and uh, you know, some of them are plastic, surrounded in plastic. Some of them are what are called glass passivated. They have glass surrounding them. But typically all of them look roughly the same. They'll have some body, and then they'll have usually a stripe, either a white or a black or a colored stripe, and that indicates the cathode. All right. And then I just wanted to show you this. This is a bridge rectifier. We're going to talk much more about this when we get to when we start designing a little bit more. But this actually has 4 diodes in it, and so this will turn an AC signals to a DC signal. We'll learn how that works. So this is a bridge rectifier, again through hole. All right. So what I'd like to do is we need to start learning how to get online and kind of look parts up and find things. So let's take a look at these parts and put them under the zoomed camera. And then what we're going to do is we're going to make a list of the parts. So I want you to get out your pads and your paper, or however you like to take notes, and we're going to actually write down what these part numbers are, or these identifiers are, and see if we can look them up, okay? So let's go over to the zoomed camera. All right, so we're under here in the zoom camera, and I've got my pen and my paper, and let's just start sorting these things out here. So let's start with this guy right here, and let's see if we can get a good view with this so we can see what we're doing here. And again, it's always hard to get this camera to focus, but we'll get it. All right, let's see. All right, so all right, and again, it's a little bit hard with the specularity, but I think I've got it right there. So see the top number? It says, and I know it's real hard, it says 1N4006. So let me put that back. 1N4006. Okay, so 1N4006, all right? This is actually a silicon rectifier diode, so we're going to write that down, 1N4006. All right, then what do we have here? We've got, let's try and play with the shadows here so we can get a better look at it. And this one, let me see if I can get it closer maybe. All right, here we go. So what do we have here? Okay, it's upside down. All right, and the bar, that white bar, that's the cathode side, always the cathode. All right, so in this one right here, we've got 1 on the bottom, 1N4001. All right, 1N4001. So I'm going to put that over there, and we'll write that down. Okay, so we got 1N4001, and this one right here is probably the same, another 1N4001. And we might need a couple of these. That's why I have 1N4001. Yep. So we'll put that over there. All right. Let's see what else we have here. We got this little one. All right. And this is actually made of glass. And if we look at this and get this just right under the light here, there we go. And this one is, the letters are written a different way, but it's 1N4001 as well. All right. So this is just by a different manufacturer than the other ones, which are, we'll put them here so you can kind of see them a little bit better. So these are all 1N4001. So the point is, different manufacturers make things you know, that look differently, but they have the same part number, and they all are trying to meet the same specification. Okay, so let's see if we can look at this one here, so we can get our camera to cooperate with us. With such a small object, it's hard for the camera to kind of lock into it. And again, let's see what we see here. And this one is challenging. Let's see if we zoom in a little bit, how that helps us. All right. Okay, and again, there we go. 1N4001. So that's another one. This one's glass passivated. Just has glass around it instead of plastic or ceramic. Right. And so all those are the same type. Okay. And let's see what this one is here. All right. Okay, so this one is a little bit different. And zoom back. Okay, so here we go. So you see the logo there, ST, that's ST Micro. And this says ST PS 2L60. 2L60. So ST PS 2L60 and then a 702 at the bottom. All right, so I'm going to tell you right now, this is a Schottky diode. All right, so we're going to put that over here, put that over there, and then we got this one. So let's see what do we got here. Okay, and again, this is why we sort these things and we label them, because we got to, figure it out again. All right, so this is much better now. This is a 1N4739A, 1N4739A. All right, and I'm not sure what this is. This might be a Zener or it might be a normal silicon diode. So we'll write that down. We got that. Okay. And what else we got here? We got another one of these glass passivated ones. And let's see if we can see it. The camera and the lighting does not like this glass. It's so specular. All right, and yep, 1N4001, if you can see that. So that's another 1N4001. So we got a lot of these diodes. We got a lot of these diodes here that are 1N4001. So we'll keep all these in one pile. Then we have this kind of oddball here, this 4739, all right, and then we've got this ST, which we believe is a Schottky, and then we've got this other one here. Let's take a look at this. And what does this look like? All right, so again, we see a logo, that's F for Fairchild, and this is a 1N751, 1N751. I believe this is a Zener diode, actually, a Zener diode. All right, and the 751, I bet you, is 5.1 volts, so it's a 5.1 Zener diode. All right, so now let's go back to the computer and let's take a quick look and see what these parts actually are. So let's take a quick look and do that and see the process that we would use to look things up and make sure we got what we want to use in our circuit. All right, so let's go back to the computer. All right, so we're back at the computer here, and so now what we're going to do is we're going to just look up what these components are and kind of look at their data sheets just a little bit. And so the first thing is, this is in section 1, a list of different computer distributors that we're going to be using, like DigiKey, for example, and I want to show you how to use this. But there's one thing I just remembered. I wanted to show you this probably a couple lectures ago. We were talking about inductors, and when we have axial inductors reading their value, and so there actually is a numeric system for that, and it's identical supposedly to the identical to the resistor color code, but I've seen cases where it's not. So you have to be careful, and that's why I say keep things sorted and know what the parts are. Don't trust the bands on it unless it's a resistor, but even still with a resistor, I'll always check it. You never know. So maybe that's just being paranoid. Anyway, so the IPC, which is like Institute of Printed Circuits. This is a body that's been around for a long time that creates standards and whatnot for printed circuit development and manufacturing. So they come up with these different standards, and one of them are all these color bands standards. So this link up here I'll put inside the notes, but it's ipctraining.org/DVD164C/charts.pdf. If you just Google for inductor color code, resistor color code, or IPC color code chart, you'll be able to find these. But this is actually a really nice one. And it shows the 4-band resistors, it shows the 5-band resistors, it shows 6-band resistors, and this is why I say these things get crazy. Then it also shows capacitors. They're axial capacitors, 4-band capacitors, and then 4-band inductors, and that's the inductors we were talking about, 4-band inductors. And of course, this is all through-hole components. Then 3-band inductors and how to read them. And then even when you have SMT inductors, surface mount, and I showed you a couple of these, and usually they're in these round kind of little flattened cylinders, like little coins, very, very small, might be 3, 4, 5, 6 millimeters in diameter, and then they have a color code on them. And this is a really cool idea. You can read the colors and read the color code. One of the problems with a lot of this, After handling these things for a little while, the paint is like rubbed off and you can't tell anyway, so you got to measure it. But if the paint is on there, then you can use these as the color code. Again, please never assume anything is correct with electronics. Double check, triple check. Make sure your components are what you think they are. All right. Sooner or later, something will be the incorrect way and you won't verify it. You got to double, triple, quadruple check everything. Anyway, this is a great little chart here. You can see what it is up here on the web URL here, and that'll be inside the notes. Okay, back in section 1 in the preliminary part of the course, we talked about different resources, your parts, this and that, and there was a list of distributors. A distributor is a company that distributes electronic components, and there are many of them all over the place. The distributors in the United States are very, very large, and they fan out all over the world, distributing components from manufacturers from every country. And three or four of the biggest are DigiKey, which is digikey.com, Mouser, which is mouser.com. All right, mouser.com. All right, another very large one is Newark, and this does a little bit more business in the United Kingdom and Europe, which is also known as Element 14. All right, Newark. All right, and those are your really, really big distributors, those three right there. And then there are other distributors that may financially be just as large, but their online system, it doesn't have as many parts. So there's Future, if we can see this, Future Electronics, which I'm not, Future Electronics, another good distributor. But you can see, like when you go in here, United States, their websites, the other distributors' websites are not as developed as Mouser, DigiKey, and Newark. So many times, even if you're going to buy parts from another distributor, we will look on DigiKey or Mouser or Newark for our parts because their search engine is so good. So anyway, there's Future, a couple others I'm going to show you, Avnet. Hopefully I've got the right URL. Yep, Avnet. This is a massive distributor, but again, their website just isn't as user-friendly as DigiKey or Mouser. And the another one is Arrow. All right, so I'll tell you right now, 99.99999% of the time, I look for all my parts on DigiKey and Mouser. Typically, I'll order them directly from DigiKey and Mouser for prototyping. Then during manufacturing, a Chinese contract manufacturer will then order the parts locally, sometimes from DigiKey, Mouser, Newark, Arrow, Avnet, or another source. But during prototyping, it's the best, easiest way. Now, there's another online system, Octopart. All right. And what Octopart is it's a search tool which basically goes through and searches all of the distributors. So it's plugged into their databases, I believe, and can find parts. So if you can see here are all the distributors that Octopart is plugged into. So Allied, Arrow, Avnet, DigiKey, Element, Farnell, Future, Grainger, Mouser, Newark, and so on and so forth, right? So when you plug a part in here, so let's just do a little part. We'll say a 74 LS04A. This is a TTL inverter chip, okay? We type that in, and then it shows us, different manufacturers. So let's say that we like the manufacturer Texas Instruments. We like this part right here, and we click on it, and then it's showing you different names of it and so forth. So this is a great search engine, and it can show you where to purchase the parts, and it can be communicated to via an API. So a lot of programs plug into Octopart, and one of them is a circuit maker that we're going to use in the second part of this course as we design circuits, so that it can search parts for you in real time, which is really kind of cool. But for right now, let's just stick with DigiKey. It's got a really good search engine, and it's fairly graphical, and this site works pretty well. Okay, so let's go back to some of our components here. So the first component was the 1N4001 diode. And again, I'm just showing you the process. This is what we got to do. So if we wanted to build something, we would start searching in DigiKey or Mauser for parts, and we might just say silicon rectifier diode or whatever. And then we see what the parts are available and we start drilling down, reading their data sheets. And this is a long process. This can take, I hate to tell you, hundreds of hours just figuring out what the parts are or the bill of materials for your designs. And over years, you start to learn different parts and you know, hey, I like Fairchild's MOSFETs. I like Texas Instruments TTL chips and low voltage TTL chips and so on. So you learn different manufacturers that you like, but you look for everything on the distributor website typically because it's got everything. All right, so we can see here we've got all these 1N4001s, and this is just a simple search engine, and you can drill down to different things here, and there's just too much information here to even begin to teach you, but we'll just clear all selections. And one thing we can do here is under packaging, we can see these are all through hole. So let's go over here and we'll do through hole because I want through hole. All right. Another thing that's really important is I want it in stock, I want it lead free, and I want it RoHS compliant. So what do these things mean? In stock, that's clear enough. What does that mean? It means they actually have stock. Lead free means there's no lead. Lead is a really bad toxic chemical, and now it's being removed from all electronic development and solder. And so we want lead free. And just for this experiment here we're doing. And RoHS means restriction against hazardous materials and substances. All right, RoHS. And this is a specification. You can Google it. So if we go over here real quick, we say RoHS. All right, restriction of hazardous substances directive here. And there's these guides. You can read about this on Google, and you can read all this material. And there's these big, long documents that describe what you need to do to be RoHS compliant. All right, and a lot of companies, a lot of retailers, they will not sell products unless these things are RoHS compliant. And the way that you design your electronics is such that you're not using hazardous chemicals and materials that are toxic or cause brain damage or cause respiratory problems. And this is a really, really good thing so that we don't do that, because the other problem is all these electronics ultimately end up in a landfill someplace, right? Or they end up destroyed or thrown away, and they go into the environment. They go into the dirt and they leach into it, and all kinds of bad things happen. So this is a good thing. And everything that I designed for many, many years has always been RoHS, and now there's RoHS 2 and so forth. But anyway, these are consortiums that control the manufacturing of products so that they're safer and less hazardous for humans to be around and for the environment. So we'll put RoHS compliant. Everything is almost RoHS compliant now, so that's a pretty easy search restriction. Now, a couple other things. Packaging. Again, you're going to learn what this all means over time. Bulk, cut tape, tape and box, tape and reel. Real quick, bulk just means like it would be a baggie full of parts, and they would just be all in that bag. So there could be 100 or 1,000 or 10,000, a million parts just in a bag. That's bulk. It just means a bulk of them. Cut tape means that either these parts came on a reel, like a tape reel, and so like just imagine a bunch of tape and they're all stuck onto the tape in a certain way, and then a machine cuts them off. Well, they've sold these tapes to different people, and they've got pieces of this tape left, like maybe 20 parts or 50 parts or 100 parts. So what they do is they just cut the tape off and they give you a piece of it. So the parts are connected to the tape so that they are easily rolled up and shipped and stored, but it's still called a cut tape because they took this long tape that had hundreds of parts, thousands, maybe tens of thousands of parts, usually thousands of parts, and then they cut just pieces of the tape off and they give it to you. All right, that's called cut tape. Tape and reel, same thing. This is just a different way. Typically, this is surface mount parts. There's a reel, and it's like a movie reel, and the parts are so small they're on this reel, and they're in little plastic enclosures on this reel. And again, that would be a kind of a whole box of them. So you could either buy a whole tape, or you could buy a whole reel, but we're not going to do that. So typically we want just bulk or cut tape. All right, so we're just going to put bulk and cut tape for our search here. Let's apply the filters. We don't care who's making it, but right now one of my favorite companies is Fairchild, let's say. So I like Fairchild stuff, and I like Vishay stuff for analog. Okay, apply filters, and now we've got 5 different selections here. All right, and we could then sort on different things. So let's sort on increasing price. Right, and we see that the Fairchild has this nice through hole 1N4001, and see how it says discontinued right there? So they probably have an updated part, so let's not use the discontinued part. And so it looks like everything from Fairchild, there's only one and it's discontinued. So let's go to Vishay, and this is not discontinued, 21 cents. And then here's some of the parameters. So it's got a reverse voltage of 50 volts, average rectified current of 1 amp, forward voltage at 1 amp is 1.1 volts. And remember we looked at that data sheet and it had some of that information, and then it says the different kind of packaging and temperatures that these things can take. All right, so let's just click on the part here, and then it comes up with a little bit more detail. And all this is probably overwhelming right now. You're probably thinking, oh wow, this is crazy. You got to look at all this stuff, and yeah, you do. And I mean, it's a process, and you got to learn about it. But once you do, you start to get the hang of it. And it's like picking out anything. It's like buying shoes on Amazon.com or anything else, right? You just get the hang of it. There are just about 100 million different pairs of shoes, right? So there are a lot of shoes. And again, there's more information here. Then we want to drill down and we want to get the data sheet. So we can click here and get the data sheet. All right, and I actually already had a copy of it, but here it is here. All right, and then we just scroll through the data sheet here, and then we see what we see. It's got the parameters and the behavior that we like. We kind of scroll through there. One thing, because all these diodes are roughly the same, 1N4001 all the way up to 4007. We already talked about this in the last lecture, and the only thing different was they all could handle the same current and all these different parameters, but they could withstand larger reverse voltages, and the 4007 up to 1,000 volts, right? And the 4001's up to 50 volts. That's it. All right, let's move on. So let's go back up. Let's go back up to the search here, and let's put another part in. So another one we had was a 1N751. So 1N751. All right, and it's not a capacitor, so it must be this diode here. So let's go here, and we can see it's coming up as this part, and there's these different manufacturers here that supply it. So again, let's pick one that's active. All right. Again, let's pick it's in stock, lead-free, RoHS compliant. And sometimes you got to be careful when you're doing searches on DigiKey and Mouser. The search engine is weird. So here's a little tip for you, for everybody. Say you have 4 constraints, and say there's one part that if you were to enable all 4 constraints, you would see that one part. The interesting thing is, database-wise, if from a programmatical point of view, if you enable these in any order, right, or all of them simultaneously, you should still get that one part. But DigiKey, depending on the order that you do things, it will not show the part. So in other words, don't put too many constraints too quickly. So to put one constraint and see what comes up, then the next one, then the next one, then the next one. If you put too many constraints, sometimes something that should be there actually won't show up. It's a mystery. No one knows why. But trust me, that's exactly what happens. And one of my favorite online blogs, EEV blog, he's even shown this weird behavior online before. So it's very weird, and the DigiKey knows that this happens, and Mouser knows that it happens in a lot of these companies, but it's just their databases are so large, weird things happen. So just go slow with the constraints. Okay, so we've got 2 remaining. If we put all these constraints here, and let's do our apply filters. All right, and it's showing Central Semiconductor Corporation, 43 cents, and so on here. So let's just go ahead and click on this and let's see what this thing is. And sure enough, like I said, it's a Zener diode at 5.1 volts. It can handle 500 milliwatts, all right? And so that means it can handle, if we look here, it can handle 500 milliwatts of power dissipation. So we would see, what's the current that's going through here, and then whatever the voltage drop over the diode, right? And then so current times voltage would be the power. So depending on how much power we want to flow through this diode, we have to look at the power dissipation. Okay, and we read these different parameters like great, and then we go click the data sheet. And again, I believe I had this data sheet. Yeah, I did. So here it is here. And this is not, this company right here, Central Semiconductor, this is not a big one. So you could probably find another larger manufacturer that has the same part if we did a search in a slightly different way. But again, they have all these different components right here. And we can find ours, which is here, this 1N751. And then here is parameters. So it's a Zener diode. And remember, a Zener diode is actually designed to operate in the reverse direction, right? and we put it in the reverse direction and let it break down, and then it maintains a voltage, and that voltage can be used for regulation. So it's like a voltage reference. So we don't use it in the forward direction, we use it in the reverse direction. So in this case, it's a 5.1 volt Zener, and the voltage will vary between 4.8 and 5.35. We'll talk more about Zeners and their math modeling a little bit, but I don't want to get too much into it, and we can look through these parameters here. The Zener impedance is 17 ohms. All right, and at some specific current, the Zener diode will act like 17 ohms of resistance. Okay, great. And then maximum reverse leakage current. All right, and this is being measured in microamperes here. So saying a microampere of current is going to go in the opposite direction when it's just leaking. And then maximum regulator current here is 70 milliamperes. All right, so you don't want to push much more than 70 milliamperes through here. All right, regulator current. All right, so anyway, but it's a Zener. Great. Okay, so let's go. Let's keep looking. What else do we have here? So now we got a Zener. Oh yeah, we had that 1N4739A. What is that? 1N4739A. Okay, and it comes up here 30, and so you can see I've already kind of searched through here. So it's Fairchild, and what is this thing? It's another Zener, except it's a 9.1 volt Zener. So 9.1 volts, and then again, you can read the parameters. We can go look at the data sheet. You know, here's a picture of it, and again, everything with a grain of salt. These pictures may be wrong. There are hundreds of millions of components in these databases. So a lot of times some of the information is incorrect. So go to the data sheet. That's where you tell if something's actually correct. So we go to the data sheet, and again, I already had a copy of it. And here it is. So here's the data sheet right here. And then we scroll through here, and let's take a look here. So what do we got? We got the 4739. So we got 4739, 4739A. So here it is here. And of course, okay, so this is wonderful. Windows highlighting is not doing what it's supposed to do here. But anyway, if we look at 4739, 4739, 4739, 4739, let's go up here, 4739, bear with me. Okay, here it is, 4739A. All right. I did not mean to highlight all of these. I just wanted, you know what? Okay, so now I'm mad. So we're going to actually draw on top of this, 4739A. Okay, there it is. And of course, it's drawing through it. That's no good. So let's draw right under it. Okay. One way or another, we're going to get what we want. Okay, so there we go. That's the part we're looking at. And again, we can look at all these different parameters, right? And maximum current in this one. So this one's interesting. So this one can handle this is reverse current up to 500 milliamperes, and maximum Zener impedance in ohms is 700 ohms. All right, and let's see here. Anything else interesting? So the impedance at the IZ, so whatever IZ is, right? So whatever this current IZ is, this typical Zener current, this will be the resistance, which will be 5 ohms. So you read all these different parameters, and you need to understand and read what they all mean and how they model the device. And we're going to learn a little bit more once we get to modeling these better. But for now, what we need to know is these things will clamp the voltage at a specific voltage, the Zener voltage, and in this case, what is it, 9.1 volts. And we can use that to make a kind of a cheap, poor man's voltage regulator. Okay, so that's the Zener. So we got another Zener there. All right, so let's go back to DigiKey. Oops, let's go back to DigiKey here. Let's change this so we can grab this. All right, and what's our last part? Okay, so we got this last part. We got this ST. This is ST Micro, PS. 2L6. Let's just search for that. All right, and let's search for active. All right, and here are the active parts right here. And so there's quite a few of them here. And this looks like our part right here. So we'll click on it. And what is this? So it's a Schottky 60 volt 2 amp through hole DO-41. That again is the style of this, DO41. It's got a certain geometrical mechanical style. All right, we read through it. It says reverse voltage maximum of 60 volts. So the Schottky diode we use in the normal forward direction that you would use a diode in. So the reverse voltage here means you can reverse the polarity, and it'll take with up to 60 volts before it breaks down and dies. All right, so okay. average rectified current is 2 amps. So this is really cool. Where you're going to use Schottky diodes is in a lot of power systems when you want to steer power, or you want to do what are called wired ORs. And I'm going to show you a little bit of that. But when you want to steer power, so say you have power coming in from a system, and what we don't want to allow is power to go in the opposite direction. So we'll put a Schottky diode on these power rails because we know that the forward voltage is very, very low. So for example, let's take a quick look over at our drawing application. Let's draw something. We're going to actually build these circuits momentarily, but let me just show you something here. So let's say that we have power coming in on this rail, and let's say that this is 12 volts. And let's say that we've got power coming in on this rail. Let's say that this is 5 volts. All right. And let's say that this power is coming, these are coming from wall adapters. All right. Somehow these are coming from wall adapters. Maybe they're DC wall adapters, right? Real high quality DC wall adapters. Now remember, when you have a wall wart, all a wall wart is a transformer, a bridge rectifier, and maybe some capacitors. Let's actually draw. And again, I'm always getting ahead of myself, but I want to show you things because we can just throw them out of our mind. We're going to learn them later, but let me show you this. So here is a wall adapter. So here is AC line voltage right there coming in. So we show this. This is 60 hertz in the United States, and this is 120 volts, and or 110 AC, depending where you read this. All right, so 110 AC, 120 AC, 60 hertz, and we've got a sine wave coming in here. All right, so this comes in, and then we have this block right here, and this is actually a bridge rectifier. So this is a bridge rectifier, and there are 4 diodes in here, and they're in all 4 different directions. And what they do is they take this sine wave, which is going plus to minus, and they make sure that what comes out of here is always plus and minus. So this never changes, all right? So we got plus and minus. So we got our bridge rectifier here. We have our AC. Now we've got our plus and minus. But now what we have is, and one thing that we need to do before we even do this is we need to back up, and then right here, so actually let's back this up. So what we need to do is we've got 120 coming in here, so we need to step this down, right? So let's put a transformer in here. All right, so we'll put our transformer in, and that's the worst coil I've ever seen. So here's our transformer. There we go. All right, so here's our transformer. Much better. All right, and let's step this down. So let's say this is a step down to 12 volts. Let's say this is like 120 volts to 12 volts, step down. Okay, so now we got our transformer here. So X-former. That's better. Now we can come into our bridge rectifier. Bridge rectifier. We've still got AC right here, right? We've still got AC, except it's 12 volts AC. So now we've got our bridge rectifier. All right, and these have 4 diodes all in the right directions, which I'll draw later, and I don't want to get into it right now. But what comes out of here is a plus and a minus, and this will be roughly 12 volts, probably 14 volts, all right? But it's going to be all over the place. What it's going to look like is we've rectified this signal. So let me show you what this looks like. So we had a sine wave that looks like this coming in, and this is called a full wave bridge rectifier. So what we're going to end up with is this. It's going to look like this. So what it does is it takes this second negative cycle and inverts it, and then pops it up here. So we always have positive going. Here's 0 volts. Here's negative. We have always positive going sinusoids. All right, inverted here. All right. But the problem is this is going up and down, up and down, up and down. So now what we do is we put this over some really large bulk capacitors or capacitor. And this is where that big 2200 microfarad might come in handy, electrolytic. Now what we're going to get out here is our 12 volts DC, not regulated, but at least smooth. So now what this giant capacitor does is as this charges up, it charges the capacitor. So as the wave charges up, the voltage increases, the capacitor charges. Then as the load over here, here's the load. whatever that load is, resistor, something, that's what we're powering. It starts pulling power from that, right? It pulls it from the capacitor. So the capacitor basically smooths this voltage and is used as a storage device. So then what this voltage really looks like, if we look at it under the oscilloscope, it's going to look like this. It's going to look like this. So it'll be smooth, and we'll see this up top here, this little ripple right here, and this is ripple. And depending on the size of the capacitor and the load, that's what will define the amplitude of this ripple. But the average of the ripple, if we go here and we kind of go in this middle, right? This is the 12 volts that we're looking for. And then of course, this is 0 volts right here. This is 12 volts right here. And so now we've turned AC 60 hertz. We've stepped it down to 12 volts. We bridge rectified it. We put it through smoothing capacitor, very large. There's some math that we can do to figure out the size of this capacitor and the load and this and that. We'll talk about that later. And then we get our voltage out. So we have 12 volts, but this is not regulated. So as we pull more current and we pull on this system, this voltage is going to move all over the place, right? Now, it's not clean enough for a digital system, all right? That's what a wall wart is. Now, when you have a wall wart that's smaller, typically it'll be a switch mode power supply. It'll actually say DC regulated. That means there are electronics in there, a closed loop regulation system that makes it 5 volts or 12 volts and it's stable. All right. So again, be careful what we're talking about and what you think you're plugging into things. All right. So wall warts are not regulated. All right. So they're not very clean. All right. Let's find a better color. Where is this color? All right. There we go. Okay. So we have our 12 and our 5 volts DC here. And these might be regulated or not regulated, but they're DC. And now this whole conversation, we pivoted over here, but what we were talking about is a Schottky diode. Now, what is that useful for? One use is this. We go here and we put our Schottky diode here, and we can put our little symbol for the Schottky diode. And then we got this guy here, and we put another symbol for our Schottky diode here. Okay, and now let's say that the 12 volt is going to go to the system, all right, and that's going to go do whatever it needs to do, okay. Now, anything that happens downstream over here, current is not going to be able to flow back up here, all right, at least unless a huge voltage is generated, then it would break down this Schottky and then it would get through there. Remember, that was 60 volts with the part we were just looking at, right, 60 volts. But let's say it's less than 60, we should be safe. So this basically protects this end of things. So this diode protects it. So it's protection, that's one thing. Now, but what's another use? Look at this. So we got this 5 volt DC wall supply, but now let's say that we also have 5 volts DC coming from a USB supply. And here it is. Now what we do is we put another Schottky diode right here. And now we can tie them together. And now what we have is we have our 5 volts here, and here's our 12 volts here. We have 5 volts, and this is either going to be, we'll call this wall or USB. All right, now, if you have one of these plugged in, then we're going to get current sourced. Say if we got the wall adapter plugged in, we're going to get current like this, and then to the load, whatever it is. If we got this one plugged in, the USB, then we're going to get current like this, again, to the load. If both of them are plugged in, it'll still work. Nothing bad will happen because current can't flow back here. Now, if we don't have these, so this is basically an ORed power supply. If we don't have these protection diodes in here, what can happen? So let me show you. And we'll just erase a little bit of this here. And actually, I want that. And let's just erase this. Let's get our little eraser here. And we'll just erase this real quick. Okay, and go back and get our little drawing guy, our ballpoint pen. Now, if we just connect these things together like this could be bad. Now, let me show you why. And a lot of people will do this, right? And this is really bad design. So let's say that we don't have the USB cable connected up at all. So there's no cable and we just got the wall adapter. Okay, so that's cool. Current flows, it flows down and goes into our load, we're okay. Where else could current flow? It could flow back this way into the USB, but there's no USB plugged in, so no problem. Okay, now let's unplug the wall adapter. We unplug the wall adapter completely, there's nothing there, and now we're gonna plug the USB in. Again, the USB, it can flow here and it can go down to your load, no problem. Where else can it go? It can go into this wall adapter, right? So let's say that you just unplugged your wall adapter. That's all you did was unplug the wall adapter. Okay, so what did we do? We basically unplugged this. But what do we still have connected here to the wall adapter? Well, we still have this capacitor here. So we're going to basically, this 5 volts DC, we're going to go into this capacitor. Then we're going to get into this bridge rectifier, all right? And then to this transformer. Now, first we have DC. So the transformers, we can think of that as out of the situation. We have this bridge rectifier, which the question is there a path for current back through this bridge rectifier so that it can get into this coil and maybe cause some damage? All right. The answer is probably no, because the way the bridge rectifier is set up. All right. So you're probably safe, but you're still energizing the circuit. You're charging this capacitor right here at very least, right? And so that's not a good thing, right? That's an unexpected side effect, right? It may be okay, but still it's not a good thing. So you want to be careful of that. So again, that's where the damage can happen. Now, what's the worst case scenario that can happen? Well, the worst case is both of these things get plugged in. All right, so now what happens is this. Electronics, in electronics, there's this whole concept of superposition. And what it means is, it's just like if you have two sounds. They superimpose, right, in space. So if you make a sound, ah, and you make another sound, oh, those two sounds mix and the waves mix in space. Electronic circuits are the same way. We can look at a circuit response by taking one signal and putting it into the circuit, then turn that signal off, put another signal into the circuit, look at its response, and if we're talking about linear circuits that are time invariant, we can then say that the output with both of those signals would be just the sum of those two individual responses. So in other words, even though both of these things work separately, what's happening here is when we connect this whole thing together, we have to consider what are the responses to each of these different systems. So we got them both plugged in. So now the USB can go and current can flow back into the wall circuit here. And the wall circuit can flow back into the USB circuit, which we have no idea what that looks like, right? We have no idea what is going on in that end. At the end of the day, what could potentially happen is you've got these two different 5-volt sources here. One of them could be a higher voltage and a lower impedance, or a lower voltage and a higher impedance. Either way, what can happen is current can get driven back through one of these lines in the wrong direction. And if that current is too high, it will damage the components. That's why when you want to tie power systems together, you can use FETs, MOSFETs, or transistors. You could steer the current, or you can use Schottky diodes, all right, and they protect it. So we throw the Schottky diodes in here, and we'll put these babies back in. So we put these Schottky diodes back in here. And now we have a modicum of protection because now we know currents can't flow in the opposite direction. So that is a really good use for Schottky diodes, and they have a very low forward voltage, usually 0.2 to 0.3 volts or 200 to 300 millivolts. So even though we have 5 volts here, right, and say it was 5 volts regulated, when we push it through this diode, we're going to lose a little bit of that voltage. Maybe we're going to drop it down to 4.8, maybe we're going to drop it down to 4.9, and the same thing on the USB. So we're going to have a little bit of loss. So if we really need 5 volts here, right, dead to rights 5 volts, then we better make sure that we're up a little bit higher over here. Maybe we're at 5.2, right? And then this would drop it down to 5 volts. What we really want to do is something a little bit different. We want to regulate the power on our side of the system so we have absolute control of it. So after we've mixed the power together and we brought the power in, say at this point, we know that we have about 5 volts, but we want exactly 5 volts. This is a precision system. So one way is then to take this and we would put this through a regulation block, and we would boost it up or buck it down and make sure it's exactly 5.000 volts. All right, so each one of these becomes a power source that's about 5 volts. It's safe. It comes in from 2 different sources. We diode protect them. Then we have this power here, and maybe it's between 4.8 and 5.2 after all the funny business with the diodes and the wall adapter and the USB. So we're gonna have to do something to that because it's just not accurate enough, and we have to then use more regulation. That's a G. And get this to exactly 5 volts. And this is just power supply design. All right. Okay. So now let's go ahead and let's get to, now that we've kind of gone through these components, let's go back here. We've gone through enough of these components, and let's look at the data sheet here, in which I already had this as well, this power Schottky. There it is there. All right, and we'll zoom in a little bit, and we'll look through it here, and it says, so the forward average, so this is IF, I forward, average, AV is average. And again, no one remembers what all these symbols mean. You have got to read these things, and depending on the data sheet, there may be more or less, and there's usually a key, or the manufacturer has a key for all these different symbols. And many different companies use a lot of these different data sheet symbols, but no one can remember them all. It's impossible. All right, so but IF is current in the forward direction, average is 2 amps, so this can take 2 amps of current. This is reverse, average is 60, reverse voltage is 60 volts it can take. And then these are thermal values here, so we're not going to talk about that, but this is how hot this thing can get before this thing overheats. And then VF is the forward voltage max, which is 0.55. So at a glance, those are those values. Then you kind of look through here, the data sheet, and you kind of see where are you going to operate this thing. So we're going to operate this thing, wow, maybe not at 2 amps, maybe not at 4 amps, maybe much, much less. So we can see that at 2 amps, it's 0.51 volts. It's going to drop in the forward direction at 125 degrees Celsius. We're not going to run it that hot. We're going to run it at 25 degrees Celsius, which is like room temperature, right? And we're not going to run it at 2 amps. So the question is there a chart that can give us some information what the forward voltage drop is? There should be, but many times there's not, depending on the manufacturer and how much work they did on the data sheet. Here's where we go looking through these data sheets. Now, I can tell you right now, we might get lucky here. So let's see. So here are our charts, and I'm going to zoom in a little bit here. Okay, and again, this is a long discussion. We don't want to talk too much about this. So average forward current, ambient temperature, normalized avalanche power. No, we don't want to know that. We don't want to know this. Okay, so those were no help. Non-repetitive, non-repetitive surge, no. Relative invariant thermal, no. Okay, nope, this is no good either. So again, almost useless. Okay, here we go. Let's see here. Forward voltage drop versus forward current. Aha, finally, this is what we want. Okay, so we zoom in here. Let's take a look at this. Forward voltage drop versus forward current. So we want to know, depending on how much current we pull through this diode, what is the voltage drop? Because we're only going to put maybe 20 or 30 or 50 milliamps in the little circuits we're going to make. So here's the current, here's the voltage drop here, and then here's the current on the vertical axis in amperes, and this is in volts. So we're saying we're going to pull not amps, right? Not amps. We're going to pull milliamps. So way down on this teeny tiny part of this little curve, and we can see we're probably going to be dealing in the 0.2 volt, 0.3 volt range. And then again, here are these curves for different temperatures. So we're expecting about 0.2, 0.3 volts to drop over this diode because we're only going to be putting a little bit of current through here. Okay, and then that's it. So this is the actual chart that we would look at to do that. So again, you got to go through these data sheets. You got to kind of try and understand what these things are. Google the different, if something doesn't make sense, Google it and say, you might say VFM for diode data sheet. And, sooner or later you'll see what it is if you can't, if there's no key. All right. Okay. And again, we're not talking about data sheets right now specifically, but data sheets have all of these electrical characteristics. They have all these charts and graphs usually, and then they have all the mechanical, I'm sorry, I'm scrolling fast here. I'm just going to get to this part. These mechanical dimensions, which for the different kinds of footprints, this is an SMB. It's called SMB is one of the footprints. And then here's an SMA footprint. And this is for your printed circuit design, right? And then here's this DO41 package, which are the ones that we have, all right? So anyway, okay. And then ordering information with these part numbers and so on and so forth. Okay, so now what we'd like to do is finally let's get over here to the bench and let's start putting stuff together. So this is going to be a pretty long lecture. So I think what we're going to do is let's stop here. Let's take a pause, and then we're going to come right back and we're going to jump directly into the hands-on portion here. But we did have to go through these data sheets. We did have to look these parts up, and this is part of the process, and I do this all the time. I sit for sometimes, I'm going to be honest with you, if I'm working on a new project, I might sit 100 hours, 2 weeks, 100 hours. I'll just sit at the computer looking at parts, writing down notes, and just reading data sheets. And then I might have to order the parts and then test the parts, right? And this process is an iterative process, and it's a very slow process until you have the parts that you like. So that's why as you design and learn electronics, you kind of find your parts that you like and you stick with them. This is good and bad. The reason it's bad is what you'll find on internet is someone will use a part and it's probably not the part they should have used. It's not new, it's not efficient, it's not effective, it's not low power, it's not cost effective. I could go on and on. But they found some circuit that had that part. And I'm going to give you an example. There's a regulator, a voltage regulator called the 7805, all right? And this is a very old regulator, maybe even from the 60s, definitely from the 70s. And I've used them many times before in the 80s, all right? And if I want to build a retro computer, I might use a 7805. It's a 5-volt regulator, but it's totally inefficient. It's a linear regulator. It's old. It's terrible. It's just yucky, 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 yucky. A million reasons. But every time you see a power supply, a lot of people will use a 7805 just because it's really an easy example, and that's okay, and I do it too. But if you're going to design something, you need to know something different. So you have to know to go look at all the companies who make voltage regulators and see what stuff they have, and they might have much more efficient and lower cost components. And then you can use one of those. This becomes really important, especially when you're designing a board, so that you're not using really expensive parts. So you might design a board and it's $70 to manufacture, and you're like, I need it to be $7 to manufacture, but you use all these super expensive parts because you copied them from internet designs. So remember, go and do your own research. It's really important, all right? And then also, it's okay to design with kind of generic parts that are your go-to parts, but you want to still go and look at parts that aren't your go-to parts and learn new components, right? So that you can become a better engineer and know what's out there. And then, like I said, there are hundreds of millions of components, hundreds of millions of components. So even if you know tens of thousands of them, you know just a tiny fraction of the components. But if you only know a few of them, you don't know any of them, right? So keep that in mind. Let's stop here, take a pause, take a break. Meet me in the next lecture, and we're going to build some stuff with these diodes, and we're going to have some fun. All right, bye-bye. Okay, welcome back to the next lecture. So we're finally going to actually build stuff with the diodes. I know this has been a kind of a long time coming. We kind of spent a lot of time in lecture. But semiconductor devices, there's a theory, there's so many types of them, and again, like I've been saying, there's countless types of electronic components, and I just wanted you to have some background, a little bit of theory on some of the different versions. So to refresh your memory, we're going to be playing with the silicon rectifier diode, which is the 1N4001. We're going to play with a Zener diode, which I think the one we have is a 1N751. Yeah, which is a 5.1 volt Zener diode. We're going to make a little voltage regulator with it. We're going to play with the ST Micro Schottky diode, which is the STPS 2L60, which is a Schottky diode. I believe it can with 2 amps of forward current or 1 amp. Let's go take a look. The data sheet is still here, and let's see where that data sheet was. Power Schottky, I believe this is it. Yep. And let's take a quick look. And yeah, 2 amps. So 2 amps of forward current that it can handle. and also, again, Wikipedia is good for quick and dirty kind of overview of things. I want you to read through our notes from the chapter excerpts, but you can always go to Wikipedia if you kind of want to do a quick and dirty. And one thing about Wikipedia, sometimes there's some nice photographs, which are nice, and then I believe this has some nice curves and some animations. that you can take a look at. So anyway, doesn't hurt. And then of course all the modeling equations. All right. So anyway, let's get right to this. So we're going to jump over to the lab bench and we're going to start playing with this. So let's start off with the 1N4001 rectifier diode and let's build a circuit with it. All right, so let's take a quick look at what that looks like and then let's come back and we're going to draw something. We're going to actually draw a circuit and then we're going to implement it. Okay, so I'll meet you over at the bench. Okay, so we're here at the bench camera and we've got our diodes and we got all of our parts here. So we got a few resistors, we got an LED, we got some hookup wires, this bridge rectifier, we don't really need to mess with that right now. And we've got our different diodes here. So let's pick out a 1N4001. So let me see if I can find one here. And here is a 1N4006. So we'll put that up there. Get that out of the way, and 1N4001. All right, so here's our 1N4001. So let's go ahead and let's zoom in a little bit. Get semi-close so you can kind of see what we're doing here. All right, so you can follow along. All right, so we've got our diode. All right, and for the first circuit, let's do this. Why don't we, let's take our diode, and we're going to take a voltage source. So we'll take our power supply, our bench power supply, and if you remember that, let's take a look at that. So here is our bench power supply right there. And right now I've got it set for 12 volts, but we can adjust whatever that is. So there's a bench power supply. We're going to use that as a power supply. All right, and we're going to bring that power in right here on these two rails. Okay, so let's start with that. And we'll go ahead and put the black lead to the bottom, which is the negative rail. And again, it doesn't really matter. The wires don't know what color they are, but we want to keep conventions here. Okay, so we got that hooked up, and let's get the wires out of the way a little bit. When you're doing electronics, the neater you can be, the better. And we make sure our power supply is off. It is. The output is off. Okay, so the power of the power supply is on, but the output is off, so there's no power flowing here. All right. Okay, so we've got our diode. So let's see, what can we do here to kind of figure out, is this thing doing what it's supposed to do? So we want to do an experiment just with the diode and see what's happening. So why don't we take a diode, and we already kind of talked about the whole computation of current. We assume the diode's either conducting or not conducting, and then we make that assumption, do the calculation. If we get a contradiction, we know we did something wrong. Anyway, so let's go ahead and we're going to take our diode and let's take a look at our resistors here and see what we have. And again, you can practice your color code here. So I'm going to grab a few of these resistors and kind of put them here. And so let's see. So I've got a 220, I've got a 330, I've got a 1K and a 100, another 100, another 100. All right, so let's take a quick look at the zoomed in camera here. All right, and start, it's not going to hurt to start memorizing these things. All right, so there's brown, black, brown, that's 100 ohms, and there's gold, gold at the end, so that's 5%. So brown, black, brown, there's a 100 ohm, all right, and then here is, what's this? This is orange, orange, brown, so this is 330 ohm, all right, and what's this one? This is red, red, brown, this is 220 ohm, and again, you can check these with your multimeter, all right, doesn't hurt. Double, triple, quadruple check everything. And then what's this one right here? This is brown, black, red. So this is a 1K ohm. So this is 1, 0, and then times 100. So we've got 1K here. All right. Okay. So we've got our resistors that we can play with. We've got our diode. All right. Okay, so let's do a circuit where we basically have a current coming in. We'll put it through a resistor, we'll put it through the diode, and then we'll put it to ground, all right? And so we should get a current in the circuit, which is limited by the resistor, and we should get a forward voltage drop over the diode of about 0.6 to 0.7 volts. So let's start there, all right? So that's what we're going to do. All right, so let's bend this up. Now again, remember I've talked about how some of these parts will not fit into these solderless breadboards without damaging these holes. All right, so these posts right here, these are pretty thick posts. All right, the gauge of this is quite large compared to say this hookup wire. So the hookup wire and I don't know the gauge offhand. I believe the hookup wire is 26 gauge, and gauge is a measurement of diameter. The lower the number, the larger the diameter. And if this is 26 gauge, then this is probably 24 gauge. All right, so it's definitely large enough where it's going to be a problem. In fact, I believe this is probably 22 gauge, and this hookup wire is probably 24 gauge. All right. In any event, if you have trouble putting components in here, what you're going to want to do is file these things down. So you can get a file, and you can just use sandpaper or a file. If you use sandpaper, so here's some files. These are diamond coated files. So diamond, of course, one of the hardest substances known. So get one of our diamond files, and what you can do is you can just simply file the part down a little bit and kind of round it and take off some of those sharp edges. All right. If you use sandpaper, it'll work, but what you'll tend to do is kind of rip through the sandpaper with this. Now, what I'm doing here is I'm taking off some of this material. It's getting on this, and I'm getting particles everywhere, right? So this is a bad idea. So if you really want to do this, you should do this on a piece of paper or a cloth, because you don't want little pieces of metal all over your electronics that can cause shorts, right? So I just did that purposely. I wanted to show you, don't do that, all right? So what I'm really going to do here is I'm going to go get my cloth, and so I've got just a cloth, little towel, and I've just typically put that towel down over to the right here. So it's over here, and I'm just going to do this off camera real quick. All right, and then then another thing that I want you guys to get familiar with is rubbing alcohol, and this is 91% isopropyl alcohol. And if you can find 90%, that's great. 70% will do, but you want to have it mostly alcohol. So this is just standard isopropyl alcohol. You want to use isopropyl alcohol, right? Take that alcohol and then go ahead and pour a little bit of it on your cloth so that you have that. And then as you clean your component, or you scrape it, or you do whatever, and I'm just going to do this on camera just for a second. All right, two things. One, this is going to get dirty, and you're going to have to wash this, and I suggest you don't wash it with clothes. Wash it by itself. But I do that, and then I can kind of clean this right here. See that? I make that nice and clean. All right, so let's just do this. And again, you know, electrical engineering is mechanical engineering, right? You got to do all these things. You got to do mechanical, you got to do electrical. You're going to have to do software when you get to firmware, right? You got to do design, you got to be artistic. So it's all of these things, right? So you have to, you know, you got to get good with using your hands. And if you're a software person, this may be a whole new experience for you. All right? So we take a look at that, and then what I'm going to do is I'm going to show you this on the zoomed camera. So let's go over to the zoom camera here. And you can see how that is now a little bit rounded and less flat and blunted. Okay, all right, so that's the process. So now you know. So now you can do it. All right, and you can get some files from a hardware store, or you can get them off of Amazon. And with tools, a piece of advice, you get what you pay for. If you buy Chinese tools, they're Chinese quality, unless they're made out of, you know, hardened steel and all that, and even then you're not really sure. So if you're going to buy tools, you want to buy them once in your lifetime, so it does pay to get high quality tools from a high quality vendor, and you can do your Googling and figure that out. All right, let's build our circuit. So we want power coming in here. We want to go through our diode or resistor and then to ground. So let's bring a resistor in here. Let's start off with a 1K, and we're going to put it from the power rail into one of the columns there. We're going to take our 1N4001 diode, and then to the right, you can see it, hopefully, is the cathode. So that marks the cathode. So we want the anode on the other side, because we're going to want conventional current to flow from left to right. Okay, great. So we're going to go ahead and we're going to put this just like this. All right. So that fit in there after we did the sanding. Now, let's go ahead and let's take a wire and let's bring this to ground. All right. So just take a wire here. And again, you're going to notice I'm very meticulous and particular about things, and you should be too when you're doing electronics. You see me straightening things out. I'll kind of, you know, bend them, pre-bend them, and, you know, just make it neat. Just make it neat. You don't have to make this stuff a complete disaster and mess, which I've seen too many people do. All right, so we're going to get that in there. And again, if I was doing this, I would make these completely flat. I would literally cut them all to size if I had to, if I was going to leave something on here to be as a functional prototype, because otherwise you're going to get noise and all kinds of things are going to go on. And I would use a solderless breadboard that had metal under it so that we had something for all of the field lines to terminate in, all right? But right now we're okay, we're just going to do this. Okay, so here's our circuit. So we got a resistor, we got a diode, we got a piece of wire going to ground, completing the circuit. Let's go draw this on the computer and let's make sure that we're talking about the same thing, all right? Okay, so we're back here on the computer. So let's go ahead and get our drawing application up and let's draw this circuit. So let's go ahead and let's do draw it in orange maybe. So here we come. So we're going to call this our 12 volt power supply. We'll call this power supply, and it could be 12 volt. Maybe we're going to do, you know, 5 to 12 volt. It could be anything. It's a variable. All right, and that's coming in. And then in our particular circuit here, we've got a resistor. All right, and then we've got our diode, which is a standard silicon rectifier, and then we're going down to ground. This is our entire circuit. So we're going to call this, let's call this R1. Right now, I believe I put a 1K in there. All right, so this is 1K ohm, but it could be anything. And then we've got our, this is plus and this is minus. This is the cathode side right here, cathode. And this is the anode side. So we're trying to learn those and remember those. All right, and current is going to flow, conventional current is going to flow through here to the right. So let's put current here as yellow. So current is going to go like this and then down to ground. All right, and let's just call that, we'll just call that I1 since we've got this R1 here. Now remember, real quick, we have V equals I times R if we want to compute I. So in this case, we want to compute I1. It's going to be V, which is, let's call it 12 volts, over our 1K resistor, our 1K. And if you do that, get your calculator. I always want that calculator out. Get that calculator out. 12 divided by 1 x3, all right, and do the math, is 12 milliamps. All right, and so what you're going to start to get the hang of here, 12 milliamps, is volts divided by k ohms equals milliamps, right? So if you know you're dividing volts by k ohms, you're always going to get milliamps, right? But do it on the calculator, make sure. All right, we got 12 milliamps, so we know the current's going to be limited to about 12 milliamps. We could go look in the charts of what the voltage drop over the diode is, but we're going to say that it's going to be approximately 0.7 volts. All right, so we run this circuit. We're expecting about 0.7 volts over the diode. We're going to put in 12 volts, so that means over this resistor, we're expecting about, and again, this is approximate, 11.3 volts. All right, so those are the things that we're expecting. Let's go back to the bench and let's see what happens. We got everything out here. Okay, we're going to put our meter here. We're going to put it into voltage mode. And let's see, I'm going to have to put the camera up just a little bit so we can see what's going on. All right. All right, and we're going to go ahead and turn this whole thing on. So I'm going to turn the power on. So the 12 volts, there we go. Nothing exploded, good news. Okay, so now let's start measuring some things. So let's measure the voltage drop over the diode itself, all right? So we're looking for about 0.6, 0.7 volts. I can measure it in either direction, but current is flowing from left to right here, from the anode to the cathode, conventional current. So if I go plus to minus, we should get a positive number over here, all right? So I'm just going to touch it carefully. And sure enough, we have 0.67 volts. This is exactly what we expect. Therefore, if we have 12 volts coming in, so here's what we have coming in. I'm going to go over the power rails. We've got 12 volts, all right? And so over the resistor, we should have a little bit over 11.3 volts. And I'm going to go to the resistor now. And sure enough, I have 11.3 and some change, and it all adds up to 12, all right? So our diode is working. Now, let's play some games with it. Let's use the diode for what a diode should be used for. Let's flip around the voltage here. We're going to flip it around, and this diode should not conduct. So let's see what happens. So I'm going to unplug these. I'm going to put ground up here. I'm going to put positive down here. All right, so here's where, this is not a trick question. I never ask trick questions, ever, ever, ever. I only ask questions that have tricky answers. but I never try to trick people, but I want to get people to think about things, and sometimes things are non-obvious. All right, so whenever you have a load, so we've got power and this is a load, all right, all these little components. Whatever this load is doing, this voltage here should always be whatever the voltage is, right? Unless the regulation can't be maintained by the power supply. In other words, I don't care what's going on in the circuit. If this is a good power supply, it should still read 12 volts. So does it read 12 volts? So let's first see that. And it does, minus 12 volts, which as it should, because we've got these reversed, okay? So we're reverse biasing this diode. So now the question is, what is the voltage drop over the resistor? What is the voltage drop over the resistor? All right, so I want you to think about that. And the first question I'm going to ask you, is there any current flowing? There should be no current flowing if this diode is not working. So if there's no current flowing, then let's see what the voltage drop is over this resistor. Either way, it doesn't matter which way you measure it. Let's take a look. 0 volts. There's 0 volts over this resistor, right? Because there's no current flowing. If there's current flowing, there'd be a voltage drop. So there's 0 volts over the resistor, all right? Now, let's see what the voltage drop is over this diode here. So let's go to the diode. All right. And now there's 12 volts over this diode. So this is an interesting situation. So there's no current flowing. All right, there's no current flowing here, and I'm going to show you, we're going to measure the current. There's no current flowing. So if there's no current flowing, then there's no voltage drop over the resistor, but we see there's a voltage drop over the diode. Now the reason why is because since there's no current flowing, right, in essence, the resistor is, its impedance becomes irrelevant since there's no current flowing, and what we're sensing when we go over the diode is we're just basically touching the power rails again. So the diode is basically touching the power rails because there's no voltage drop over the resistor because there's no current flowing because the diode is reverse biased. It's not forward biased. It's not working. Let me prove it to you. Okay, so we measured the voltage over the resistor, right? And it's 0, 4 zeros, right, to the 10,000th place. But maybe there's a little bit of current here. So let's go and let's measure what this current is. So we're going to open the circuit up. We're going to put the meter into milliamp microamp mode. So I'm going to move the probe down at the bottom. I'm going to put it down into microamps. All right, so the meter's in microamps now. Okay, now we need to put something in here, so we got to go in line. So we're going to go like this, and then we're going to put our wire here. We got to complete the circuit, so we got to go in line in the circuit when we're measuring current, right? Okay, so this is in line in the circuit. Now, when I put the probes back in, we're going to complete the circuit. So we're going to put these probes in, and we should turn the power off, but we're just going to throw caution to the wind here. Okay, and there we go. I've completed the circuit. I'm measuring nothing. I'm measuring no microamps at all. So let's change the range a little bit. And we're on AC here. We don't want to be on AC, so let's fix that. Okay, we're on DC microamps, and now I'm going to change the range. And notice we can get maybe we can get this thing to say there's a little teeny tiny bit, a 0.1 microamp, so 0.1 of a millionth of an amp. In other words, there's a teeny tiny bit of current when this thing is reverse biased. That's leakage current. So even when you reverse bias this diode, there's a teeny tiny bit of current that flows. But in the forward direction, we can get up to 2 amps to flow, right? We can get 2 amps of current. Now, let's go ahead and flip this back around. So let's flip this back around, and let's put the system into milliamps. We're going to flip the power supply back around. We know this thing is going to flow. We calculated about, I think, what, 12 milliamps of current should flow, roughly. All right, and look at our meter. 11.3. Why is it a little bit less? Because the diode is some resistance. It has some resistance. We did the calculation just with the resistor. Now, if we change this resistor, if we make this resistor lower, it's 1K. Let's take this resistor and let's make it 10 times smaller. So roughly 10 times as much current should flow, right? It's a linear system. Okay, so for this, I'm going to turn the power off. All right, we're going to find our 100 ohm resistor. What's 100? Brown, black, brown. We're going to pull out the 1K resistor. We're going to put in our 100 ohm resistor. And you know, this is a simple circuit, but a lot of things are being illustrated here, and this is why you got to take your time and build this stuff so you have a good feel for it. You know, if you haven't done something, you don't have a feel for it. You know, I've never driven a tank, and if I got in a tank, I'd probably press the gas too hard, right, and the brake too hard, and I'd oversteer because I have no feel for it. It's a big mass to move around. And same thing with these little teeny tiny electronics. You have no feel for it. So we got to play with things, even the simplest circuits, so we get fundamentals in our brain. Okay, I'm going to turn the power supply on. We're expecting what? 100 milliamps, right? About 10 times what we had before, and there you go. So now we've got our resistor in there. If we just do the math, we do 12 volts divided by the 100, that's 120 milliamps. But because the diode is in here, this has some resistance, it has some impedance, so it's dropping a little bit of voltage, which is decreasing the overall current in the circuit, right? So there's more impedance, so we have a little bit less current. And there you go. And our meter is showing 106 milliamps. Now, if we put our finger on this resistor, right, that is hot, okay? That actually burns my finger. Okay, so it's burning my finger. Let's put another meter and let's see what the voltage is on there. All right, so this has got 106 milliamps, so we're pumping 106 milliamps through the circuit, or 106 milliamps is flowing through the circuit as a result of the voltage. All right, so I'm going to put another meter here. And let's see, can I get these both on screen at the same time? I think so, I think so. All right, we'll just zoom back a little bit. Zoom back a little bit. Okay, let the camera stabilize. All right, all right. Okay, so now I'm going to get the second meter out, and I'm going to go measure the voltage over that resistor, okay, the voltage over the resistor. Now, what do we expect it to be? About 11.3 volts, right? So we've got it on voltage. I got this meter on voltage, and I'm going to go measure this. Okay, so I'm going to measure it, get my hands in here, put the polarity right. Doesn't matter, but we can always reverse the sign, but might as well do things correctly. All right, and what do you see? 10.43 volts, okay? So now let's see what's dropping over this diode. Okay, moving my hand, 0.76. So see the voltage went up. So because there's more current flowing through the diode, the dynamic resistance is increased and the voltage drop over it is higher, and that's going to keep happening. The more current, the higher it's going to get. Let's go back to our resistor here though. All right. Our resistor has 10.5 volts dropping over it. Let's get our calculator. 10.5 volts, and we got 107 milliamps. 10.5 times 107 milliamps equals 10.5 times 107 milliamps equals 1.1 watt. So that resistor is dissipating 1.1 watt. I can tell you right now this is a 1/4 watt resistor, and that's why it is burning hot. It is burning hot, and it might start smoking in a minute. So we're putting way too much current, but notice what's happening. It's tolerating it. Why? Because it's in open air, right? It's connected to some metal here, which is also dissipating heat, giving a path for heat to flow. So this is an important little thing. Heat flow, let's talk about that for a moment. Okay, so we're not going to deal with this directly, and probably not do a lecture on it on thermal heat flow and heat circuits and doing the calculations. But one of the things that's important with electronic devices is how much power that they can dissipate. And if we put too much power or too much current through them, they won't be able to dissipate that power. And you know, I'm teaching circuit analysis right now, and thermal circuit analysis is analogous to circuit analysis, where you actually have thermal impedance and you can have heat flow and things that act like capacitors. So it's really interesting. And some of these values in the data sheets talk about or are used to do heat computation. So you can compute how big of a heat sink do you need to remove the heat fast enough and all that. All I want you to do is make sure that when you do designs, try and rough out what the current is or the voltage is, voltage and current, compute the power that the device is going to have to dissipate, and make sure that the device can dissipate at least twice that amount of power. That's a rule of thumb. All right, the other thing is these devices are connected to metal. Metal conductors, metal this, metal that. This is connected to this big piece of metal. There's these metal conductors here for the power rails, and then there's metal in these sockets. So that heat is flowing from the resistor body down through the metal, and it's dissipating, and these are acting like heat sinks. So if I were to touch these, so this is actually warm. The top rail is quite warm, and I can feel the heat radiating off the resistor right now. It's like cooking. All right. And so anyway, I'm going to turn this power off because I don't want to damage this resistor. All right. So the power's off now, and now that resistor is going to cool down. But again, because we had it kind of heat sinked in this metal, it was able to tolerate it, right? But that's why we want to make sure that we over-design our circuits. Moreover, a lot of things are already what are called derated. And so when they put the thermal rating of a component, they actually derate it so that you actually get more. So if they say it's 1 watt, it's probably 1.3 watts it could actually withstand. So they derate it to 1 watt so that, because they know you're going to probably go over it. So it's just another safety precaution that manufacturers use. Okay, let's keep going. All right, so all right, we measured the voltage. Now let's do something else. Let's put this meter away here. All right, I'm going to put this one away. Okay, so let's bring our circuit back into view here. Okay, so we got our circuit. Let's zoom back in a little bit so we can see what's going on. Okay. All right, so what do we want to do next? Let's do something else fun. Okay, so we got our diode up here. So that's dropping 0.6, 0.7 volts, and it's allowing current to only flow in one direction, all right? So what I'm going to do now is I'm going to actually remove this resistor here, and this thing is hot. It's definitely hot. Ouch. All right, so what I'm going to do is I'm going to grab it with some pliers. It's actually that hot. It is a little bit toasty. Put it in my hand. And it's definitely not scorched. So see what I'm doing here? I'm just kind of dissipating the heat. Okay, it's good. All right, now what I'm going to do is I'm going to leave this diode in our circuit. So I'm going to take it directly from the rail, and I'm going to take this and try and put it in here. So we know directly coming from the power rail, we have this silicon diode, which is going to drop 0.7 volts. Okay. Now let's go ahead and let's take our Schottky diode, all right? And what we're going to do is, and we're just, we're just having fun. We're just messing around. We're just, and this is what you do. You got to mess around. You got to play with this. All right, let's take this. Here's our Schottky diode, the ST. What was the number? STPS2L60 and whatever else. All right, and okay. So now we're going to put this in the proper direction. So we're going to put anode to the left, cathode to the right. And maybe we can zoom in just a little bit for you. Okay, and we're going to hook this up, and I'm wiggling. Okay, another little trick. Again, you're going to feel this stuff when you do it, but when you start messing with the Sawdust breadboard, when you push something in, it's just not going to go. So you got to wiggle it, but hold things firmly. And another thing, if you've never used tools before, and I've seen a lot of 20-something guys that have never held a wrench in their lives, a screwdriver, never taken a tire off a car. And the first time they do it, they don't even know how much force to put, and what they end up doing is slipping and ripping off, their knuckles. So remember, whenever you're pushing anything, whenever you're doing anything mechanical, and for those of you who know how to do this, just ignore me, but if you're not a person that's mechanically inclined, when you apply force to stuff like this, anticipate it slipping. And then in your mind, be like, if this is going to slip, I don't want to push my hand through something. There's 2 posts here. I can impale myself. I can hurt myself. So if something slips, catch yourself. So always be anticipating it's going to give, it's going to break, right? Don't push all the way through it, all right? That'll save you some pierced fingers. Okay, so we got our rectifier diode up here, which we're not caring too much about. We know that's going to, once the circuit starts conducting, it's going to drop 0.7 volts. We got a wire here. We got a Schottky diode here. All right, and let's go ahead and let's put a resistor back in the circuit, and let's limit the current. So now let's put a 330. Okay, so that's orange, brown. Here's our orange, brown. And you know what? I'm going to put everything kind of sideways here for you so you can see it this time. All right, and then I'm going to run this down to ground. Let's find a nice wire to run it down to ground. That'll fit. Let's see. Okay, so here's something right here. Again, meticulous, clean things up, keep it clean, you know, so that these wires don't get all bent up and messed up. And then I'm just going to kind of bend it with my fingers. All right, now look at that shape I just made, right? And so it's going to go here and it's going to go to ground. Here and ground. Nice, nice. Make sure it's in there. Okay, I'm happy with that. That looks good. Okay, so now we've got a complete circuit. Let's take a quick look at this back on the computer and make sure we know what we're talking about. Okay, so we just created another circuit. So what does the circuit look like? Again, we've got our power supply. So now let's kind of do this, and we'll kind of do this, and we're coming in here, and we've got our silicon rectifier diode. All right, that's our 1N, our 1N4001. Right, this is the plus side, this is the minus side. Now what do we have? We've got another diode, but this time we've got a Schottky diode. And here's kind of the symbol for that. Again, this is plus to the minus, plus and minus side. We know that this is going to drop approximately 0.6 to 0.7 volts, roughly. This is going to drop 0.2 to 0.3 volts at the currents we're going to mess with, up to like 0.5 volts if we really put an amp through it, but at the currents we're going to mess with. And then we've got a resistor. And then we're coming back down here and we're returning back to the power supply. All right, so this is plus, this is minus, this is VS, our source. All right, and I'm just going to try and, I try and draw things in different ways. And then this is what we're calling ground. We're going to call this R1. Right now, I think we just put a 330 ohm resistor in there. Right, so let's do a rough calculation. So let's say that we put this at 12 volts. Again, we're leaving it at 12 volts. So we're going to drop 0.7 over this diode here. We're going to drop 0.3 over this. So what is going to be the current in here? So let's give it a whirl. So voltage over R1. So, and let's pick another color. So voltage R1 equals what? 12 minus the drop of the first diode. And let's go ahead, let's give this a name. We're going to call this D1. We're going to call this D2. Drop of D1 minus the drop of D2, which is equal to 12 minus, we're going to say it's 0.7 minus, and we're going to say it's, just go high, 0.3, all right? All right, so we got 12 minus 0.7, so that's 11.3, right? 11.3 minus 0.3, so we got 11 volts. 11 volts, so we got 11 volts. So right here at this node, we expect to have 11 volts. So 11 volts is going to drop plus to minus. So let's compute what's going on over here. So remember, V equals I times R. That's Ohm's law. So the current in the circuit coming through here, we call that, if we want to call that I, let's just call that I, or we could call it IR1, but it's the I, same I in the whole circuit, the same currents flowing in, flowing out. So we're just going to call that I. So I equals what? It equals V. What's our V here? 11 volts. Over R, which is 330 ohms. Let's get our calculator out. Get our calculator out here. So I got the calculator, 11 divided by 330 equals, and 33 milliamperes, right? 33 milliamperes. 33.3. Call it 33. 33 milliamperes. All right, so we got 33 milliamperes. So this is kind of what we're expecting. All right, let's go back to the circuit. Let's see what happens. All right, so we're good to go. We got our circuit. Let's go ahead and turn the power on. Nothing exploded. That's always positive. Let's start measuring voltages. We'll zoom out a little bit. Get things in here. All right, see this big meter. All right, and let's put this meter back into voltage mode. Okay, and we'll move its range just a little bit to give us some decimal places there. All right. Okay. Okay, so let's measure the silicon rectifier diode. So we're thinking what? We're thinking about 0.7 volts, right? The second it's on, it's going to hang at about 0.6, 0.7. It's going to increase as the current increases, but just slightly. 0.725 volts. Okay, looks good. Now the Schottky diode, we're expecting 0.2 or 0.3 when this thing is on. That's the whole point of it. And what do we got? 0.26. Wow, things are working. Now, whatever 12 minus those two is going to end up over this resistor. Let's measure that. 10.9 volts. All right, and if you look at our calculation, we said it was going to be 11 volts. So wow, pretty accurate. And the current should be about 33 milliamperes, right? So if we want to measure the current, we think it's about 33 milliamperes. So we could open this up and put the meter right inside there and measure what the current is if we want to, right? But let's just leave that alone right now. We're not even going to do that. What we do know is that at this point right here in ground, we have about 11 volts. So we got these diodes working for us. We got about 11 volts right here, and we've got about 33 milliamperes. Let's go put a light emitting diode in here now. So let's just add a light emitting diode. All right, so I'm going to add this green light emitting diode. And remember, the cathode is the long bar and the anode is the short one. Let's go to the zoom camera. Let's take a look at that. All right, so the cathode, and where's a pointer when you need one? This is the cathode. That's negative, and then the anode's the other side. And then remember, there's a flat spot. And let's see if I can show you that. Yeah, there's the flat spot. You can see the flat spot right there. Flat spot, and that's usually the cathode. Not always, and I've even seen LEDs where the large side is not the cathode, it's reversed, so you always got to check it or look at the manufacturer, okay? Don't make assumptions. You can make educated guesses, but check things out so you don't blow things up. All right, so now we've got this current limited to 33 milliamperes. We've got 11 volts, so what's going to happen if we put this diode inside of here, all right? So the diode is going to drop 2.1 to 3 volts, right? Okay. The current's limited to 33, so this LED should survive, right? And then the voltage will drop over the resistor and the circuit will come to equilibrium. So I'm going to turn off the power, all right? I'm going to undo this wire right here. I'm going to put our LED anode to cathode. All right, so the anode's on the left, the cathode's on the right. So all these different kinds of rectifiers are all in the same direction. All right, and now let's get a little longer piece of wire this time. Clean that one up, straighten that one up a little bit. So when you use it again, it's not all jacked up. Okay, got another piece of wire. Let's go ahead and we're going to put this to the cathode. We're going to put it to ground. All right, so now we've got our circuit. So we got silicon rectifier, we got Schottky diode, we got LED, we got a resistor to limit current, and then we got our meter. And let's move this over just a little bit so you can see what's going on. All right, so let's go ahead and let's put turn the 12 volts on, and let's see what happens. And lo and behold, the LED turns on. So the LED is not going to be able to get brighter than 33 milliamperes, right? So we know that. So we know that we're probably safe because this particular LED could probably take 20, 30 milliamperes before it overheats and causes damage. I'm feeling it with my finger. It's not hot. Anything, here's another little tidbit. When you're doing electronics, if it is too hot for your finger to stay on it, if it's uncomfortably hot, it is too hot. I guarantee if you go into most consumer electronics, power supplies, you start putting your fingers on things, and of course don't do this with AC power supplies, do it with like DC, low voltage. But if you start putting your fingers on things, everything is going to be too hot. That's a poorly designed power supply. It should not be uncomfortably hot. It's, you know, warm to maybe hot, but not like, ouch, I got to take my finger off it. I got to do that. This is fine. Okay, so I'm okay, so we're good. Let's see what our voltages are. So should the voltages on the diodes change? No, not really, just a little. Okay, so let's see what happens. So our first silicon rectifier diode, it should be at about 0.7 still. So I'm checking it, 0.71. So it decreased a little. Why? Because less overall current is flowing through the circuit because we added this extra impedance here. Our Schottky diode, that was at about 0.25 before, right? What is it now? 0.25, a little bit less, All right, and our resistor, what's it at now? It's at, let's get a good, okay, let me get it good here. And so, you know, sometimes this is hard to get in here. There we go. It's at 8.6. It was almost at 11, right? But it's at 8.6. Why? Because this LED is going to drop whatever it needs to get forward biased. And what is that? 2.3. All right, so there it is. So we've got three different kinds of diodes here, one light emitting, and they're all doing what they're supposed to do. Let's reverse it real quick. Ready? Will anything work? And the answer for $1 billion? No, it can't. even though there might be a minute amount of leakage current going through here because it's all reverse bias, there's not enough to energize this LED definitely and to get any photons out of it, right? Okay, so let's put that back. Okay, one last little quick thing. Let's measure the current real quick. Let's measure the current real quick. So I'm going to open this up. And I'm going to take my meter. I'm going to put it in milliampere mode. I'm going to put our little adapter that I made here. I'm going to put this in milliampere mode here. Okay, and then I'm going to plug this in, and this will complete the circuit. And what do we got? 25.9, 26. So we went from 33 to 26, and that's what we expect because we added another impedance, this LED. So that's the whole point of current limiting resistors. They give you a top, right, an envelope. You're not going to be able to get current more than that. You're going to definitely get current less than that when you add the actual diodes in, but that's a starting point to limit the current so you don't damage the circuit. Okay, let's do one other fun thing. Let's do this. Let's add the Zener diode. Let's make a 5.1 volt, roughly, power supply. So let's turn the power off. Okay, let's go back to the computer and let's draw something really quick of what we're going to change here, and this is going to be cool. All right, so let's go back. Okay, so let's see if we can undo some of this drawing here. Undo some of this drawing. And good. All right, that's enough, and let's go ahead and erase the rest. All right, so let's see here. We are going to do this. We're going to open this up. We're going to change this. All right, let's get rid of this calculation here. It's no longer accurate. We're going to keep the circuit mostly like this. Now's where the fun part comes. All right, so let's go ahead. Let's get a different color here. All right. Now what we're going to do is we're going to add in the, well, that doesn't make any sense. You see that 0 ohm right there? Let's fix that. Okay. All right, let's go back to the ballpoint pen. All right. We're going to add the Zener diode. All right, and the Zener diode we are going to put in the reverse direction, and it's going to clamp the voltage. That's what Zener diodes do. All right, so we're going to put it in this direction, like this. I know this is kind of weird. And then it's going to go down here. All right, and then we're going to connect that there. We're going to connect that there. Remember, the symbol kind of looks like this. They're kind of these angled ones, whereas the Schottky diode are at 90 degrees. All right, let's for our resistor, let's put that at say 220 ohms. Let's increase the current a little bit. So we're going to decrease that to 220 ohms. So that's going to be brown, black. We'll get to that in a minute. All right, and now what we're going to do is here's our, and this is our 5.1 volt Zener. Now what we're going to do is this 5.1 volts is going to be here. This circuit now, we're going to have 12 volts. It's going to drop. And then what's going to happen is at this point right here, this is going to want to stay at 5.1 volts. So we're going to have some regulation here, Zener regulation. All right, and then we're going to take this and we're going to go through a 330 ohm resistor. Then we're going to go down to our LED, down to ground back here. And there, what's our symbol for the LED like that? And this is the plus, and this is the minus, and this is LED. All right, this is the circuit we're going to make. So what's going to happen here is the stuff over at the left, we're going to get, the Zener diode is going to clamp this at 5.1 volts. Now we've got 5.1 volts. Now we're going to take that 5.1. It's as if it's a whole power supply unto itself, right, on the right side of this barrier, with a 330 ohm, and then we're going to put it through the LED. So 5.1, so we've got V equals I times R. We've got 5.1 volts, so let's compute I. So that's going to be 5.1 volts divided by R, which is 330 ohms. Get our calculator out. Remember that calculator, I want you to have it just constantly. All right, that's going to be 15 milliamps. 15 milliamps and some change. Call it 15 milliamps. All right, lighting that LED. 15 milliamps. Lighting that LED. Okay, that's a horrible 15. All right, 15 milliamps. All right, so this is a circuit that we're going to build. So let's see what happens. Let's go ahead and build it. Okay, so we're back here on the bench. Let's undo some stuff here. Make some room. All right, so you can remember what we're doing here. Let's get this in the middle here. So let's zoom in just a little bit so you can see what I'm doing as I'm doing it. All right, so we've got our 330 ohm there resistor. Let's pull that out. Oh, here's something interesting. So here's our resistor, right? Let's go to the zoom camera. After it cooled down, look at the scorching. It is scorched. It's okay though, it'll work. All right, so here's our 220 ohm. We're going to use this in the first part of the circuit, and this is going to limit what our total Zener current or the current going into the Zener diode is, so we have a little bit more current. All right. Now let's find our Zener, our 751. Here it is right here. Here's a 751. This is a 5.1, and now look at where the bar is. That's the cathode. Now normally we'd put it this way if we want current to flow, but we put it the opposite way. So we're going to put it like this. All right, and we're going to put this just like this. All right, and then we're going to take that to ground. We're going to go right here to ground. Okay, let's bend this, pre-bend this. Nice, nice. Always nice. Keep everything clean. All right, good to go. Now, at this node right here, this is now we should have 5.1 volts. Let's check that. We should have 5.1 volts right there right now. So this is going to clamp this voltage here. So we're turning on the power supply. Let's get our meter. Get our meter back in the scene here. And let's zoom out a little bit for you. Okay. Let everything stop shaking. Okay. Okay, so here we go. I'm going to go this way so you can see this. Okay, so I'm going to go over the Zener. So from the Zener to ground, this is ground right here. And, oh, what did I do? I forgot to put the meter back in the right mode. I got it in milliamp mode. I could have damaged it. All right, and again, you know, it's like flying an airplane. You got to do a checklist, right? You got to look at stuff. Okay, so let's do this again. Thank goodness that the designers of this equipment know you're going to do stupid stuff. So there we go. How cool is that? 5 volts. What's the power coming in? That's up here at the top rail. 12 volts. But somehow, magically, we're getting out this 5 volts. This is what the Zener diode does. It clamps the voltage. So we got 5 volts. That is really cool. Wow. Okay, now let's build the rest of the circuit. So we got 5 volts right here. Let's put our resistor in here. So we're going to put our we're going to put our 330 ohm resistor. And we're going to put it, and you know what? We're going to go right here, right at that node. We don't need another wire. So now we got our resistor. Okay. And we'll zoom in. Let's zoom in a little bit so you can see. All right, we got our resistor. Now let's put our LED, anode to cathode, anode on the left. There we go. All right, and now let's take it to ground. And so the current has a place to return. And the moment I've still got the power on, and I'm going to plug that in, and boom, there it is. It's on. So let's look now. What's going on here? So this Zener, so we got a rectifier diode here. We got a Schottky diode here. They're doing what they're doing. And this current is limited here. Through here is a gatekeeper. Through this 220 ohm, there's only so much current that's going to get through there, right? Now, some of that current is used to maintain this Zener regulation, all right? And then the rest of the current goes through this other branch of the circuit. But this voltage will stay the same here, all right? So now we've added some current here. We're drawing some current through here. So the Zener is going to have a slightly different voltage now, okay? And we're going to go there, and we'll go to ground. Let's get our meter, and you can still see that. Can you see that? Let me zoom out a little bit for you. Okay. All right, so we're looking from the Zener to ground, and 4.99. Wow, that's pretty cool. So we got 4.99, and so we've got this LED over here, and now what is the voltage over this resistor here? So the voltage over here is 2.9 volts. So we can compute the current in the LED branch. Let's do it. So voltage equals current times resistance. So current equals voltage divided by resistance. So the voltage was 2.9 divided by the resistance, 220 ohms, equals 13 milliamps. 13 milliamps. All right. So we've got 13 milliamps. So look at that. We just created a voltage regulator. Now is what I want to show you is something really cool. I'm going to put the meter on the circuit on the node here, on this node. That's supposed to be 5 volts, okay? And then I'm going to change what the input voltage is and make it not 12 volts. And we're going to see Can this circuit maintain regulation? Did we just make a poor man's regulator? Okay, so let's go back to the circuit here. All right, so let's just turn the power off. And again, if we're working with higher power and parts we care about and all that, turn the power off more, but I think we're okay. So we want to get the voltage off that node where that Zener is. Okay, so what I'm going to do is I'm just going to run a wire pretty long here. I'm going to run this wire all the way over here. Okay, so I got that wire right there. A little too bit of long wire, but it's okay. And now I'm going to put my little sensing socket here. And now we need to go to ground. So let's get a wire to go to ground here. Nice straight one. Okay. And again, it's about you don't have enough hands. You need to have 8 hands, right? Like a heptapod. All right. Or that would be 7 hands. I just saw the movie Arrival. That's going to date when this course was done in 2016. But anyway, they had 7 hands or 7 legs, heptapods. So that would be really nice to do electronics. So I'm sure they're very good at electronics. Okay, now we're going to plug this in, plugging our meter in. Okay, let's get everything back on the screen here. Okay, cool. All right, so let's straighten everything out. All right, so now here is what we're trying to figure out. And as a matter of fact, you know what? This is not good enough. I want to show you 2 things simultaneously. So I'm going to change the voltage on the power supply over there to the left on the bench from 12 volts. But we're looking for the power on the voltage on the Zener to maintain at 5 volts. All right, so I'm going to turn the power on now. And okay, so the Zener voltage is at 5 volts, 4.98, right? Okay, but as I change that voltage over there, you're not going to be able to see it. So I want you to be able to see it. So we're just going to have to get crazy here and get 2 meters out. Okay, again, that's why now you see why I have so many meters, right? And I've got, I think I've got about, I don't know, 15 meters, 15 actual really good meters. And then I've got boxes of hundreds of meters that go into products. All right, so we need the voltage on the power rails. All right, now I'm going to do a little trick right here. Can I do it? Probably not. So what I'm going to do is I'm going to connect this connector right into the power rails right here. And I'm going to put it like at a diagonal. Okay, so I've got, and as a matter of fact, I need to put it backwards. I need to put it like this. Okay, now up here we've just got plus, and down here we've got minus. I'm gonna run the minus up here also, okay, from the bottom rail. So I'm gonna run the minus up here so that I have minus and plus up top so I can make this measurement. Okay, now I'm gonna bring these cables around here. I'm gonna plug them in, and I'll straighten this all out in a second so you can see everything. Just bear with me a minute here. Okay. So now we got our whole circuit here. Let's just open this up a little bit. We don't need to be this close. All right, we got everything hooked up. So you can see everything's hooked up here. All right. So we got both of our voltmeters. We're going to measure what the incoming, what the voltage is up at the top rail, and we're going to measure what the Zener voltage is as well. Okay, so let's go ahead and let's turn this thing on, and let's hope that nothing explodes. All right, let's do it. So there we go. So we've got 12 volts coming in, 11.99. We got 5 volts there. Okay, so now there's a number of different things when you're talking about voltage regulation. All right, one of them is called load regulation, and one of them is called line regulation. Let's talk about load regulation first. Load regulation means as I change the load, so the LED and the resistor here, if we increase or decrease the amount of current, that 5 volts should stay the same. Now we're not going to do that right now. Right now we're going to do a different thing. We're going to do line regulation, and what that means is the voltage coming in is 12. It should, if it's 7, 9, 11, 12, 13, shouldn't matter. This should stay 5 volts. So how well it regulates the line power, the 12 volts coming in, is one parameter of how good the voltage regulator is. And then the other parameter is the load regulation. As we change the load, does the voltage stay stable as well? And we want both of those things to be perfect, right? I don't want to change, I don't want the voltage to change no matter what, right? Okay, so here we go. So I'm going to go over there and I'm going to actually change this voltage. You're going to see it change on here, so I can't cheat. But we don't want to see it change here much, right? And we could calculate for every volt here what it changes over here. So it's at 12 volts right now. So I'm going to grab the fine adjustment and let's see what happens. So I'm going to drop it down, and I'm dropping it, and I dropped it a whole volt, almost a whole volt. And let's get the course, and I'm going to probably overshoot it. Yeah. All right, so let's just go back up. All right, there we go. So there's roughly 11 volts, and we see that the voltage is almost staying exactly 5 volts. Okay, now I'm just going to do it with the course. So we got 10 volts, and it's barely, you can barely move this thing. And look at that, 4.8, 9 volts, 4.8. Let's see if we can put it down to 7 volts. 7 volts, 4.5. So, all right, we've decreased the power supply from 12 down to 6 roughly, right? So we've decreased it 50% down, but yet the voltage is only changed by roughly 0.8 volts, right? That's still pretty horrible, but it's not bad. So if it was just modulating around 12, it would stay pretty good, right? Okay, let's go in the other direction. So let's get it back up to 12. All right. And what I'm going to do here is I'm going to get the fine adjustment. I'm reaching over here, so it's a little bit hard. Okay, so we're at 12 and 4.99. Now I'm going to increase the fine adjustment slowly. All right, and see, we're staying now. We went up over 5, right? The circuit's being driven a little bit harder. There's a little bit more current in the circuit. But notice the LED is not changing brightness. And it shouldn't, because the voltage on it is still exactly the same. Very, very little change. Look where we are. We're at 16 volts, and we're still at a beautiful 5 volts. So this is really good at regulating a higher voltage. All right, and here we go. We're at 18 volts. All right, 18 volts, and we've still got barely 5.1. Look at that. That is beautiful. So this thing regulates really well as the voltage goes up over about 9 volts, right? So at about 9 in this particular circuit configuration, and then we can mathematically model this all out. But anyway, at about 12 volts, there it is, perfect. All right. So that was line regulation. So we see there is some line regulation, and especially as the voltage gets higher, this thing stays pretty stable, but it's burning a lot of current. As the voltage gets lower, it has a hard time maintaining regulation. Okay, now we aren't going to be able to do any kind of variation right now with load regulation because I haven't introduced potentiometers. I probably should have, but a potentiometer is a variable resistor, and right now I just want to use something discrete. So I'm going to turn off the power supply. All right, and now what I'm going to do is I'm going to double the amount of current. So we've got a 220 ohm resistor in there, right, in the LED circuit. I'm just going to double that. I'm going to make that a 100 ohm. So I'm going to double it plus a little. So twice the amount of current plus a little will be able to flow here. And let's put this in here. Okay. All right, and you know what? It's a lot harder than it looks to put little things in these little tiny things, you know, so, you know, you got to, like I said, wear magnifying glass eyeglasses will help not strain your eyes. Okay, let's turn it back on. So now we're doubling the current, roughly. So we're going to turn it on. There it is. We've got our 12 volts at the input, but now we've got 4.7 volts here. So what's happened? What's happened is we're drawing way more current through the LED circuit, and since we're drawing more current, this Zener voltage on this Zener is having a hard time maintaining this 5.1 because we're pulling all the current from it, and there's not enough current to maintain this Zener voltage. So let's look at the current. Remember, we calculated the current, and it was about, what was it, 13 before? It was like 13 milliamps, I think, something like that. Let's just measure it. Let's measure it over the resistor, and then we can compute what the current is in this part of the circuit. All right. And we've got 2.4 volts over that resistor. So let's do our math. So we want to compute current. So what's current? Current is voltage over resistance, 2.4 divided by the resistance, 220 ohms, resistor, divide, and, oh, I'm sorry, 100 ohms, 100 ohms. You guys got to help me out here. Don't let me make mistakes. All right, 2.4 volts divided by 100 ohms. All right, and that gives us 24 milliamps. So before we had about 13. Now we've got, you know, almost twice the amount of current, and that's why we're seeing that Zener voltage drop off a little bit, and it's only at 4.7. If we plug this one back in, this one is the Zener voltage. and it's at 4.7. Anyway, so that is some diode experiments, and that's how you use them. We forward biased them, we reverse biased them, we did Schottky diodes, we did Zener diodes, we did silicon diodes, we did LEDs, and you can have a lot of fun with these. You can actually build logic circuits with them, and what's called resistor. You can do diode logic, diode resistor logic. You can do lots of cool things with them. You can use them in power supplies, and they're really magical devices and the basis of a lot of things that we're going to do with semiconductors. Next, we're going to talk about transistors. All right, so next we're going to talk about transistors. So take a pause, take a break, and meet me back, and we'll do the transistor discussion and start into the theory of that, and then do some experiments with that. All right, so I'll see you then. Bye. All right, welcome back. We're on the next lecture, so hopefully you have had time to recover from our diode discussions. So that was pretty long. We went through a lot of material, a lot of theory and hands-on experiments. So we're going to do the same here with transistors, but let's take a look back and think. We've gone over resistors, we've gone over capacitors, inductors, LEDs, diodes, now transformers. We know Ohm's law, we know digital, analog, what the words mean at least, and we're really making good progress here. So after we get done with transistors, we're going to have a good set of building blocks to make a lot of really cool circuits. So let's see. So what we're going to do is we're going to do some theory, and then we're going to jump in, and I know I say this always, we're going to do theory, and then we're going to do the actual some experiments with transistors and play around with them. All right. So and this is, and I've thought about this. This is a really hard subject to teach in kind of a simple way. You really do need to dig down and do the math and do the physics and take time with it. But I want to show you at least a general overview of what's going on with the physics, something like we did with the diodes, and I think that'll be good enough. A really simple equation that models how we're going to use a transistor, and then later, as we go down further lectures, we'll kind of add to it a little bit. And of course, you can always on your own go and Google and look online and look for more advanced material. There's plenty of it. But what my goal always is to try and give you a working knowledge and hands-on technique so that you can actually build something and work with me as we build something and see the thought process. All right, so take a look at the screen here. So let's get right into this. All right, so we've got the transistor. So the transistor, and we're going to be talking about the bipolar junction transistor, BJT it's called. And this is a 3-layer device, and you're going to find 2 different kinds of transistors, which are the most common, and that's called a PNP and an NPN transistor, and it basically is talking about the doping. So PNP or NPN, it's just like the diode, which is just P and N. All right, and these transistors have 3 leads, and one is called the base, the other is called the emitter, the other is called the collector. All right, and before, so let's take a quick look. Let's take a quick look on one of the other bench cameras. I want you to actually see this. Okay, so here we have a 3906, and this is a PNP transistor, and we're going to look